Hi, welcome to Rosensteel. So it's a great pleasure to start off this the third Miami CAST workshop, summer school and winter. Yeah, so this has kind of been our norm that whenever we have a meeting that we hold in January before the semester, we always end up wearing our heavy coats when we've been advertising how warm and comfortable Miami is. So this follows that trend. I'm Paquita Zaidama. I'm chair of the Atmospheric Sciences Department here, and CAST is a collaboration between the College of Engineering and our department. So that's this is the third year that this workshop has been held, and it was at the initiative of the new dean. This collaboration between the two colleges. So it's really great to see this developing some momentum. And with that, I'd like to turn it over to Samuel, and we'll look forward to the talks.
All right, thank you so much, Paquita. And again, welcome everyone. Again, it's a kind of a cold day, unexpected here in Miami, but hopefully it warms up as you stay through the workshop. So again, welcome, and we'll kind of get started. So today morning we have a session with Malvern Panalytical and NETCH, and kind of talking about some of the advances in particle characterization and also in the terms of aerosols and sprays. So that's the Malvern Panalytical one, and you'll hear kind of developments in and kind of some of the background for techniques such as dynamic light scattering, electrophoretic light scattering, also kind of aspects of nanoparticle tracking, and then moving on to kind of some of the kind of techniques which are utilized for characterizing sprays, which kind of falls within the context of aerosols and a lot of the work that's done within CAST as well. So I think as part of CAST, we do kind of the whole area of nanoparticles and then aerosols. So we tried to bring together technologies which are utilized in that context. So on one side, it's a characterization of the particles and particle size distributions, but then also incorporating them into formulations and other aspects. So we kind of bring in the aspect of some of the physicochemical properties through rheology as well. So you hear some of the kind of applications of rheology and measurement techniques and rheometric measurement techniques as well from NETCH. And also kind of grinding and milling as well from kind of getting particles to the right level of sizing. So without further ado, I think we'll get started. So I'll kind of invite over Raghi from Malvern Panalytical to start us off and talk about some of the particle characterization techniques which are being developed and are present at Malvern Panalytical. Thank you, Raghi.
Thank you, Samuel. And yeah, you don't have to convince me too much to shovel snow to get my car out and fly down to Miami. So I appreciate the invitation and the collaboration we've had for many years with Samuel in many different forms. So yep, as Samuel said, my name is Raghi Ragam. I'm a senior specialist with Malvern Panalytical, having worked with the company for a number of years on nanosite and Zetasizer nanoparticle tracking analysis, dynamic light scattering, electrophoretic light scattering, and a couple other technologies we've got at Malvern Panalytical. Just as a quick overview, you've got your regional account manager here, Bill Saskowitz, who's joined me today, along with Ash from our food and pharma sector. But we've got a whole suite of tools that you can come up to us later and talk to us about, covering all other types of techniques and metrics beyond what I'm going to discuss today. So, feel free to reach out to Bill as we proceed throughout the week. So let's, get into some of the techniques we've talked about. We're going to talk about particle size, concentration, zeta potential. There's a lot of resources you can, use to explore those techniques. And so we'll start right into dynamic light scattering. Dynamic light scattering is a technique that's used to look at the scattering intensity of particles moving around in Brownian motion. What we're doing is we're looking at the fluctuations of the signal coming from those particles as they move around. And then we reinterpret that information to determine the size and size distribution of your particles in a sample. And so as you look in literature, there's a lot of synonyms for dynamic light scattering. It's also known as quasi-elastic light scattering or photon correlation spectroscopy. In any case, they all refer to the scattering intensity fluctuations that are used to analyze the diffusion movement of those particles moving around, and then using that to determine their hydrodynamic size. And I'll define that term further here in a moment. But when we talk about light scattering, we're looking at how particles are experiencing an incident beam and then absorbing those particles and scattering photons in different directions. And so you could have particles scattering photons in different directions based on their size. If they're pretty small, they'll scatter light evenly in all the different directions, and that's called isotropic scattering. If they get a little bit larger, then they'll start to scatter light more in what's called Mie scattering, or more in the forward direction. But in any case, how those particles scatter light, is determined by their size and other characteristics. But when we talk about light scattering, when we have larger particles in the presence of smaller particles, what we find is that larger particles will scatter light to the 6th power more than smaller particles. So, dynamic light scattering inherently is a intensity-based distribution. So you have a laser, going through a sample, the sample scattering photons coming back to a detector. And so what you can appreciate is that it's a non-invasive technique for measuring the size of particles and molecules in suspension. And it will look at the Brownian motion, which is the random movement of particles as they're being bombarded by solvent molecules around them. And so DLS inherently measures the diffusion of these particles undergoing Brownian motion. And here's just whoops, that didn't quite work. I'm gonna mute this. So you can see that Brownian motion, again, larger particles will move slower, smaller particles will move faster. And what we're seeing is the Brownian motion is dictated by that bombardment of the solvent molecules. Okay. So what that leads to is that small particles will have faster Brownian motion, lead to faster intensity fluctuations. And conversely, larger particles will have a slower Brownian motion, leading to slower intensity fluctuations. So that you can see that here. And when we talk about Brownian motion, if we want to quantify it, what we're doing is actually looking at the translational diffusion coefficient. And so for people who are online, maybe can see me. When we talk about translational diffusion coefficient, translational means that it's, we're looking at, a very, well-defined movement. Rotational diffusion is the particle moving in place. So that's just a kind of a quick definition of translational versus rotational diffusion. And then in any case, what we're doing is we're looking at the translational diffusion coefficient, capital D, and relating that to the hydrodynamic diameter with an equation called the Stokes-Einstein equation, where you can see the variables that affect that relationship are primarily the temperature of your solution and the viscosity of your solution. So Brownian motion is dictated by the size of your particle, the viscosity. If you know the solvent viscosity, sure. But if you get to a concentration that's a little bit, too high, and then you have to consider the bulk viscosity of your sample. And then also the temperature. And so the temperature, when you're measuring it, in a DLS system, will, usually be set at a particular temperature. You can do thermal ramps and isothermal experiments. But in any case, it needs to be stable so that you can then appropriately account for the size through the Stokes-Einstein equation. And so when we talk about the hydrodynamic diameter, the size of the particle, the ISO definition is noted here in boldface and in red. And it's the radius and diameter of a hard sphere that diffuses with the same diffusion coefficient as a particle or molecule being measured. So that means that, it accounts for anything around the particle that will affect its diffusion movement. So it's not just the core of the particle, but it would also be any ions around it, the ionic strength around your particle, any surface structures around your particle, and the shape of your particle. All those play into the determination of your hydrodynamic diameter. And so when we look at, determining the hydrodynamic diameter, we're looking at, these fluctuations of particles moving around in Brownian motion. We look at the signal of these fluctuations and map the change of that signal over time. And we do that on fractions of a second, microseconds, where we relate the original time point and then see how that changes. And you can see that further actually in, this slide, where again, if you have particles that are completely stationary, they'll, scatter photons coming back to the detector, and they'll have a static signal. But because particles are moving around constantly in Brownian motion, that signal that's being at the detector is fluctuating. And so that's what you see, is that as you have smaller particles, you might have that more frequent intensity fluctuation. If I'll let the video catch up here in a second. So again, smaller particles moving quicker in Brownian motion. So when you look at the intensity fluctuation, you see it's more frequent over time. And then, excuse me, larger particles will have a slower Brownian motion. So they lead to a slower intensity fluctuation, or a less frequent intensity fluctuation over time. So then what we do is we map out the change of that signal over time by looking at rapid snapshots in time on the order of microseconds, and we look at autocorrelation. So what happens is that you'll find that the intensity fluctuation at time 0 is such, but as time progresses, that signal changes, and we're correlating it, and we're mapping out what it essentially is a decorrelation in that signal over time. So you can see that the correlation coefficient is dropping as time progresses, to the point where, over a certain amount of time, it's completely decorrelated and you have a flat baseline. So larger particles, you might find that it takes a little bit longer for that decorrelation to occur. And then with smaller particles that move faster in Brownian motion, you'll see a quicker decorrelation over time. And so what we do is then we're going to look at the correlogram. We're developing that correlogram in a stepwise fashion here. Again, we see the intensity fluctuations that are pretty frequent for small particles, less frequent for larger particles. On a linear time axis in the middle panel here, you see, the rapid decorrelation for small particles, a slower decorrelation for larger particles. And then essentially, at the end of the day, we're actually plotting the correlogram on a logarithmic time scale. So this is essential because whenever someone comes up to a DLS system and they want to measure the size distribution, we always say, look at your correlogram first, because the correlogram is going to tell you about different characteristics within your sample, and then enable you to get more confidence in what your data looks like. You could have some samples that are not quite suitable for analysis in terms of like their nature or their prep, and you might get a nonsensical correlogram but still get peaks in the size distribution plot. So just because you get peaks in the size distribution plot doesn't mean that it's reliable data. Now, within our software, we've got checks and balances about how to trust the data, but it just should be second nature so that you understand the theory and be able to have more confidence yourself in how the data is collected. So when we look at the correlogram, we can actually look at different parts of it and note different characteristics. So the y-intercept is your signal to noise ratio. Ideally, and in a theoretical setting, you have a correlogram, you have a y-intercept of 1. But because there's some aberrations and things like that, you won't always have a y-intercept of 1. A good signal to noise ratio will be a y-intercept of 0.7 to 1, somewhere in that range. And then where you see the onset of decay, that's dictated by the size of the particle. As we just showed in the previous slides, if you have smaller particles, you might see a quicker onset of decay. Larger particles will have a slower onset of decay, just because they're moving in Brownian motion a little bit, little bit slower. And then the gradient will tell you about the polydispersity of your sample. If you have particles that are all the same size, they're all diffusing at the same rate. And so over time, they're all going to move away from each other and decorrelate pretty quickly. And so you would have a steep gradient if your sample is more homogeneous. If your sample is more heterogeneous, you've got particles moving at different Brownian motion rates, diffusion rates, and so you might see a shallow decay or a step decay in some cases. And then finally, the last part is the baseline. The baseline will tell you about the presence or absence of any large scatterers that are present in your sample. If you've got some large aggregates or scatterers present, they might pop in and out of the scattering volume within the system and offset the count rate, leading to a really noisy baseline or a raised baseline or some form of disrupted baseline. So that's, a quick overview of the corellogram. There's a lot of math on here, but essentially what the point here is that, when we talk about a size distribution, we want to look at the width of that distribution, and we can use the width of that distribution to calculate the polydispersity index. How heterogeneous is your population or your size distribution, or how narrow is your size distribution? And essentially, the polydispersity index is calculated by looking at the standard deviation divided by the z-average diameter with the whole term squared. So, switching gears a bit, when we talk about, developing the system in terms of how you can actually get confidence in the data, what happens is that when you make a DLS measurement, it's actually a series of subruns. And what we're doing with adaptive correlation is we are looking at those subruns and teasing out any outlier events by the z-average, the average diameter, and the polydispersity index. And when we do that, we are actually now filtering the data, so we are showing a bulk representative of the data. And that's what we call steady state, a representation of the bulk of your data. Any outlier events would be called transient data. And then, you can always look at unfiltered data as well. But that's just part of the adaptive correlation. Malibu Analytical has, taken a really good stab at, giving a higher confidence in the data that's represented. So when we talk about outlier events, what could that mean? It could be dust, could be aggregates, filter spoil, being mindful of the choice of filter, so that you don't have filter debris coming off if you haven't selected the correct filter. Making sure that you've got clean glassware, some of the logical steps that anybody would take to make sure they've got, a clean and well-defined experiment. So, but in any case, usually that, the dust are usually much larger particles than what is the typical population of a sample, and you'll find that it'll result in kind of a noisy baseline in the corellogram that we just discussed. You also might find it'll cause what is called number fluctuations. So because you have these large particles that are popping in and out of the scattering volume, they might cause, these number fluctuations in the count rate. When we talk about count rate, we're talking about photons per second, kilocounts of photons per second. And so they might result in a y-intercept that's larger than 1, which is the theoretical maximum. And so when you have something above the theoretical maximum, that's a nonsensical data. Those are number fluctuations caused by any large aggregates or debris or dust that might be in your sample. So adaptive correlation, you can see here that when we look at a corellogram, this is the steady state data. This is the representation of the bulk of your sample. If we look at the transient, you find that the outlier events by themselves produce a nonsensical corellogram. You have something well above the theoretical limit of 1 for the y-intercept, and you have a very disrupted gradient and almost a non-existent baseline. These are just outlier events that are not really being well defined. And if you were to look at the unfiltered data, you find that those outlier events really have a weighting against the bulk of the data. They raise the baseline, they raise the y-intercept, and so forth. So you can see that the default is steady state. Steady state will give you a good representation of the bulk of your sample. So it's a lot quicker, it's a lot more robust, steady state. For those who might have experience with our kind of a previous generation of systems, you might have seen something like this if you look at a lysozyme and a buffer, but then with adaptive correlation, you can clean up the data, get a better representation of the bulk of your sample. So, excuse me. We want to, promise everything under the sun, but we're realistic and we can't, right? So there are limitations to the system, to DLS in general. And part of that, the limits are about 0.3 nanometers to about 10 or so microns in diameter. On the lower end, it has to do with just being able to, track the Brownian motion enough, having enough photons coming from a particle. We've been able to publish and show that we can look at cholesterol and sucrose down to the 0.3, 0.6 nanometer range. We use that as our benchmark and actually how we spec systems and so forth. And then when it gets to the larger side, it's really about, will the particles stay in solution, will stay in Brownian motion, or will they just start to settle out of the beam? And if that's the case, that's kind of what dictates the upper limit as well. And so when you get to the larger particles, it's also a matter of statistics. You might have fewer larger particles present in your scattering volume. You need to be mindful of that. So in any case, there are lower limits and upper limits to the system. Has to do with optical configuration and the detector choice, the refractive index of your sample itself. Upper limit, you have these effects that you'll come across if you have a higher concentration. You'll have something called multiple scattering, where you might have photons bouncing around neighboring particles in the scattering volume. And what that does is when the photons bounce around neighboring particles at a higher concentration, they'll diminish in intensity, causing the software to think that you've got smaller particles than you truly do. You also have a converse effect where you might have restricted diffusion. So at a higher concentration, you might have some particles repel one another, causing multiple scattering. At a large, and in some cases, you might have particles that are attracted to one another at higher concentrations, causing restricted diffusion. In any case, you need to be mindful of the particle-particle interactions, whatever they may be, at higher concentrations. So whenever you make a measurement, it will behoove you to do a series of dilutions, serial dilutions, to make sure you map out the appropriate concentration range, especially if you're, let's say, analyzing a sample of its, first of its kind, and then you can map out the appropriate concentration range. And then as you analyze further similar samples, you can apply that, concentration or dilution factor appropriately for further samples. So, ways you extend the lower limit might be by the optics, the backscatter. Backscatter is the angle of detection. We'll talk about that here in a bit, but it maximizes the scattering volume, and you can pick a higher laser power to get that extra sensitivity, to extend the lower size and concentration limits. So, along those lines, when I talk about non-invasive backscatter, so when we talk about the laser source, we have got a laser source, and then you have a detector that can come at different angles. So backscatter detector will give you a larger geometric scattering volume within your sample, within the cuvette. And then it also enables you to adjust the measurement position so that you can handle higher concentrations of your sample. So in this case, you can see that if you have a dilute sample like the one on the left, you can measure in the center of the cuvette, with no problem. But if you were to measure in the center of the cuvette on the right side, you'll see that those, photons in the center of the cuvette might bounce around neighboring particles and diminish in intensity by the time they reach the detector. So that's the multiple scattering effect. To overcome that, what you would find is that you can actually adjust the measurement position, measuring closer to the cuvette wall, and that will mitigate that multiple scattering effect. You'll find photons, coming off particles closer to the cuvette wall will scatter directly to the detector instead of bouncing around like a pinball machine in the center of the cuvette. So again, multiple scattering effects are things that you need to be mindful of when you're extending the concentration, the upper concentration range. So You can see that when, you know, if you're analyzing something, sample A would absorb too many photons, you might not get reliable data. But, you know, sample B passes what I like to call the finger wagging rule. If you're holding the cuvette up to your eye, you wag your finger behind it. Can you see your finger wagging behind the cuvette? Excuse me. So there's a number of cuvettes that can handle, you know, aqueous-based samples. If you're using organic solvents, there's glass and quartz cuvettes and so forth. I talked about, you know, 10 microns being the upper limit for DLS in general, but we can actually push that a little bit more. You know, we have something called a low volume disposable sizing cell. And what that does, it's a capillary that fits into an apparatus with a magnetic clasp that helps push that upper limit a little bit more. It utilizes only 3 microliters. You know, it's glass, so you can use it for aqueous or organic solvents. It uses a side detector angle just because of its configuration. And you can, you know, dip the capillary into your sample, or if you're fastidious, you can just micropipette your sample into the capillary. But basically, what it does, it also, in addition to it utilizing 3 microliters, you know, low volume, being glass or aqueous and organic solvents, it will also reduce sedimentation and convection. So when we talk about the upper limit of DLS, you can actually use something like the disposable sizing cell to push that upper limit. We've shown data where we can get samples analyzed up to 15 or 20 microns in diameter when you think about the scope of DLS. So, you know, you can see the reduced percent error for that range and you know, get some higher than typical DLS measurements. So when you are looking at parameters that you need to know about for DLS, the raw form of the data is an intensity-based distribution, as I described before. Larger particles will scatter light to the 6th power more than smaller particles. So when you are looking at intensity-based distribution, you need to know the sample viscosity or the bulk viscosity, depending on the concentration, and the dispersion refractive index. And then if you want to convert that to a volume-based distribution, depending on the size of your particle, you might be experiencing me scattering or not. If your samples are about 200 nanometers or less, then they'll scatter light more isotropically. You won't necessarily need to know that much more about your sample. If your samples are about 200 nanometers or more, then you'll need to know more about the refractive index and the absorbance of your particle, and to convert that from intensity to a volume-based distribution. So by ISO standards, what DLS provides is the mean size, which is defined by the cumulus mean. Again, it's the total average, which can be susceptible to aggregates that are present in your sample. The width of your distribution, the polydispersity index that I described, and it will also look at the size distribution, typically at a 3-to-1 peak-to-peak ratio in terms of resolution. So dynamic light scattering, it's a well-established technique. Very little volume is needed, can be sensitive to large scatterers, and that's just kind of DLS in a nutshell. So there are other types, extensions of DLS that you can use to get some extra information. So one of these is multi-angle dynamic light scattering. It's the idea that large particles might be non-isotropic scatterers, meaning they scatter more in the forward direction, and so you might find that as you look at different angles, you might have slightly different size distributions. So what multi-angle dynamic light scattering does is that it will take information from the back, the side, and the forward angle, the raw correlograms from each of those angles, compile them, and get you an angular independent analysis, giving it with higher resolution. So DLS typically, like I said, gives you a 3-to-1 peak-to-peak ratio. With models with multi-angle dynamic light scattering, you can get down to a 2-to-1 to peak-to-peak ratio. So, it'll give you intensity, volume, number-based distributions for each of those angles. data quality guidance and so forth. But models doesn't give you just an overall correlogram. You have to look at the correlograms for each of those individual angles. Nor will it give you an overall z-average or PDI. You have to look at the z-average and PDI of each of those different angles. But models does give you, the higher resolution distribution. So limitations of one angle will be the limitations for the whole measurement. So if you think about the side detector angle being susceptible to number fluctuations, that means that, the upper limit for using models is about 500 or 600 nanometers in diameter. Forward scatter is going to be susceptible to multiple scattering, so the concentration should be relatively low when you want to use models. And then you can always look at, the quality guidance for each of those individual angles to get a good sense of whether models has worked for your sample or not. So you can see an example here where you have single backscatter angle giving you a distribution around 7 or 8 nanometers or so. Models can actually tease out a 10 nanometer and a 5 nanometer peak within your distribution. So you can do an extension of models, looking at particle concentration, particles per mil with a DLS system. That's an extension of the model's measurement. It will take, the scattering per particle, a lot of factors, and actually calculate, the particles per mil per peak. So a lot of input parameters. I'll skip a little bit through this if you don't mind. And then you get a total, particle concentration, distributed particle concentration, and cumulative particle concentration. Things that will affect that that determination would be the viscosity, making sure you understand and know what the viscosity is of your sample, knowing what the electrical double layer is. So if you are, introducing different salt concentrations around your particles, that will be good to know. And also having a good understanding of your material's refractive index. Those variables will affect the determination of your particle concentration. So, there are a lot of things to consider when you're wanting to improve the accuracy of particle concentration. That's the viscosity, the electrical double layer, refractive index, aggregation, and restricted diffusion. All of these factors come into play. And there are some cuvettes that are, better suited for these models and the particle concentration. You have a way of developing methods and so forth. I'll skip over a little bit of this. If you want to see, you'll see it in action when we have the hands-on session tomorrow. But, dynamic light scattering can really give you a lot of information about trends that's happening in your sample. So if you have, let's say, a polymer particle that's swelling, you can do a temperature trend. You can, incrementally increase the temperature and watch the mean count rate decrease as as a polymer is swelling. You can also see obviously the size increase because with swelling the particles are becoming larger. And so you can really tailor a DLS measurement, many different ways to suit your research needs. You can also look at how things might be susceptible to temperature changes, and causing aggregation or denaturation of your particular sample if it's more biological in nature, or otherwise. There's a lot of other things that you can do. With a DLS system, you can also get a titrator, get some better understanding of pH trends. So if you're looking at isoelectric points for your sample, you can do that a little bit more automated. And if you have complex samples with complex viscosities, you can get a viscometer to get, a quick measurement of the viscosity and use that value and input it in the software. So there's a lot of things to glean from dynamic light scattering. Again, the things to keep in mind is that large light scattering particles, light scattering is proportional to the 1/6 of the diameter. They are susceptible to aggregation and dust and things like that, so you need to be mindful of it. Along those lines, avoid sedimentation and number of fluctuations. You want to model an appropriate concentration range. So if you're coming up to the sample, at least, do the finger wagging rule, and then, go through 5 or so dilutions to kind of map out the appropriate concentration range. you can start with a higher concentration and dilute down. That's usually an easier approach. And again, along those lines, watch out for those particle-particle interactions such as multiple scattering. And then you can also look at, the sensitivity over time. And, just the last statement is not even a zeta, a DLS statement. It's a logical statement. Just do repeats. I always say, do 5 repetitions, because if you have 5, 1 outlier, you still have N of 4, 2 outliers, you still have N of 3, and you keep reviewers happy when you're looking at manuscript publication. So, pretty, easy. It's a relatively easy system, easy approach, with little volume, little requirements, and there's a lot to benefit from dynamic light scattering. How am I doing on time?
Yeah, it's about 5 minutes.
Oh, geez. Zeta potential. Okay. I did not adjust this appropriately. Sorry. Okay, so dynamic zeta potential essentially is looking at the colloidal metrics, colloidal stability of your sample. You can look at how particles are moving around in response to an applied electric field, and look at how how stable your sample is. If you have samples that are less stable and crashing out, they'll get more zero. They'll get down to 0 millivolts in nature. And you can analyze zeta potential for particles up to 80 or 100 microns in diameter. And what we're doing is we're looking at the interaction between the particle surface, the valence charges around a particle surface, and the dispersant. So if you change the dispersant, you're changing the zeta potential. So there's a lot of different, factors that come into play, ions, cations, and so forth. So did not time this well. So you can come talk to me about zeta potential as well. NTA, yeah, we'll do that. Fair enough. The last thing I want to talk about is nanosite, or nanoparticle tracking analysis. What we're doing, I'm going to get straight to the theory. So when we talk about nanoparticle tracking analysis, this is a separate technique. What we're doing is we're looking at particles moving around in Brownian motion with a camera. We're looking at the light scattered off particles moving around in Brownian motion with a camera and an objective lens. And what we're doing is we're looking at the frame-by-frame movement of those particles. And so we can determine their size, we can determine their concentration. Technically, this is a number-based distribution. And thinking about the comparison to zeta size, the DLS, that's an intensity-based distribution. This is a number-based distribution. And we can look at their concentration of particles. We can look at fluorescence, look at percent labeling of your particles. And again, you can see that we're not looking at direct image of these particles. We're looking at light scattered off these particles. And so mean square displacement is actually what we're using to determine the hydrodynamic diameter. This is a variation of the Stokes-Einstein equation. And then we can look at the number of particles per frame, calculate their concentration on a frame-by-frame basis, and in a short period of time, in the order of a few seconds, you can get an absolute number average in terms of particles per mil for your sample. This is the general apparatus. So you have a laser module going through the prism, scattering to a suspension of particles. Those will scatter light. We're looking at with a camera and an objective lens and looking at their movement. The limits, the size distribution is a little bit tighter. The size limits are a little bit tighter than Zetasizer, or the DLS system, I should say. On the low end, it has to do with the material refractive index. Denser particles will scatter light a little bit more efficiently. You can push the lower limit down to about 10 nanometers. On the upper range, you can get about 1,000 nanometers. That has to do with the retardation of Brownian motion. A particle gets too large for it to move enough distance between frames to be tracked appropriately. Concentration, you can go from 10 to the 6th, 10 to the 9th particles per mil. On the low end, it's a matter of statistics. On the high end, it's being able to distinguish one Brownian motion track from another. So essentially, that's what's happening, is that you have you're tracking those particles moving around on a frame-by-frame basis. You can see the red Brownian motion tracks. here. So that's what we're doing when we talk about dynamic light scattering. You have the ability to look at, put a filter in there, look at subpopulations that are fluorescently labeled, get percent labeling of your particles, and get really high resolution data. It's a number-based distribution, so you can gate, your population and say what percentage of my particles or what's the concentration of a sub-range within the total population, and get, some really high resolution data from there. Okay, from there, I will stop and switch over to Daniel, who will follow me talking about spray tech. Thank you so much.
How about Q&A session after the talk?
Let me just share the slides.
Yeah, sounds good.
First one. It's the DM targeted delivery. Is it this one?
Yeah, it could be that one.
Yes.
So I thought it was gonna be a lot warmer here in Florida. Still is a lot warmer than in Colorado. So I'm happy about that.
And then this is
Perfect, thank you so much. Sure. Hello, everyone. My name is Daniel Mangel. I'm an application scientist for Valve Impact Analytical. Today, we're going to be talking about laser diffraction, specifically about sprays and aerosols. We're going to be looking at the spray tech. The title of my talk is Targeted Delivery, Designing Sprays to Go Where You Want and Avoid Where You Don't. Hopefully, by the end of this talk, you can actually understand what that title means. So we'll start nice and slow, nice and small and slow. So what do we mean by a particle? What is a particle? So a particle can be described as a discrete subportion, usually much smaller, of a substance. For example, we could have solid particles. These could be like table salts in an air. That would be a solid particle, but we could also have them in a suspension. So, perhaps rocks in water, you could think of it that way. We could have gas bubbles, and we could have gas bubbles in a liquid medium. So, for example, the bubbles that you would have in a Coca-Cola this afternoon. We can have liquid droplets as well. So we could have liquid in air. So, for example, sprays, or we could have liquid in liquid, so some type of emulsion. We could have little fat droplets in some type of aqueous suspension. For example, some of the milk that you added to your coffee this morning. I missed breakfast today, so you can see that I got food on my mind. So laser diffraction measures particles in the size range from nanometers to millimeters. It's a huge range. It's 10 to the factor of 6, very broad range. And it does so with really excellent repeatability as well as accuracy. So particles come in many different shapes and sizes. How is it that we describe these particles? How do we describe the size of these? So we can see in these images, we have this nice kind of crystalline material, some type of API, some type of active pharmaceutical ingredient. Top right, we have these like plaque-like shapes, some type of agglomerates, some kind of cruder material. The bottom left here, we have these rod-like, these needle-like shapes. And at the bottom right, we have these very spherical droplets in some type of emulsion. So how do we describe the size of these particles? This brings me to the concept of equivalent sphere diameters. So if we take this rectangular box over here, how would we be able to describe this in the idea of a equivalent sphere diameter? Well, basically what this means is that we can find a volume for a sphere that is equal to the volume of this box. And this becomes a very useful tool for us to describe different shapes and sizes. Excuse me. So I won't talk too much about this, but something that's very important to know is different particle size and techniques will report different equivalent sphere diameters. So I think the easiest way of thinking about this is if we think of a sieve. So a sieve is just, some aperture. We're going to have a particle that goes through this aperture. We're going to be able to describe that as the diameter of that sieve. We know that our particle is going to be smaller than that diameter, so it goes through it. laser diffraction, which we will be talking about exclusively today, gives us the diameter of a sphere of the same volume. So it's a volume-based technique. We'll be looking at volume distributions. So how does laser diffraction work? This image is a little dark, but hopefully you can kind of see it. We have this kind of central spot here. So this is a diffraction pattern. We have this central spot here. It's characterized by a very bright spot in the middle, surrounded by these bands of light and dark rings separating from the center. Based on the intensity and the separation of these bands, we can actually calculate the particle size distribution. Laser diffractometers are really simple instruments. Basically, all we really need to use one or to create one is we need some type of laser light source. So for ours, it's a helium neon gas 633 nanometer light source. We can pass it through a series of optical systems, and then we get into this measurement window. As the particles flow through this measurement window, light is scattered off of them from our laser. We can then collect the scattered light on our detectors using a Fourier lens. Once it's on the detector, we can determine the intensity and the angle. And from that, we can calculate our particle size distribution. In addition to that, we also have this obscuration detector. So this is going to determine how much light has been blocked by those particles. And this is useful in determining if, our sample is too concentrated, are we getting multiple scattering, are we, having other issues that we can kind of solve from that. So let's talk a little bit about light scattering. We have this fairly large particle here, and when our laser diffracts off of this, we have two things. Larger particles tend to scatter larger or more intensity, and they do so in a small angle. Here we have our diffractogram over here. So we have this central spot, and hopefully you guys can see this clearly. You can see the light and dark bands that are coming off of this spot. So we have really good resolution with larger particles. As we get to smaller particles, you can see a few things. First, these arrows are a little bit smaller, might not be so intuitive, but they're smaller, indicating that there's less intensity coming off of them. Furthermore, they scatter light at a larger angle. And what happens is we kind of get this diffuse pattern that is seen over here. At some point, this is actually going to be our limiting, our bottom size limit. And what happens is it becomes so diffuse that we can no longer determine the spacing and the intensity between the bands. And this tends to happen in the nanometer region. Of course, say we're using a 633 nanometer laser and we're trying to measure a particle that's 100 nanometers. Our particle is now much smaller than the wavelength of the laser. So you can imagine it. So our wavelength is somewhat like a ruler. As our particles get smaller and smaller, that ruler no longer becomes useful. So we have to go to a smaller ruler, right? We have to go to a smaller wavelength to get better resolution. And at some point, that no longer becomes laser diffraction. We're talking now more about X-ray diffraction or some other techniques. So we have a kind of a bottom limit using laser diffraction. That's somewhere around like the 10 to 100 nanometer region. For our master size, we tend to advertise 10 nanometers, but that might be pushing it just a little bit. Typically, it's somewhere around the 20 nanometers to 50 nanometer region. Here we have our Spraytec system. So this is our laser diffractometer that we use to measure sprays and aerosols. Very simple system, as I mentioned. Most laser diffractometers are very simple systems. On this left side, we have the housing, the laser housing unit. It's a helium neon gas powered laser. And it passes through a series of these optical lenses, which then push it through our measurement zone. On the right side, we have the housing unit for our detectors and our data acquisition systems. It's separated by some type of space, and it's on this nice little bench. In our measurement zone, we can measure pretty much anything within reason that we push through this. So we could have particles, sprays, droplets, or actual powders. Very useful system, very robust. We can get a lot of information from this, and it has a wide range of applications, just pretty much because anything you put in this measurement zone will be measured. So how does it work? Well, initially, we're gonna get a scattering data from our instrument. From this data, we're gonna plug this into a optical model. I won't be talking too much about these optical models, but it could be, say, the Fraunhofer method or the Me theory. Both have some validity, but we won't get too in depth into that. The optical model is then gonna try and fit theoretical data to match our experimental data. It's going to do this through an iterative process. And once it's been able to fit this data, we can then get our particle size distribution from this. So it's kind of an interesting process. We have our initial data that we measured, and then we take a theoretical model and we keep plugging in this initial data, and we kind of fine tune it. With the theoretical data, we know what the particle size distribution is. So once it matches our what we observe in the instrument, we can actually get our particle size distribution. So why do we want to use laser diffraction to measure these spray droplets? Well, it's a very well-established technique. It's a very well-established technique. You know, ISO has kind of some guidance on it. It describes the general principles of the technique, as well as the expected performance of it. Has a wide dynamic range. So for the spray tech, it's 0.1 microns to 2000 microns. It takes very rapid measurements. So in 1 second, it'll take up to 2,500 individual measurements. So what that really means is that we can assess spray events that occur very quickly, and we can also assess continuous spray events in great detail. Furthermore, it's very repeatable. As I mentioned, in 1 second of measurement, we can take maybe 2,500 individual measurements. And these individual measurements will get averaged into a single result. So it's a very repeatable, very robust method to use. Overall, it has a very high sample throughput. Each measurement only takes perhaps a few minutes to do per sample. And that's taking 5 repeats. It's really quick. If you have a spray, you can just spray it through the laser and that's it. You get your data. You want to do 5 more times, that works. You want to move on to your next sample, it's ready to go. So overall, very high throughput system. Furthermore, it doesn't require calibration. This is because it's based on a first physical principle, and therefore we don't need to calibrate it. We can verify it using standards, and that way we can just ensure that it's working correctly. So what are the applications of laser diffraction? So laser diffraction is quite important in a variety of industries. Particle size correlates to a wide range of physical properties. So in the pharmaceutical world, we're talking about solubility, content uniformity, stability. Are we forming aggregates in solution? Are we breaking apart our particles in solution? And deposition. So for example, we'll be talking a lot about targeted deposition. So inhalers or nebulizers, and getting those particles into the portion of your lungs that really matter. However, it's also used in many different industries. So in the food and beverage industry, particle size is critical for flavor, critical for mouthfeel and texture, has a big role in that industry. And for the materials industry, we have it can be a predictor of reactivity, it can be a predictor of strength and the curing properties of your compounds. It's quite important for the appearance. So for paints and coatings, it's really important, as well as for viscosity and the flowability of powders and whatnot. Today, we're going to be kind of focusing on 2 applications, the targeted deposition, and we'll be looking at nebulizers, as well as dry powder inhalers, as well as briefly just some domestic products and personal care products. So inhaled drug deposition. What are some of the important parameters when it comes to inhaled drug deposition? First and foremost, the patient is critical. And now it could be a human patient, but we could also be talking about veterinarian type practices where the patient is, say, a cat or a dog or a horse even. And if anybody here has ever had to give their pet any medications, if it's an oral medication, it's not necessarily a very easy thing to do. They tend to resist quite a bit. And when we get to larger animals, say horses, for example, it becomes much more challenging. So if you're trying to give a horse eye drops, horses are very smart animals. They're very strong animals. And what happens is they'll see you coming up to them, trying to give them an eye drop, and they will close their eyes and they won't open it until they know that you've left. And you can't pry a horse's eyes open. They're very, very strong creatures. They have very strong eyelids. And so you can't do that. And what they do instead is they surgically implant a tube that goes from the back of their shoulder all the way up through their neck and under their eyelid. And then they'll put the eye drop in this tube and and that's how they get eye drops in horses. So, you could imagine that, say, putting a mask on a horse might be a better way of delivering drugs to that horse rather than having to do that whole surgical procedure. Within a patient, the lung anatomy is really quite important. The age, the disease state, the breathing pattern. So each human is going to have a different breathing power. They're going to have different force of inhalation. So all these are considerations that you have to take in. In addition to this, the aerosol generating device is going to be quite important, whether we're using a nebulizer, whether we're using a dry powder inhaler or a metered dose inhaler, or even a nasal spray. All these are going to produce different particle sizes, and they're going to be able to target different areas within your body. As well as the particles themselves, the physical characteristics of the particles themselves play a critical role in this. So size, the shape, the density, the charge, and all the other physical parameters. But amongst these, size is the most important parameter that we look at. So let's talk a little bit about dry powder inhalers. So here we have an image of a dry powder inhaler. They're quite useful devices. So how they work is you'll have a dose. It's going to be a pre-weighed dose. This could be in the form of a capsule, or it could have some, some engineering behind it, so you don't necessarily have to put capsules in it. And how this works is when the device is actuated, so when the patient breathes in on the device, the airflow is going to carry the powder up through the device. After that, the powder is going to be subjected to shear forces, and that's usually within the device itself. Either we'll have some type of twisting and spiral-like features in the device. And what it does is it actually will de-agglomerate some of the particles. It breaks these particles apart, which is a very important process for these, because when you're targeting your lungs, you need the particles to be fairly small, very small, actually, between 1 and 10 microns. And we'll take a look at that a little bit more in depth on the next slide. And so if you're forming aggregates, your drug particle is forming aggregates, it's not going to get to the desired location. Another important thing I should mention is that all the energy that is used to break these particles apart is actually coming from the patient. So a patient's breathing force is going to be different from one another. So it's kind of a tricky process. Typically, the drugs are, as I mentioned, 1 through 10 microns in size. This is to ensure that it actually penetrates to the proper regions in the lungs. The excipient is typically a little bit larger, 60 to 200 microns. This is so that it doesn't actually get into the lungs of the patients. Excipients are added for the purpose of breaking agglomerates apart, as well as so for breaking the agglomerates apart, as well as bulking up your powder, so that it makes it easier to deliver an exact dose, to weigh out these doses and deliver them with accuracy. So this slide kind of shows what we're trying to achieve with the dry powder inhalers. We have percent deposition. So this is how much of the drug is actually going to be deposited within the body. And we have aerodynamic diameter. For large particles, say greater than 10 micron, what happens is when you breathe these in, the air carries them into your mouth, and they actually hit the back of your throat, and they stay there. They stay in the mouth area, they stay in the throat area. They don't actually make it to the lungs. So if you're trying to target some, throat pain, this is really an important factor. You'd want to create these particles so that they're bigger, so they don't go deeper into your body. For medium-sized particles, which I'm calling 1 to 10 micron right now, these tend to deposit in the upper airways. So you breathe them in, They don't hit the back of your throat, and then they kind of get deposited in the upper airways. This is really important if you're trying to target the bronchial tubes. So for example, if you have bronchitis or you have some type of asthma, you're really looking to target this area. You don't want to go deeper into your lungs because it's not relevant there. Now for lung deposition, so this is for deep lung deposition, we're looking at particles that are sized between 0.5 and 2 micron. And what happens is they'll get carried in by the air. They'll get deep inside the lungs. They'll land on the surface of your lungs. And then through diffusion, what's going to happen is they'll enter your bloodstream. So if you're trying to get a drug to go inside of the patient's bloodstream, you're really aiming to get the particle size between this region. Now, what's interesting is you would think that perhaps going smaller would be able to get these particles deeper in your lungs, and that's not necessarily the case. There is a range where if you're too small, essentially what happens is you're just going to breathe these particles out. You breathe them in, they remain in the air, and you exhale them right out. So it's crucial to be able to control the size of your particles with these devices and be able to monitor these sizes. Let's take a look at some data from our spray tech. So what we have here, we have two formulations. Both of these were measured on the spray tech, and both of these were used on the exact same device. So there's no difference between the two devices. We have formulation A and we have formulation B. Formulation A is a mixture between lactose and some API. Formulation B is the very similar mixture, except the API has been milled. So it's been really grinded down. So it's a very fine powder. And what we can see is we have our time of actuation. So this is a size history chart. We have time over here, and we can monitor the changes in our DV50 over time. We can see that for formulation A, roughly a very equal particle size, very little change in the particle size. While for formulation B, we seem to deliver a very small powder first, or small particle first. It shoots up, and then it goes back down to a very small particle. And so what's happening here is we're actually delivering this API deep within the lungs because it's been very, very finely milled. So the particle size at the start tends to be very small, and that's just mainly our API. And then we get more of our excipient over here. And finally, it's more of our API once again. Let's take a look at this. So this is kind of interesting. So what we have here is we have our particle size distribution, and we have varying pressures on the dry powder inhaler. And we want to see how this affects essentially our particle size. So if we take a look at the 30 liter per minute, so these are those circles, so we can see we have very large particles in this region. We have some smaller particles over here. As we increase the pressure, we can see that we are actually reducing the size of these agglomerates. And eventually, once we get to our 90 liters per minute, sorry, 30 liters per minute is kind of what a normal human will breathe in. Once we get to 90 liters, we can see that very little of these agglomerates exists, and that's likely that is due to the increase in pressure. It's the pressure that itself is breaking these apart. However, we can also add various different excipients in order to reduce the formation of agglomerates. I mentioned that previously. So here we can see, here we have added our lactose as an excipient to our API. And we can see that we have actually broken up the formation of these very large particles. So that kind of shows the power of these excipients. The excipients can prevent your API from agglomerating with itself. There are some ways you can do that through chemistry. So you can modify the surface chemistry of your API so it prevents the formation of agglomerates. And we're seeing a lot of work in that area, but definitely excipients have proven to be quite useful in this field. So I'll just very briefly talk a little bit about nebulizers. So essentially all a nebulizer is you'll have this device and you'll add your drug into it. It's usually dissolved in some aqueous solution. And through liquid shearing, it's going to produce these droplets. Typically, the droplets are very fine droplets, and they're advertised to have a very consistent rate. If we take a look at some data for a nebulizer, first off, we're looking at 400 seconds here. So if I went back a few slides, over here, we're looking at, 500 milliseconds. So it's a completely different scale. So yeah, 400 seconds. And we can see that the particle size is relatively stable. We look at the DB10, which is this bottom line over here, very stable. If we take a look at our DB50, very little fluctuation as well. And our DV90 definitely has a little bit more fluctuation. This fluctuation typically doesn't really affect the patient too much. Usually it's because some of these particles are condensing in the air and they form these larger particles, but usually that doesn't really matter for a patient. What we're looking for in nebulizers is that at least 50% of the vapor is respirable. So at least 50% of the vapor can get into your lung. So if we take a look at our DV50, we can see that this is below our 5 micron size. So we typically would consider this very respirable. This is the output of a breath actuated nebulizer. If we take a look over here, we can see that our transmission, it should start at around 100%. It immediately, as soon as we detect a drop in transmission, our spray tech is going to start recording the data essentially. This is kind of relative concentration, you could say, of our nebulizer. And once again, this is a very stable system, very stable device. We have very consistent particle size throughout the entirety of this breath actuated nebulizer. We have a few larger particles here at the beginning as well. This is likely caused by some buildup at the device nozzle itself. And usually this doesn't really affect the patient very much at all. So let's talk a little bit about personal care and domestic sprays. So what we have here is a size chart for a medium hold hairspray. Typically, hairsprays will produce particles between 30 and 60 micron in diameter. Larger droplets, larger particles lead to larger droplets. They have longer drying time. You'll tend to notice this beading occurring in your hair, and they're often linked to higher firm holds. Finer droplets, they'll dry faster, they'll have less tackiness, but they'll have a reduced hold overall. This is a very typical size history chart for a hairspray. At the start, we see these large droplets, and you can always make sense of that if you've ever used nasal sprays or hairsprays. At the very start, you tend to find these large droplets, and that's usually because of some buildup in the nozzle. If we take a look at various hairsprays, so we have this natural hold, which is kind of like the weakest of the hairsprays. We take a look at this firm hold, as well as this extra hold. We see that the natural hold is going to have the smallest particles, and as we go to our stronger hold, extra firm hold, we're going to get an increase in our particle size. So this takes me to the last couple slides, and here kind of ties in the title of my talk. So if you're looking at these personal products, what % of these particles are actually respirable? So it's going to depend on different types of products that we're using. If we look over here on the y-axis, we have essentially a % of respirable particles. On the x-axis, we're going to have two types of sprays. We're going to have a propellant-based spray and a pump spray. And then we're going to have various types of products. So what we can see here is that these products are actually delivering particles that we can breathe into our lungs. So if you're using dry shampoo, for example, they found that on average, we're looking at around 23.5% of these particles can actually go into your lungs. Hairsprays and sunscreens, a little bit less, but still concerning. Sunscreens have, they don't have chemicals that you want necessarily in deep parts of your lung. So this has become a concern for the regulatory environment. And we can see that it's not necessarily based on the type of product it has. It's much more complicated than that. It'll vary by spray system, by the product type, by the galenic form. So whether it's an emulsion, a liqueur, an oil, a powder, as well as the nozzle design. And even very similar products are going to have differences in their particle size due to the differences in the formulations and the nozzles. So this is kind of raised concern for the FDA. They are now looking at potentially introducing these kind of requirements to label products that have very fine particles as, problematic. So they're going to introduce this kind of labeling system on a lot of these products, sunscreens, personal care, in order to kind of start encouraging these companies to design these systems so that these very small products don't go deep inside of our lungs. And with that, I believe this was my last slide. So I believe we have a Q&A session here next.
Thank you so much again, guys. Appreciate it. We'll kind of open it up for questions, both for Raghi and Daniel as well. Any questions to start off with on either kind of the data sizer, nanoparticle tracking, or spray tech, and kind of laser diffraction, general particle sizing? Yeah, go ahead, please.
I have a question about measurement with this spray.
Yeah.
So what do you measure if you turn on the device with no sound? You have, let's say, air or light?
You're essentially just measuring air. That's what's going to be our background. So you're going to remove that.
But you get a part of it. You
get some distribution. That could be particles in the air, some moisture, but really it's just background.
So then let's say you measure a aerosol where the particle is very small, the number density is very low, right? You can remove that from the back. It comes from this.
Yes, we removed the background prior to.
Now, I have another question. So, you said that, it doesn't require calibration, right? But now verify.
Yeah.
Verify using that.
Yes.
So can we do that in the lab? Like, I've seen it like also, but not. Only-
If you have to, it's necessary. So the way that they do this operation is they actually attach themselves to the machine. They can monitor, this is something.
Yeah.
That's where we have. So if you see the necessary, which you don't want to do, if they don't want to be able to look, you got not only measure spray and aerosol, but want that. No problem. So otherwise, you're like, all one of us. But it's only accessible. It's
I saw them, the verification, into suspension water.
Yeah.
Is it possible to do it with a gas verifier, not in water?
I would say it's possible. We don't do that. I don't think. I wouldn't say it's impossible or difficult. I'd say it's more challenging. Sprays tend to be a little bit more complicated than say just the energy, but it could certainly be possible. The problem with that is if you're thinking about a spray, usually you're looking at the droplet size. Controlling the droplet size is a little bit tricky. I lots of so more challenging.
I saw that, for example, there are some papers nature particle size distribution in sunscreen and stuff like that.
Yeah.
Can you talk a little bit about the experimental stuff? How is that measured? Like,
We're talking about
particles are
aerosol.
Oh, yeah.
Yeah, so we're talking about sunscreens like aerosol sunscreens have gotten in a lot of trouble in the past because they put in some chemicals, a lot of density. And so there's been a little bit more focus on studying those particle sizes. Because of that, that's what I was trying to allude to. You don't want that to be inside of it. That's a bad thing. So, but yeah, it's spray. It's always spray. Yeah, if you're trying to measure the particle size of say some type of wavelengths, the spray type is probably not going to be your first choice. I would say we'd have to look a little bit into that, but one of the purpose would be what would be the purpose? So if you're trying to mimic the real life wavelengths, then dissolving or diluting this in say suspension might not make a lot of sense because that's never how it's practice. So yeah, we'd have to kind of come up with any sorts of ideas, but more than likely it'd be through automated image analysis, I guess.
Okay.
Yeah. No problem.
Other questions?
I've got one for, about tracking of the, NFR tracking analysis. You showed, a screen there. Your applications, the black screen of all those farmers. Scattered. What's the time scale to scan, how rapid is that?
Yeah, so it's all on over seconds, like, we could say, so the idea is that we're using what is called a variable frame rate. So if your particles are scattered like really efficiently, the exposure time is reduced, the capture time is reduced. And so the amount of time it takes to get to something like 1,500 frames, would only be like 20-something seconds. If your particles are dimmer, then the exposure time is increased, which causes a longer capture time. And so you might have more like 60 seconds or so to capture 1,500 frames. It's the idea of like targeting a number of frames to get, the appropriate analysis.
Yes.
And, the movements of particle movement from one frame to the other, you can imagine that it's all fractions of a second. The frame rate, can vary from between 20 and 65 frames per second to capture the mean square displacement of those particles on that frame by frame basis.
I want to ask, thank you for the really nice. I want to ask about the other. Yeah, I'm you. I'm about to. So, from here, if you feel like you need back to the. NCA, that your new strains. Now, you have, issues with they have some ions surrounding particle. Right, that's nice. So intensity without seeing that time.
Yes, to a degree. So what happens when, and you can just do this by simply analyzing a, let's say, 400 nanometer standard, like the latex standard. If you were to dilute that in water, then you would find that it would actually get undersized. Because in water, it doesn't have, the stable ions around it. I've seen the data myself. I've actually analyzed it. I take a 400 nanometer standard, I might get around 350, 360. But if in our literature, we've got a technical note where we highlight what NIST requires. So let's say if you were looking at latex standard, they'll require that you suspend those standards. They'll come in stock solution, and that usually is too concentrated for nanosite analysis. It's the analysis. You'll need to dilute it. And this has a protocol where they'll say, take potassium chloride. Filter through 0.0, 10 millimolar, filter through 0.01 micron filter, and then use that to dilute down your standard. Depending on the size of the standard, they'll say you should dilute by a certain factor, like a certain fold dilution, and then that will get you proper size analysis. You'll find out a 100 nanometer standard. Now with the electrical double layer accounted for with the salt concentration, will actually be right at 400 nanometers. So the effects of what's around your sample can affect the Brownian motion, can affect how fast those particles move around. So that's,
I'm a super things for that. I mean, what then you have to
so
I'm sorry, can you repeat the question?
yeah, so the question is, what's, why choose NTA versus DLS or DLS versus NTA, just to put it simply. So it's not that, that there's a metaphor of an elephant in a room and people, seeing the trunk and seeing the tail and thinking that you got a rope or a tree, just depends on the perspective of what you're looking for. And so the two techniques are very comprehensive, together. they complement each other very well. People who often have a nanosite system have a synthesizer and vice versa. So DLS will give you a wide size range, 0.3 nanometers to about 10, 15, 20 microns in diameter. 3-to-1 peak-to-peak ratio typically for that full range. So it's a lower resolution technique, but a wider size range. And it also does, the DLS system will often come with ELS, engaging zeta potential. So that's just, why one person might pick a DLS system. You get a wider size range, can handle, a wide, range of particles. NTA, it's a little bit more known for a higher resolution, but a tighter size range and concentration. So it's not just the sizing, but it's also what other measures come with the system. So DLS comes with zeta potential as well. NTA comes with concentration as well. So NTA is a higher resolution. It will give you the ability to gate within a certain population. You can say what percentage of my particles are within a certain range, and gives you concentration, particles per mil on a number-based distribution. And fluorescence. So it's the comprehensive metrics that are within each system that allows people to dictate one or the other. If you were simply looking at the size of, let's say, 120, 200 nanometers, you might be well served by both. If you're looking at a population that's within the analytical range of both systems, and you didn't necessarily need with the highest resolution, or for analysis, you can be served by both.
Those finally, what's the I went up so right? So
Oh, that's the Howard. That's just fundamentally how the techniques work. We're looking at Brownian motion in solution. That they do require samples per heat in solution. Because what we're doing is we're looking at Brownian motion as defined is the bombardment of solid molecules against the particle itself, causing this random movement in solution. If you're looking at a powder form, then yeah, you're talking about other techniques such as laser diffraction, the arrow disperser, or morphology based, like you look at shapes and size of the particles from dry powders. The analytical range for measuring smaller particles is better suited in a solution form. You have to think about, okay, how small can I actually analyze something that's still in a dry powder? The technique gets a little shaky. You can start playing around with like TEM, SEM, you can look at that. But while those techniques are very prevalent with all their benefits, they are not as quantitative about their size distribution. During my postdoc, I used to use SEM, TEM. Now we use sometimes image chain analysis to be able to get some sense of size distribution. But if you want more quantitative analysis of particles on a smaller range, then you're going to put them in solution and watch their Brownian motion and use that to determine their size.
there's a question of the
Thank you for the talk. Could you comment on the difference in light scattering between a neutral particle and a
Neutral particle and charged particles. Yeah, so it depends on the nature of the particle. If you're if we're talking about, analyzing their charges, right? We're talking about zeta potential. And so when we talk about zeta potential, there's two main mechanisms for a sample to be stable. One is electrostatic stabilization, and the other is steric stabilization. So if you're talking about something that's charged, then we might be looking at more electrostatic stabilization. How that particle will respond to an applied electric field based on the charges in the slipping plane around that particle. However, there is also steric stabilization. Steric stabilization would mean that you might have those charges are shielded, maybe resulting in a little bit more of a neutral charge. But doesn't necessarily mean the sample is colloidally unstable. It might be stable. A lot of people, let's say, will pegulate a particle for better trafficking in certain aqueous environments. And in that pegulation, you'll find that the charges are shielded. So zeta potential might actually result in a more neutral value or closer to 0 millivolt value. So if you find that, then you know, that's where size and zeta potential comprehensively give you a bigger picture of what's going on. Because if you have a neutral charge, but you subject the you know, sterically stabilized sample to different charges, then you would you know, if you subject it to different concentrations of salt, they still might stay the same size because they're sterically stable. Does that make sense at all? And then, you know, if you're not looking at something that's sterically stable, something that truly is neutral, then you might actually find that it's crashing out. It's might be unstable if it's not sterically stabilized. Does that answer your question? If not, you can come talk to me afterwards.
All right, thank you, guys. I think we'll move on. I mean, there obviously you both are here
Yep.
today and tomorrow, and there'll be a chance to kind of interact and talk with them as well. So thank you again. Thank you. So we'll move on from kind of particle sizing to rheology, and then also kind of particle grinding and milling as well with NET. So kind of it's a pleasure to kind of introduce Phil Rolfe, who's been kind of involved in rheology for a very long time, and I know him personally for a long time as well. So again, Phil, thank you so much for coming, and kind of looking forward for you to taking us through the world of rheology.
Thank you. Samuel gave me a very tough job, which is to give you an introduction to the fundamentals of rheology and also applications of rheology in food and pharmaceuticals in 40 minutes. So I'll do my best to do that. So rheology, I think some of you are experts at this. I'm going to give you a very high-level introductions for the people that really aren't experts, people that haven't heard much about rheology. So rheology is defined as the science of deformation and flow behavior. And so I'm going to talk about these separately. First of all, flow behavior. So you could be talking about viscosity of a sample, maybe a paint. How is it going to be pumped? How does it flow? How does something flow into a mold? How does it flow when you eat it, if it's a food, and that sort of thing. So there's lots of different situations that you can imagine that we might want to measure flow properties. Obviously, there's the processability of it. There's the end use, as in with food, you know, or spreads and things like that. How does it taste? How does it feel in your mouth? How does it behave when I try to spread it out? And there's also the formulation side, which relates to all of this. Now, we're going to be using a few shear terms, and one of the common ones is shear rate. So this would be how fast something is flowing, but in a dimensionless way. So for instance, there's something you may have done this morning is spread some butter on some bread or toast, and you put some butter on the bread there, and then you move the knife across it. And if you wanted to calculate a shear rate for this process, then you could say, well, how fast is the knife moving? Let's say it's moving 3 centimeters per second, and the layer of butter is about 1/4 millimeter, then the shear rate is actually the lateral speed divided by the gap between the two surfaces. We'd say 30 divided by 0.25. And so that gives you a shear rate of 120 reciprocal seconds. So you can calculate shear rates quite easily for many different processes. And on a rheometer, you can replicate those. So we can actually do simulations of real processes on a rheometer. And you may have heard of viscometers. They are kind of fairly narrow range. You may have 3 orders of magnitude of shear rate that you can cover. So you can usually look at pouring, mixing, and maybe slow pumping, but not really anything too slow. You can't really see leveling or sedimentation. If something's sedimenting, it's going to be a pretty slow process usually. If you're looking at higher speeds like high-speed pumping or spraying or roller coating, things like that, then you're going to get to incredibly high shear rates. And so this is when you'd really want to be looking with a rheometer, because you can get the whole shear rate range with a rheometer. Okay, so there's 2 different rheometers that commonly people use. There's a rotational rheometer, and these are stronger at measuring the lower shears up to moderately high shear. But you can get to about 10 to the 5, so 100,000 reciprocal seconds with a rotational, but the data is getting a little bit unreproducible as you get up to these very high shears. Its real strength is in the lower shear ends. And then if you want to go to ultra high shears, you really want to go to a capillary, because the sample can't go anywhere except through the die, and you're going to squeeze it through a die very fast. And so you can get up to over 10 million reciprocal seconds with a capillary. So looking at a rotational, what do we have? We've got this motor system at the top, and it has an air bearing so that you've got very low friction. And we can apply a torque onto the sample. This is going to rotate. We're going to put the sample on this lower plate, which is temperature controlled. And then we're going to clamp it between two surfaces. We're going to rotate the upper surface. And then we're going to measure the resistance to flow. So for a known torque, what rotational speed do you get if you want to measuring stress control? Or you can actually have a closed loop system where you control the speed and measure what stress was required. And obviously these switch out, the lower plates switch out, and also the whole temperature controller switches out. So if you want to measure in a cup, you can do that with a Peltier cylinder. We can use Peltier plate. This is usually up to about 200 degrees C. We have a hooded plate. This heats from the top and the bottom. And then a high temperature cell. This is with forced gas, and this will go up to 450 degrees C. So you can measure polymer melts and things like that. So pretty modular, and you obviously buy whatever you need, and you can extend the system year on year if you need to do new projects. So we have different geometries for different types of sample as well. So if you have a very, very low viscosity material, you may want to use a cup and bob. So if you're measuring water or milk, then this is a very good way of measuring a lot of surface area. Obviously, the more sample you measure, the more resistance to flow that you're going to see. So if I wanted to measure the resistance of air, the viscosity of air, I'd be better off using a sail than I would a small cup and bob or something like this. So the larger the geometry, the lower the viscosity you can measure. And we do have some pretty big cones and plates, and the instruments are pretty sensitive nowadays. So you can actually measure water and milk with cone and plate or parallel plate as well. But historically, anyway, we used to have to use concentric cylinders. The downside of these is you've got a large volume of sample. As you go to cones or plates, you can use a very small volume of sample. So we could be testing 40 microliters of material if you're looking at injectable drugs and things like that. Now, if you're looking at stiffer materials, then you really could use small volume anyway between parallel plates. Maybe you're going to look at a gum or even a solid strip. Maybe this is a composite or piece of glass or something like that. You can just clamp it top and bottom, and we can do oscillation testing, look at the torsional stiffness of it. So on the same instrument, you could be measuring water or solvents on one end and measuring solids on the other end. And using, just depending on which geometry you use, you can pretty much test anything in between. So looking at the shear terms again, we've got shear stress. This is the force per unit area. So if we know the surface area of our upper plate or cone, and we know the force that we're rotating on it, looking at any one cube of the sample, we can calculate the force per unit area. And so the SI units are known as pascals, which is 1 Newton per square meter. Obviously, we're doing this torsionally rather than just a lateral flow. And so we'd calculate that, but we still get the units of pascals. Now, strain is deformation divided by the gap or the height of the sample. So if the sample moves 0.2 millimeters and the gap's 1 millimeter, we say we applied 20% strain to the sample, or 0.2 strains. And this has got the symbol gamma. And obviously this is dimensionless. So it's 0.2 millimeters divided by 1 millimeter. So we get 0.2 strain or 20% strain. Now, if you have a liquid, obviously, instead of it just moving and stopping, it's going to keep on flowing when I apply a stress. And so we can calculate this shear strain rate or shear rate. So this is gamma dot. So the deformation divided by the gap, that's obviously the strain. And then over the time taken, that gives you the shear strain rate. And that was dimensionless divided by seconds. Obviously, you get reciprocal seconds. So if it's a liquid, you'd expect it to keep on flowing. If it's a solid, maybe it will just deform and then stop. So looking at our capillary rheometer, this is where we're squeezing a sample through a die. So we've got this crosshead here at the top, which is going to push down on these two pistons. I'm going to put samples in 2 barrels. And at the bottom, we've got the dies. And the sample is going to get squeezed out through the die. So we can control directly the shear rate as the sample gets squeezed through the die. And then we have pressure transducers on either side. So they actually are looking at the sample, the pressure just above the die, to see what force it could take to get it through that die. Now, some people historically would measure the pressure on the crosshead, but then you have to deduct all the friction of the piston in the barrel. So it's a bit messy that way. But looking at the pressure to get the sample through the die gives you a lot more accurate results. And actually almost looking at first principles, right? What's the force right above the die entrance, and the controlled rate is controlled by the piston here. So this gives you the ability to use a very small die, and pretty high shear rates can be attained. So we can get up to over 10 million reciprocal seconds. So if you really want to look at spraying or roller coating or high-speed slot coating, things like that, then these are much easier with the capillary rheometer. So this is the sample flowing through a capillary die. Obviously, this would be vertically mounted on the rheometer. But if you've got Poiseuillean flow and it's a Newtonian material, then you expect a parabolic flow profile on the front here. And we can calculate the shear rate. So the approximate shear rate, or the apparent shear rate, is 4 times the volumetric flow rate over pi times the radius of that die orifice cubed. But usually materials aren't Newtonian, right? They're slightly shear thinning. And so we have to do a correction on it. This is called the Rabinowitz correction. And if we know the shear thinning factor, that's when we've got a viscosity versus shear rate curve. You can see the gradient here. Then the n value can be made to correct the shear rate. And so with a shear thinning sample, actually, where the material is getting higher shear, it would get a lot higher shear, and you have a flatter front of flow here, and then a more on the edges. And so this is the Rabinowitz correction, gives you corrected shear rate. So that's something you can switch on or off in our software. And if you switch it on, you just want to be consistent. If you switch it off, that's fine. You're going to get relative results, and they won't be exactly quite as accurate. But don't mix up your results, some with your corrections on and some with them off, because you're going to get quite different data. So I'm saying that if you turn all these corrections on, there are different corrections that you can switch on. If you turn them on, actually they do correlate really well between the instruments. So you could actually have a curve here with the rotational rheometer, and then the capillary just carry it right on up to the high shears. So we're measuring SI units, we're measuring absolute viscosity. And so you really can compare and model these things. Now, sometimes materials don't behave the way you expect. They start to slip. And so if you, let's say you rotate this upper plate, you'd expect a laminar flow field, like a pack of cards, but often you don't get it. You get some slip on the top and the bottom plate, and the bulk of the sample doesn't really want to flow. And so the common thing for slip is suspensions such as tomato ketchup. But you can see at any time really where you have things that phase separate under stress, like ice will melt. Obviously, when you put an ice skate on it and you stand on it, you've got a thin layer of water there and you're sliding along the top of the water. Phase separation happens, obviously, if you have a concentrated suspension and you apply a stress to it, it's easier to phase separate than it is to make that bulk of the material flow. And so we got water coming out of the tomato paste. And so it forms a slip layer on the measuring surface. And so that just slides along. Now notice this is only going to happen when you have some yield stress. If the material doesn't want to flow, then it's likely to slip. If it doesn't have a resistance to flow from the bulk, then you're going to get laminar flow all the time. So there's some a nice video or two here that I got from my colleague. This is glycerol solution flowing through a tube, and you can see that parabolic flow profile behaving itself, and it's doing what we hope. This, on the other hand, is carbapol gel. You can see it just flowing as one slippy lump, right, through the center of the tube. And you can see a few particles stuck to the wall, but pretty much you've just got one whole thing. This is called wall slip behavior. And this was actually just measured with a syringe pump pushing a sample through a tube here. So that's very difficult to measure when you've got complete slip. But we can ameliorate the situation by using roughened measuring systems, and they will grip the sample. And if you know that there's a certain volume of material phase separating, maybe you know that there's going to be a 10 micron layer of water coming out of your tomato ketchup. If you have more than a 10 micron profile of roughness on your plate, then you can accommodate that water separation. And now we're going to get good, good flow of the bulk material. You can also use a vein in a cup. So this way, obviously, the sample is going to be trapped in the vein and going to grip pretty well. And if you have a much bigger cup than a vein, then you're going to disperse that stress over the whole surface pretty well. So this would be on a viscosity curve, how you know you're getting slip. You get this weird looking dogleg characteristic. And this is really where it's slipping. You can see the viscosity is lower than it ought to be. And then it's starting to get higher and then lower again. This is weird. You would never expect a viscosity flow curve to look this shape. And so if I see that, I would say, oh, let's use a serrated plate and see if it goes away. And then we can see it did. So obviously we had slip. And so what you normally do is you use rougher and rougher measuring systems until you get a constant shape of a flow curve, and then you know you've eliminated the slip layer. Okay, so some materials don't initially appear to flow. So if you think of frosting on a cake, obviously you can make it flow, but it doesn't flow initially. And that's quite nice because you want to see that surface profile of your frosting maybe. And this is called the yield stress. So the yield stress is a stress required to start the material flowing. Maybe a bulk structure in there, maybe a gel or something like that. And it won't flow at all until you reach the yield stress. So as I apply increasing stress, no shear rate occurs until I get to the yield point. And then it may go up linearly if it's a Bingham liquid or exponentially, what's this kind of exponential decay with Herschel-Bulkley fluid. And you can model materials. Historically, what people used to do was take a few different measurements at different shear rates and then extrapolate to 0 shear rate and say that's the yield stress. But often it doesn't really work like that. This is actually much more of a curve. And so we can actually control by increasing the stress and see when it starts to flow. So yield stress is a very useful term because you can see how easy is it to make the material start flowing. Like, how is it going to be for pumping this material? Is it going to resist sagging or sedimentation? Is it going to therefore give you a good shelf life if it resists sedimentation? How thick does it feel? If you're thinking of a mouthfeel, how creamy is this yogurt? How nice is this frosting? Things like that. That's basically all related to the yield stress of the material. So this is mud being pumped down in a drilling situation. Obviously, you've got to put cement in there. You've got to put mud in there. This is for fracturing. You might want to pump a fracturing fluid in and hold the thing open so that the oil can come out for fracking and things like that. So in a rheometer, on a stress controlled rheometer, you can actually ramp up the stress with time in a linear way. And we will look at the viscosity with time. and you can see whether the material's yielded or not. So initially, you're going to push on the material and it pushes back. It doesn't move. And you get an instant viscosity. It doesn't look very high. You push harder, it pushes back harder. It looks like it's getting stiffer. This is because we're not really waiting for equilibrium. So this is just elastic stretching behavior. Then you push hard enough and the material starts to flow and the viscosity actually starts to break down. And so the yield point is actually the peak on this curve. So if you plot viscosity versus shear stress, you can actually just see, okay, that's the yield stress. So it's a very quick test, maybe 30 seconds or a minute long. You can see the viscosity is the yield stress in the material. Here's a couple of results for inks. So this is a paste ink, and this was a lower viscosity ink. Obviously, we can't see yield stress. If there is one, it was off the bottom of this curve. Now, some people would say yield stress isn't that easy. You're just looking at the startup yield stress, static yield stress. So from moving from stationary to flowing, that's the static yield stress. Now, there's also something called dynamic yield stress. So if your material takes a certain stress to start up, and then it comes down and it takes the same stress to stop, then the material is not at all thixotropic. And so it would have the same static and dynamic yield stresses. But some materials are thixotropic, and it takes quite a lot of stress to start them flowing. But after they've been moving, they flow a lot easier, and they have a sort of residual stress when they stop moving, if you like. So that's the dynamic yield stress, the stress just required on a down ramp to stop it flowing once it's already started. So it's good to think about what actually do I need to see for this process? Do I need to measure the startup yield stress? Do I need to measure the dynamic yield stress for when the material is stopping to from flowing? And obviously, the dynamic and static yield stresses that I just showed here are different when the material is thixotropic. What's thixotropic mean? Well, basically, this is shear-dependent rheology. So if the material is shear thinning, it could be just shear thinning, rebuild immediately, like hair gel. You know, you can rub it on your hair and then it rebuilds structure immediately. It needs to because it's got to hold your hair in place. But if it's like paint or something like that, then when you get it out of the shed, it looks like a big jelly. You take the lid off or you shake it up and you stir it. And then it becomes like a liquid for a few hours. If you put it back in the shed and take it out a week later, it'll become a jelly again. And so there's this rebuild time for it to recover its structure. So that's thixotropy. And so you can see here, if a sample was mixed up and then rested for 10 minutes, you can see it's got a fairly low yield stress. 2 hours, obviously it's got an appreciable yield stress. 2 days, a much bigger yield stress, because this is building up structure at rest over time. So these things are good to remember, good to recognize if you want reproducible results. You can think, when would I get thixotropy? It's usually when you get flocculation, things have to reagglomerate, or maybe when you've got hydrogen bonding, things have to get back to their original conformation. Different particle packing effects or polymer solvent effects can give you thixotropic behavior. But if you really appreciate you've got a thixotropic material, that will help you get reproducible data. So I could test a sample, and if I mix it up very well and then test it, I'm going to get a lower result than if somebody else doesn't mix it, right? So obviously I need to make sure that we do the same thing to it to get the same shear history to get the same results. So on a rheometer, you might say, okay, I'm loading it the normal way, and I'm going to apply a shear for 20 seconds. Then I'm going to give it 2 minutes of rest, and then I'm going to make my test. And that way, at least we'll have eliminated any shear history from when somebody loaded it or mixed it well or didn't mix it well. So that will practically help you get more reproducible results. Obviously, you'll have eliminated any long-term structure that doesn't rebuild in a couple of minutes. Okay, so that's viscosity from flow behavior and yield stress. Now, there's also the deformation aspect, the science of deformation and flow. So what if you just deform a material and don't really break it down? This is done by oscillation testing or creep or relaxation testing. But I'm going to touch on oscillation because this is the most common one. So instead of just shearing your sample around and around, we're just going to oscillate the top plate left and right, very small amount. Now, this is such a small movement, actually, you wouldn't be able to see it. Usually, it's in the order of microns of movement on the upper plate. So we're using a very, very small oscillation on the upper geometry, and we're just probing the structure without destroying it. So we have a stress wave, and we have the movement here. We call that the strain wave. And so if we have to apply a very large stress and we get a very small amount of movement, we can obviously deduct it's a pretty stiff sample, right? If I have to apply a large stress, I don't get much movement. And so the stress amplitude over the strain amplitude, that gives me my modulus. We call it G star, complex shear modulus, because it's done in an oscillation test. We take out the inertia and things like that. But basically, it's our modulus, how stiff the material is. There's also another thing you can see, and that's from the lag between the stress and the strain. And that's from the phase angle. So the phase angle is the absolute lag where a complete wave is 360 degrees. We can say how much lag did I get from my input stress to the measured strain. So if your sample is completely in phase, then it's elastic, right? So if I apply a stress and the material moves, and then when I take off the stress, it comes right back, then obviously the stress and strain are in phase, and it's a purely elastic material. But if it's a viscous material, I apply a stress and it accelerates, and I take off the stress and it stops. And my strain is a maximum, my stress is 0. And then when I apply a stress the other way, it accelerates. And then when I take off the stress, so you get a phase angle of 90 degrees for a viscous liquid, a phase angle of 0 for an elastic solid. And so you can see from the phase angle how elastically natured a sample is, or how viscously natured a sample is. So we've got two parameters here. We can see the actual modulus of it, and we can see how viscously or elastically natured the material is. So mathematically, this is how it looks. You've got stress amplitude over strain amplitude. You've got stress over strain amplitude multiplied by the cosine of the phase angle for the elastic component, or by the sine of the phase angle for the viscous component. So if the phase angle is 0, right, 0 degrees, they're completely in phase, the stress and strain. Cosine of 0 is 1, so the elastic modulus is a maximum, and sine of 0 is actually 0, so there's no viscous component if they're completely in phase. If the phase angle is 90 degrees, showing they're viscous, cosine of 90 is 0, and so this would be 0, and sine of 90 is 1, and so this is a maximum. Now you can also get this G star value divided by the frequency, and that gives you your complex shear viscosity from an oscillation test. So similarly to doing a rotational test, you can get viscosity. If you do oscillation, you can measure the complex viscosity that way. And if they match, this is something called the Cox-Merz rule. You can actually do oscillation instead of doing shear. Now this happens for most samples where there's no agglomeration and things like that. So if you're looking at a polymer melt or something like that, you can actually do an oscillation test instead of steady shear and get exactly the same data. You just oscillate at different frequencies. And that's quite good because the sample doesn't come out of between the geometries, whereas it would do if you're doing steady shear with the polymer. So we've got these two numbers, G prime, our elastic component, and G double prime, our viscous component. And what we can basically say is that if the sample is more elastic than viscous, then it's going to behave like a solid. Therefore, it's not going to suffer from sedimentation stability. It's not going to phase separate. You can do this with any liquid, right? I mean, any any material that flows. We generally think of them as liquids, but they might actually not be a liquid. There's a material that you may have heard of, this vodka that people have put gold flake in, and I think it's called Goldschlag or something like this. Yeah. Anyway, this is gold particles and they're suspended, and it looks quite, fancy in the jar. But they don't sediment. But as soon as you pour it into a glass or drink it, it behaves just like obviously a normal drink. But when they calculated this, they said, well, if we have all the gold at the bottom, it doesn't look very fancy. We want it dispersed throughout the whole material. And so we're going to add a weak gel in there to suspend these gold particles. And so actually, when you do an oscillation test on it, you'll see that this is slightly more elastic than viscously natured. And so it's only a weak gel, but it's enough to keep all the particles suspended. The name, same for Tropicana, actually. Tropicana realized that if all of the pulp in their orange juice settles to the bottom, it doesn't look so fancy. You just have a clear orangey liquid with lots of murky stuff at the bottom. It doesn't look very nice. But if you can keep that pulp suspended, then it looks a lot more appetizing, and it's also got some flavor and taste to it, thickness. And so they add a thickener to these different juices to make them stay suspended. So we call it a vanishing yield stress, but it is actually solid-like behavior at rest. So you might say, well, how about honey, and yogurt? So yogurt is actually an elastic solid. When you apply a stress to it, it will drop in lumps. It will break off cleanly. Whereas honey is a liquid, it flows and it continues to flow. You try to dispense this and it's messy, it keeps stringing. This is easy to dispense because it breaks cleanly. When you open a container, you can actually see the ripples on the top of the yogurt from the last time somebody opened it. Whereas on the honey, it's going to have leveled out very smoothly. So you can see just by opening a container if something is actually a liquid or a solid over long time scales. So on the rheometer, what do? We first of all do an oscillation test with things called an amplitude sweep. So we're oscillating at larger and larger amplitudes. And initially, the material doesn't break. And so we're just looking, this is our elastic modulus in red, the viscous in blue. And you can see the material is fully structured. Maybe it's even recovering a bit from when I loaded it. So it's slight rebuild there. But it's not breaking down until a certain strain gets reached, and then the material starts to break down. You can see the modulus dropping, the elastic, the viscous may be going up as some of the elastic structure becomes viscous, and the phase angle, the wave lag between them, goes up as well. And so this is our linear viscoelastic region. This shows us that you can oscillate this material so far without any breakage to it. If I go too far, obviously it breaks the material, but as long as I only keep it within this distance of movement, it won't break down. And so I can do an oscillation and know that I'm not destroying any of the structure. I could watch curing happen and know that I'm not retarding a cure process. I could watch something rebuild after shearing and see how long it takes to recover from its shear process and things like that. So another thing you can do in oscillation is a frequency sweep. So in this case, we're sticking with an amplitude, which is inside our linear region. Usually, let's say this is the amount that we can move the sample and know it won't break. And I can either do that slowly or I can do it very fast. And then we can see how the viscoelastic behavior behaves within the linear viscoelastic region. So I'm not destroying the structure, but I want to see if it's elastic at high frequencies and low, or only at high and not at low, or only at low and not at high. So this is actually something that's elastic at high frequencies. You can see that G prime is higher than G double prime, so it's acting solid-like, and but liquid-like at low frequencies. So this is actually a silly putty. It's quite a rare thing that you see this, but you can roll up silly putty and you can bounce it, right? And so we can see that very high impact time, it's going to act like a solid and bounce. If you leave it on the floor or a while on a bench, it's just going to flow out and become a puddle. And you can see it behaves like a liquid over longer timescales. And actually, you could get the molecular weight from the crossover frequency and the molecular weight distribution from the modulus at the crossover. So you can do this with polymer melts and see quite a lot about their structure just from the rheology of it. So rheology is quite useful. It shows you the processability, the pumping time, that you know how it's going to mix, spray. You can also see if something's going to be storage stable, if it's going to sediment or not, the rebuild time after you've broken something down, the thermal stability. Obviously, if we just oscillate at one temperature, you can heat it up, cool it down, and see if it freezes or thaws, how easy it's going to spread. You can obviously check the mouthfeel at different shear rates and from the yield stress. So if it's a liquid, you can measure the mouthfeel of drinking a liquid at about 60 to 70 reciprocal seconds, and cooking characteristics even from like bread doughs and things like that with the viscoelasticity. So very, very comprehensive analysis available for food products. Now for pharmaceuticals, also we have a very wide range of things you can do. You can look at dissolution time. Obviously, if the viscosity goes up and up and up and eventually plateaus, you know that it's dissolved, it's fully dissolved when it plateaus, right? So you can see at any temperature, at a certain speed of shearing, how long does it take to dissolve a drug into a particular solvent? You can look at injectability, obviously from the viscosity. If it's below 10 centipoise, it's considered easily injectable. If it's between 10 and 20 centipoise, you might need an auto injector. Above 20 centipoise, really too high viscosity to inject. You can look at suspension stability for sedimentation. You can look at topical creams and see how they're going to spread out, if they're going to be more of a barrier cream, or if they're going to soak into your dermis and epidermis for drug delivery. You can see how something's going to spray from the particle size distribution of the spray droplets, which is related to its viscosity. You can obviously look at tablet coatings. Obviously, they're sprayed on and they need to be evenly coated like that. You could obviously measure the dissolution time of the tablet coating, but also you can see how uniform a tablet coating will be from the sprayability of it and how evenly it flows onto that surface. You can look at eye drops and see whether they're going to stay in the eye or if they're easily going to get blinked out by how the viscosity is. If it's too low a viscosity, then between 99 and 90% of that drug will immediately get washed out by eye irrigation. But if it's slightly more viscous, then it's going to stay put in your eye and it's going to give much better drug delivery vehicle. And obviously, there's a lot of delayed release vehicles, transdermal patches, hydrogels, and things like that. So rheology can be really central to food formulation. It can be really central for pharmaceutical formulations too. So this is a few examples of, how long do I have actually? 10 minutes?
Yeah.
About 10 minutes, yeah. So this is testing a very, very small volume. It says 40 microliters of water here. And then this is an oil standard. So this is 3.818 centipoise. I measured 3.811 centipoise. So we can get within 100th, or, you know, measure in the tenths of centipoise easily, and accuracy to a few hundredths of centipoise if you set the instrument up correctly. This is millicube water, which should measure about 1 centipoise at 20 degrees C. I'm measuring 1.008. So it's possible to measure very, very small volumes, 40 microliters here with a rheometer, to see their injectability and things like that. These are different monoclonal antibody formulations. This is the buffer on its own, but different shear rates. And this is sample C, 100 mg per mil. You can see obviously it's more viscous, but at 230 mg per mil, it's getting way too viscous. So this is too thick really for injection. This would still be injectable. And we could run standards equally to verify that the thing's running accurately. These are the spray droplets from a spray gun. So if I want to spray at a different pressure, obviously the higher the spray pressure, the smaller the droplet size, right? The lower the spray pressure, the bigger the droplet size. But also we can see with different viscosities, we're going to get larger and larger droplet size. So 1 centipoise is water. That's going to give you a certain pressure, a fairly small size. At 10 centipoise, obviously we're going to get much bigger droplets, and 100 centipoise, we're going to get much bigger droplets again. And so we can see quite easily how viscosity correlates with droplet size for sprays. This is a nasal spray where you obviously get bigger droplets if you have a higher viscosity. But there's another thing that occurs here, is that when you spray into somebody's nose, they breathe it in, it sticks on your nasal cavity inside, and you think, oh, great, I've delivered this drug. But actually, if it's like water, then it just runs down your throat and you swallow it, and you don't really get much bioavailability. The drug was delivered, sure, and then it quickly got flushed out by your nose running a little bit. And so you don't actually see much effect from that nasal spray. But if you thicken it up slightly, then it sticks on the nasal cavity inside, and it doesn't just run down your throat. And so you actually get much better bioavailability. And the thicker it was, the better that it stuck, obviously, and stayed put. Obviously, you've got a limit here. If it's too thick, you won't get it to spray very well, right? So there's an optimum viscosity. It can still be sprayable, but it gives you better bioavailability by staying put in your nose. This is a test I did with a few different types of yogurt. So I'm measuring viscosity flow curve from 0.1 to 1,000 reciprocal seconds. And quite a quick test here, 20 degrees C. So I just want to see how are these yogurts going to flow. And obviously you can see a viscosity flow curve between 0.1 and 1,000. We've gone across 4 orders of magnitude. And these are common brands. Look, you can see Dannon, Light and Fit. It's lowest viscosity. We've got Yoplait, and we've got HEB, key lime pie there in green. Should be green, right? Key lime pie. And the fruit on the bottom. Now, HEB wanted to make the fruit on the bottom thicker so that when they transport it, the fruit didn't get mixed up and it was fruit throughout. It was supposed to stay fruit on the bottom. And so they actually made this slightly more viscous so that it wouldn't mix in with the fruit. And you can see it right there. The settling behavior on the low end, the mixing, and then the mouthfeel here about 70 reciprocal seconds. For topical creams, this was the creams that you put on when you have a rash or something like this. You want to rub it into your skin. You obviously have to go through new drug application. It takes quite a long time to get formulations to market. And so the FDA came out with an abbreviated new drug application where if you've got a cream which is pretty similar, you're just making an aftermarket version of it. You're not inventing anything super new. You just have to show the particle size is about the same. It's the same drug. There's a few different things you have to go through. But for rheology, you basically have to run a viscosity flow curve to show you that the cream will rub onto the skin the same way. The yield stress needs to show similar yield stress behavior, and the viscoelastic response with a frequency sweep, let's say, should be reported, it says, for that. So a complete flow curve is able to show this is the control, the release drug, reference listed drug here. And then this is somebody's attempt at making one. Obviously, they've missed the mark a bit. It's a bit too low in viscosity. They should be making it thicker on a log scale. This is like twice as thick. So you can see that we can easily see the flow properties of these materials. Now, if you've got lower viscosity at high shear rates, this is the material that's going to rub in better. This is the one that's going to give better drug delivery. The one that's thicker at high shear rates is going to be more of a barrier cream. So if you want sunscreen, you want it to stick on the top of your skin, not soak right into it. then you actually want it to be higher viscosity at high shear rates. So there's all kinds of things you can see from the viscosity flow curve. So we were talking about yield stress of frosting, and maybe also enrobing of chocolate bars, right? This being a Milky Way. In England, we'd call this a Mars bar. I don't know why they changed the name from country to country. But people want to see these big ridges on the top of their bar, and they don't really want feet on the bottom. This used to be a problem for Mars, that the chocolate would flow down, there were these feet on the bottom. And then they found by formulating the chocolate better that they could actually give it better stand-up properties, and it wouldn't run down. They could save the extra chocolate they were wasting on feet. And it saves them millions of dollars a year, apparently, by yield stress formulation. So this is frosting, and I measured the yield stress. It's plotted here with viscosity versus stress. You can see it's flowing, it's not really flowing, and then suddenly it starts to flow. I did it in duplicate. We've got red and black as one repeat second time. But you can see, obviously, it's a lot temperature dependent, right? If it's melting, it's going to flow much easier. If it's cold, it's going to be much more resistant to flow. Now, this is going to be useful for frosting, right? Because you're going to make it for somebody's wedding cake. You're going to leave it out, and it might be a sunny day. So you don't want it to melt too low a temperature, too high a temperature. So anyway, we can see here, if I take the data as it crosses maybe 5,000 shear rate, Pascal seconds, I can actually get an Arrhenius curve for yield stress versus temperature and see, okay, is this material melting at any particular temperature specifically? Is it going to be a problem? If I want to change the additive, right, I might find that these give a yield stress high, 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 and then low. And you can see exactly where it's melting. In this case, maybe it's just softening, so there's nothing actually melting in it. But people might want to formulate for this melt in the mouth idea. So maybe where you know your temperature of your mouth is 37 or something degrees C, you could have the material melt at 34. And so that's what happens with chocolate. They make it melt at 34 degrees C. So it melts in the mouth. This is the yogurt yield stress, just presented differently, where we're applying more and more stress, and then the material starts to flow. You can see the fruit in the bottom is actually much thicker to get it to flow. So this is a study that UMass Amherst did, where they were looking at mouthfeel, and they said, okay, we want to look at chewing a food and see how it's going to behave when you swallow it. And so they took the food, and actually the test goes, squeezes down, and then it applies shear, and then it opens up. So this was supposed to be like biting, moving your tongue around, and then opening your mouth and then biting again. And so it does that repeatedly. On the rheometer, it actually moves down, shears slightly, and then moves up, down, moves slightly, moves up. And you can see the tack. So this is the down force. When you squeeze down, obviously the force goes up, right? And then when you move the gap back up again, you get this trough of normal force as it pulls off. And you've got this where you've got the rotation here. You can actually see the stress drops away a bit. The normal force drops off. So this is the rest, if you like. So we can see a force up and then back down, and then the second bite, and then the second opening. And you can see if you take those peaks without saliva, the material is quite thick. With saliva, it actually obviously much thinner, and it breaks down. And then this is with mucin. This is kind of an artificial saliva. And people are trying to formulate different salivas or artificial salivas for people that have dysphagia, so they can't swallow materials very well. And if you can get it to act exactly like saliva, then it's going to give you the best mouthfeel. So that's the maximum peak height, and this was the maximum trough for these different materials. This is for gums and gels. I'm over. I'm sorry. Okay. So you can watch gelation happen. This is cooling temperature down. We see it gelling up. And also, lastly, you can actually look at the sample under a microscope. So if you have a sample that's got emulsion droplets in it or something like that, we can see with different temperatures how they're going to agglomerate, how they're going to ripen, or things like that. So that was my last slide. I don't know if there's time for questions.
No, we do questions with that.
Okay, great.
Thank you so much.
Thank you.
Kind of some of the grinding and milling solutions that are available to get to kind of correct particle sizing, particle sizes.
Oh, thanks. You know, in the place, it's not. It's weird, but you know,
Share it again.
Yes, is this your slides? No, right? No, okay.
So I think,
It should be here. This one, right? Mhm. Sure, no problem. Do you need presenter mode? I know, you can just. Mhm. Okay, it's presenter. Mm, Let me share again here. Share again. Uh, let me see. Give me 1 second. Okay, we should share the other.
Hi, everyone. My name is Rebecca Harmon, and I'm the Regional Sales Manager for the Southeast at NETCH. Thank you all for having me here today. I'm looking forward to discussing some of our grinding and dispersing technologies with you all. Some of the other previous talks, gave some information about how to measure particle sizes. Well, this will focus on, if you're not getting the particle size distribution you want, say it's too big, you need to shift it a little smaller. This will focus on how to achieve those smaller particle sizes. So first, I wanted to start off by giving a little bit of background about our company, NETCH. You can probably guess by the name NETCH that we are a German company. But the main focus today is going to be on the Delta V1 functionality and sharing some application examples. Now, it's mostly going to have to do with a lot of the wet grinding technology, but in the last section, we'll talk about dry grinding and classifying as well. So NETCH is a mid-sized family-owned company that manufactures machinery and instrumentation worldwide. We have 3 business units: the analyzing and testing, which my colleague Phil just presented on, the grinding and dispersing, which I'm part of and I'll be presenting on today, and pumps and systems. Maybe we'll have somebody next year present on that. But within the grinding and dispersion business unit, we have multiple machines available for a variety of different applications, ranging from your lab scale to pilot, production, and complete plant systems as well. So within our grinding and dispersing business unit, we have 4 different business fields that we really try to focus on, which are chemical and minerals, food and pharma, energy solutions, after sales, and service. And so when we're talking about some of the applications in chemical and minerals, food and pharma, and energy solutions, our machines are particularly well fit for these in this industry, and they're each industries. For example, when you're milling battery material, it's really important to have low contamination levels. Contamination can have strict requirements, and it can be pretty hard to meet those. So one of the things that we do with our milling technology is we often use a ceramic liner inside of the mills in order to meet those strict contamination requirements. We also have a strong engineering team that's designed around supporting our key technology areas, which you can see here. We have wet and dry grinding machines as well as classifying machines. I'm not going to really talk too much about our homogenizers, but we do have those available too. So some of the application examples for our homogenizers are going to be face creams and toothpaste, those types of products that need mixing and dispersing. We also work with complete plant systems. But one of the things that is unique to our areas is the toll grinding. When you're working with the Delta Vita 1, which we'll get into in the next section, you're working with very small sample sizes. So say you land on a formulation and you think it's great and it's going to hit the market really well, but you're not really ready yet to invest in, purchasing additional equipment without really knowing, is this going to be something the market responds to well or not? So toll grinding can be a great option then too. So the Next Group as a whole has about 4,600 employees worldwide, and about 1,100 of those are going to be part of the grinding and dispersing business unit. So we've got 60 sales and service locations worldwide, which you can see here on the map. The blue dots indicate service sites, and the orange dots are going to indicate our sales locations. In the US, we have a location in Exton, Pennsylvania, where we have a customer lab. And within this lab is where we invite people from the industry to come in and test some of their samples out. There are multiple different types of machine and different sizes as well. So you're able to really kind of optimize what equipment you're using, and you can also optimize your process conditions at this time too. It's really our only lab in the US, but that's having its headquarters in Celle, Germany. We do have a stronger presence in that region of the world too. So next we'll talk about the Delta Vita 1. So the Delta Vita 1 is based on a dual centrifuge technology, which means it's rotating on 2 axes. Typically, this machine is going to be used for small scale formulating for a product that's going to eventually be scaled up. When you need to run a bunch of different samples, maybe in a short amount of time to test and optimize your conditions, that's when the Delta Vita 1 is going to be really helpful. But the objective of the Delta Vita 1 is to prove that a particle size or product quality can be obtained with a given formulation and bead size or type. So when we're considering some of these applications in industry, we can start to see how a particle size can be really important and key to a product's success. With some of the emulsions and suspensions that are out there that we're working with, we can see agglomeration happening or perhaps some settling happening that needs to be prevented. And that's when milling can really be a benefit. Agrochemical suspension coatings are also often going to be using milling technology in order to create nanoparticles that can improve the product quality and the stability. So a lot of the time too, we're dealing with some pretty viscous products in these applications, ointments, silicones, that sort of thing. And a lot of the time we get the question, well, how high of a viscosity can your mill handle, or can you mill in general? And a good rule of thumb is that if you can pump it, then you can mill it. The product does need to have, some flowability there. It needs to be moving in order to be mixing, but in general, if you're able to pump it, then you'll also be able to mill it. With some of these emulsions, when they're being milled, inside the mill, there's a lot of agitation going on, and this agitation tends to create foaming. Well, when a product becomes foamed, then you're introducing air into it, and the viscosity can become higher. So with that higher viscosity, sometimes that can cause a little bit of issues. So sometimes you'll see these emulsions formulated with a defoamer in order to prevent that. Now, I will say probably about 95% of the time, as of right now, the Delta Vita 1 is currently being used by drug companies to formulate injectable nano suspensions, but it is being used in other applications as it's discovered more. So by taking a look inside of the Delta Vita 1, we can see how the different parts are fit together. to really kind of understand how are these samples being run inside of the machine. So unfortunately, tomorrow we won't be able to do a demonstration, but here, you know, the chamber is going to be closed anyways when it's running, so you're not missing out on too much. But in the left, you can see that there are a bunch of small vials that are put together on the rotor table. And these are going to be 2 milliliter twist top vials. When using the sample size, you can run up to 40 samples at one time. You know, you can take them out and test them and check them for stability or, you know, the polarity of whatever you need to be measuring at different time intervals very easily. You know, it's a simple to use machine and very user friendly. But you can also run larger sample sizes too. We have 50 and 15 milliliter polypropylene tubes available for larger sample sizes. So within these vials, you're going to have your product, and you're also going to actually have beads put inside of the vials. That's what also makes this technology very unique. So we can look at the equation and remember, you know, force is equal to mass times acceleration. Well, the force that is created in these beads is what's going to be responsible for the grinding action and actually, you know, breaking apart your particles or deagglomerating them into smaller sizes. So the typical types of beads that you're going to see, at least in the Delta Vita 1, are going to be polystyrene beads or Vita beads. There's also yttrium stabilized zirconium and cerium stabilized zirconia available too. So the polystyrene and Vita beads have sanitary certifications available for them too. Since this equipment is commonly used in drug delivery and drug formulation, that can often be required. Now, in addition to the type of material a bead is made out of, you can also have different sizes of beads too, depending upon what kind of particle size you're trying to achieve. So typically when working with a Delta Vita 1, a bead size of 0.1 to 2 millimeters in diameter is going to be working well. So here we can visually see the axis of rotation that the sample is subjected to when inside of the machine running. So you've got your primary axis of rotation that can rotate up to 2,500 RPM. And at the same time, you have your secondary axis of rotation that's held at a 40-degree angle and can rotate up to 900 RPM. So when you have this dual axis rotation going on, it creates a frequent change in direction within the product. So you're able to create more opportunities for collisions at the right angle and with the right force for that particle size reduction or deagglomeration. So here it's illustrated as well how the two axes are working together in order to create that high impact force. So of course, with all of this nice grinding going on, you have a lot of shear forces, a lot of friction created, some high pressures. Well, a lot of times you're also generating a lot of heat, and heat can be an issue for some products. So the temperature control can be very important here. There is a cooling capability within the enclosed chamber. So that can be really important when you're generating a lot of heat, is to make sure the product is cooled so it's not adversely affected during the grinding process. So when we look at the rotor design here, we can see some advantages that the Delta Vita 1 offers over other similar types of equipment that are on the market today. So it uses gears for rotation and it gives it a long lifetime. So, you're able to run this machine 10,000 times before it needs to be rebalanced. So if you run it once a day, then to get 10,000 runs out of it, you're going to be looking at like 27 years. So you can run it for a very long time and you don't need to rebalance it. And a part of that is due to the special ball bearings that are used in the rotor design as well. So you've got this very big rotary table that's able to fit different vial sizes and accommodate multiple small samples as well. So naproxen is a common drug used by pharmaceutical companies when formulating. So below, we're looking at different particle size distributions for increasing solids content of this drug to compare different types of technologies. So the Delta Vita 1 works on a dual axis centrifuge where the planetary mill is just working on a single axis. So you can see with the Delta Vita 1, you're able to get a consistent particle size distribution independent of the solids content. Whereas with the planetary mill, it is going to be, you're going to see that particle size distribution shifting with the solids content of the naproxen. So it can make it a little bit more challenging, but with the Delta Vita 1, it just makes it a little bit more easier to formulate with, less variables there. So a key feature of the Delta Vita 1 is the scalability of it too. So here we're looking at the particle size distribution for the Delta Vita 1 and the Delta Vita 300 and the planetary mill at 3 different batch sizes. So the red and the blue overlapping curves, of course, are going to be Delta Vita machines. And the 2 different batch sizes are 1 gram all the way up to a 500 gram sample, and your particle size distribution is not shifted here. And then you notice you have a little bit of a higher particle size and wider distribution when working with the planetary mill of just a batch size of 10 grams. So we offer a bunch of different types of Delta Vita machines. What's unique to the Delta Vita 1 though, other than it being our smallest, is that it's going to be the only one that works with that dual axis centrifuge kind of technology. The larger Delta Vitas are going to work by the agitator bead mills. So we have designed the Delta Vita 1 in a way that the dual centrifuge technology does a really good job of simulating what's going to go on inside of these larger mills. So that's how we're able to get this nice scalability and quick industrialization. So as I mentioned, the Delta Vita 1 is our smallest in the series. It's able to work with just, 2 milliliter sample sizes. And then we've got ranges of machines from the R&D to pilot production scale, and our largest is able to handle up to 4,000 liter batch sizes. So you've got a wide variety to scale up to. Now, what machines that you're working with and the kind of grinding technology you want to hone in on is also going to be determined upon what application is the product going to be used in. So when working in chemical, mineral, and battery applications, some of the examples are shown below, like paints and coatings, printing inks, that sort of thing. Maybe the Delta Vita series isn't going to be the best to scale up to. You have been able to create this great formulation using the Delta Vita 1, but there are other types of mills too that may be more fit for certain applications like these. So the mini series is able to convert the Delta Vita 1 to these other types of technologies, like the Discus, the Zeta, and the Neos. And with the Discus, the Zeta, and the Neos, similar to the Delta Vita product line, you also have different sizes available for them as well. For example, our Discus LabStar has a batch size of 1.5 to 5 liters, while it can go all the way up to the Discus 1200, which can handle a batch size of over 2,500 liters. Now, the Delta Vita 1 and the Delta Vita Mini are relatively new machines. We introduced these in order to bridge the gap to small scale formulating so that you can easily scale up to these industrial sizes. So now, lastly, I wanted to talk about the dry grinding and classifying technology. Most of the time, the Delta Vita 1 is going to be used for wet grinding. but it can also be used for dry grinding. An example of that is gonna be when sugar was used to be built in the Delta Vita one quite successfully too. Other than that, we really don't have that many applications for dry grinding, but like I said, it's a simple machine. You can put dry material inside of the vial with your beads and hit go and see what you get. So when scaling up from the Delta Vita one, typically a Lab Compact Plus or a Lab Pilot dry machine can be used, but of course that data could be translated to some of our other industrial dry grinding equipment too. So we offer a wide range of dry grinding and classifying machines in order to accommodate a bunch of different particle sizes that people work with in the industry for these different applications. It would be great if we had one mill that could do it all. But over the years, we've created these different types of machines to really focus in on customizing and tailoring them to these different types of applications. So the air classifier is a very unique type of technology. The air classifier is often built into our dry grinding machines, and it can also be used as a standalone machine by itself as well. The way the air classifier works is that, for example, in a dry grinding machine, you have your particles that are being accelerated towards each other, and the acceleration is what's causing your breakage inside of the dry grinding machine. Well, once these particles reach a small enough size, then they have the velocity to fit through the air classifier. So the air classifier is actually like a wheel that's spinning. So depending on how fast the classifier is spinning, that can determine on how large of a particle can fit through with a given velocity. So what the classifier is really doing is it's separating a product based on its particle size into two fractions. So a lot of the times you're going to see a classifier being used in situations like if you wanted to eliminate your particle fines. Sometimes particle fines can actually be viewed as contamination in a product. So if you have this, tail on your distribution that you want to get rid of, a classifier is a great way to do that. You can also classify out larger equipment too, or larger particle sizes too. So if you want to really tighten your particle size distribution and narrow it up, then an air classifier can help do that. So that was all I had today. So thank you for your time. I appreciate it. And I think we're going to do some questions in just a minute.
I don't know. Do you want to? So there's questions for Rebecca or Michael. So.
So the classifier actually does not use beads to classify, and you can collect, yes, the two different parts that are created. Does that answer your question?
So when I say size things, I mean different size ranges that classify the particles. And then what is like the minimum size that can classify like the maximum size?
It can classify down to, probably about 1 micron, 1 to 2 microns, and then up to about 100.
What's the resolution on that? So like, is it like fractions? What's the
For
so like, does it separate them by like 1 micron each, or does it?
Oh, no, so it would have to be, so what you're gonna do is like set it, say if you want less than 2 microns to be classified out, then it would be everything under 2 microns that's classified out.
Yeah.
And then, so that's how you have your two parts. It wouldn't.
HPLC where it's getting like fractions.
Right, yeah, but we would have to do that in steps.
What is the material of the vial where you insert the sample that you want to drive? Right,
What are the vials made out of?
yes, but
Polypropylene.
so if this was by car, how do you get rid of the contamination? Does the vial doesn't break?
No, so that hasn't been an issue, but we're actually developing steel vials too. To take care of that. In some cases, you know, people do want something else, they want another option besides polypropylene, which makes sense, you know. I can see how contamination would be a concern, even though it hasn't been an issue so far, it's definitely something that could be. So that's why the steel vials are gonna be an option.
What is the carbon material that you can process with this? Like you can repeat this as your sand or like a ceramic, like a hard ceramic?
Yeah, so hardness is not gonna be a limiting factor. I mean, we've got people who are using these mills for milling tungsten carbide or silicon carbide. You know, gonna have to do some maintenance on it, but it can be done.
Okay. Other questions? I have a question about the measure viscosity.
Mhm.
How long can it take? How long can it take this? Are those like minutes, seconds?
How long can a test take? Well, yes, it can be from like 1 minute, maybe 2 minutes on the low end, up to hours. If you can run the test all night if you want to, you know, so.
But is there any need to run like for a long time to measure viscosity? How would you pick the time?
So using the high shear rates, that's very quick measurement, right? But as you go to lower and lower shear rate, it takes longer time per point. So if you want to look at sedimentation that occurs in an hour, then you're going to go to lower shear rates and it's going to take you several minutes per point.
Do you have to address the thermal energy generation or not?
You can sometimes have a problem with that, and that's something you can actually calculate by the NAME number. So if the viscosity changes due to heating, viscous heating, then the viscosity is going to go down. You're going to get the wrong result because it's viscously heating itself rather than staying at the temperature you want. So the NAME number will show you how the viscosity is sensitive to temperature and how much viscous heating occurs. But it's usually quite easy to dissipate the heat from the sample because you're measuring between small surfaces, you know, narrow gap. So you can control it up to hundreds of thousands of reciprocal seconds. That's when it gets challenging to keep the sample cold. Yeah.
Other questions?
So just a quick question in terms of, in terms of just for people's kind of knowledge, I guess one of the things is that you talk about the overlap between capillary and rotational geometry in terms of shear rate range, extending it to higher shear rate range with the capillary geometry. But you could also achieve quite a bit of that in a rotational geometry by going down to narrow gaps.
Right.
On a parallel plate, correct? But just
Yeah.
because a lot of people are interested in sprayability and spraying, and so if it's a high shear process, you could still do that on a rotational geometry.
Absolutely, yeah. So as Samuel said, if you shear a sample between cones and plates, if the gap is too wide, it flies out, right? The sample comes out of the gap. And so people often think, oh, I can't get more than 100, you know, more than 1,000 or 5,000 reciprocal seconds. But if you narrow the gap, actually the sample will stay in there and you don't have to rotate so fast to get the same shear rate. So if you go to 1/10 of the gap, you can get 10 times, more than 10 times the shear rate. And so you can get to actually pretty high shear
You have
rates.
to be careful of secondary flow and other things, especially as you go down to lower
Yeah.
viscosity fluids.
Yeah.
That respect. I mean, any other comments in terms of some of the areas which people kind of are using rheometers for or going beyond just rheology and moving into things like tribology and things like that? Can
Oh,
you kind
yeah.
of comment on some of these other kind of capabilities of a rheometer?
Yes, there's actually a huge range of accessories I didn't speak about because of time. But tribology, that's kind of lubricity, the frictional properties that material will have. So instead of looking at the bulk flow, you know, of a load of sample, how does it lubricate if I just apply force between two plates? And so you can measure that with a ball on 3 plates or 3 balls on a plate. And then you can see things like mouthfeel or lubrication properties. In a rheometer.
Kind of a few other accessories besides topology, you talked about the imaging or the microscopy.
The microscopy.
Yeah, and do you have other kind of accessories?
There's DMA attachments, so you can do a 3-point bending. There's like a 3-point bending where it actually breaks the sample, so more like a texture analysis accessories. There's tensometry, so you can do adhesion and tack. You can squeeze and tack and then pull off again, things like that. So, I mean, there's a lot of different applications. Yeah.
So it can be used for more than just rheological parameters.
Yeah.
Good point. Any other questions or? No, then we have some extra time. Yes, I mean, I don't know if we are. Oh, we're ready. So then maybe, oh, there's one question. Yeah.
Inside of idea how to measure the viscosity of a aerosol stream.
Viscosity of an aerosol stream.
That you have, instead of just one phase, now we have 2 phases, right?
Right. So you're talking about particles of a liquid in a gas.
Yeah, so let's say you have a solid particle flowing or being carried by a gas, or a liquid particle being carried by the.
Yeah, I've never done that, and I don't know. I would presume that at dilute concentrations, it's going to be predominantly the viscosity of the gas, right? So you can look that up. But if as you get to very high concentrations, maybe the viscosity would be higher. I don't know. If you have droplet connections, usually then that's when you see viscosity change. Yeah.
All right, anything else? It's not you, maybe you can.
Yes, right now we're going on the country from, so we are ready to talk.
All right, then thank you again, everyone, and thanks to all the speakers.
I got burned. Yeah, that's what I'm. But he won't talk to yes. They've walked right and they put it on car. I'm not really. So where was the lighthouse? That was like, it's not worse, but My watch number there was here prior to incident. And we were doing the last time, we went find out that all the bags were- That's the same thing. I mean, it's like one of the most dangerous, you know.
I would
cities
not
in the
have guessed
country.
that. I would not have guessed.
Oh, yeah, yeah, it's very. Not only like crime, but like any crime, like murders. It's, you know, it's one of the dangerous cities.
Are you guys staying?
I am tomorrow. I'm staying
Well,
till
you're
Friday.
Yeah, till Friday, okay. And you're leaving today or? Oh, okay.
Yeah,
all right.
yeah. Gonna go ahead and exit.
Yeah, so the put it on the people online.
Kind of get started, so if we can, take your seats. So again, we'll start off this afternoon session with the first tutorial, which is advanced light scattering for particle characterization. And it's a great pleasure to welcome, Professor Frank Sheffold from the University of Freiburg, in Switzerland. So Professor Sheffold, is in the physics department at Freiburg and also holds a joint appointment at the Freiburg Center for Nanomaterials. He's also the co-founder of LS Instruments, which does a lot of instrumentation in terms of particle sizing, microbiology, etc. But I'll maybe give you to introduce yourself a little bit as well, Frank, of your background. But again, thank you so much for today's talk and also for coming to University of Miami and spending several months with us as well.
Thank you very much for the kind introduction, and it's a real pleasure to be here. So as Samuel already mentioned, I'm from Switzerland, University of Freiburg, and I'm also on the board and developing instrumentation with the company LS Instruments. And at the moment, I'm on a sabbatical leave at the University of Miami, hosted by the engineering department and then Samuel. So this. Oh, now it's working. Okay. I just want to say a few words about how we transfer knowledge that we mainly acquire during our research in light scattering in the university laboratory. So the LS Instruments is a company that we founded in the current state some 14 years ago. And the idea and the goal is really to bring the most advanced light scattering techniques, static and dynamic light scattering, also microbiology, as Samuel mentioned, to the users, and continuously develop new approaches to improve this type of light scattering techniques. I mean, in tandem with many other advanced companies, as we have already heard this morning. So I think this is complementary. And the two founders are myself and Peter Schurtenberger, who is now in Sweden, and they have extensively spent time in major research institutions and also been active in the research community. So that ties together the research that we're doing that is then translated into instrumentation and our academic part. I'm mainly also highlighting this if you're interested in this type of light scattering methods and technologies. There's a whole range of seminars that you can also find online that go beyond of what I'm able to present in this relatively short time. So what I'm presenting today is partial. Sorry, this was the wrong. Okay, now we are here. It's partially covered by this webinar that I gave for LS Instruments a while ago. There's a long webinar also by Eric First from the University of Delaware on DWS microbiology, which I will barely touch due to lack of time. Another one by Samuel while he was still in New York on applications of diffusing wave spectroscopy for cosmetics. And something that's also very interesting, I think, for many people are gels. So there's also a webinar on gels and many more. So if you're interested, just go to the webpage and look through which webinar might be of interest for you. Okay, without further ado, I'd like to delve into the light scattering part. So since it's a tutorial, I'll start relatively basic with explaining the fundamentals of how light scattering works. We have heard a little bit of that already in the morning. And then I will progress by explaining what are the new technologies and the new advances that we have introduced in the field, and we'll illustrate that with a couple of applications, depending how much time I have left. So the main ideas you have already seen in the morning is that we have a system, and here we are talking about suspensions, so particles or polymers or proteins that are dispersed in a liquid, often water. And if you do your light scattering experiment at home with a laser pointer like one I'm carrying now, you see that if you shine through water, there's very little scattering. It's almost basically undetectable with the naked eye unless you have dust inside. Whereas if you have a particle suspension, then you can see the trajectory of the beam going through the cuvette here due to the light that is scattered out of the sample. So this is light that has been scattered. This is not kind of illuminating the water. This is really light that is scattered in the direction of your eye. If you look angular dependent, this you can do for relatively large particles if you put the screen behind your cell. So this is the same type of cell as here. With scattering particles, then you see this type of rings that are characteristic for the size of the particle. And then if you have a movie, this used to be a movie, but now it's not embedded, then you see the fluctuations of the laser light scattered, as it was explained also in the morning. And the speed of these fluctuations, the time scale of these fluctuations provides information about the hydrodynamic radius, and I'll come back to that briefly later in my presentation. So why is light scattering so popular or used in almost every laboratory? It's that the reason is that you can cover a really large range of sizes of particles, depending on whether you use static light scattering or dynamic light scattering. You can go from almost the molecular scale, so a fraction of a nanometer or a nanometer, to tens of micrometers or even more if you use laser diffraction, as we have already seen in the morning. And this can be sometimes complemented with other techniques, but light scattering is really one of the, or maybe the technique that allows you to cover all these length scales basically with one instrument or two different versions of a similar instrument. Then you have other techniques like microscopy, neutron scattering, particle tracking that we have seen in the morning, ultracentrifugation, that are also very useful, have specific advantages, but don't cover this very broad range. So kind of the base technique for many people for characterizing particle sizes in solutions is a variant of light scattering. And here on the left, I've just plotted a few of the many, many different soft matter systems that people are looking at, that we are looking at: particles, droplets, polymers, proteins, viruses, and so on and so forth. So this is why light scattering is used so much. And we distinguish, as we have seen already today, between static and dynamic light scattering. And these two methods are linked and can be integrated also in one single instrument, where you can measure angular dependent, static, and dynamic light scattering. So I'll introduce these techniques. I'll be a bit faster on the dynamic part because we have heard a lot about this already in the morning, which will probably save me some time to discuss more applications. And then I'll talk in some detail about something that we invented, which is the cross-correlation, 3D cross-correlation light scattering, which eliminates all contributions from multiple scattering, which can contaminate your system without that you noticing it. And then the last part, I'll discuss several applications, as I said, as time allows. So let's start with the fundamentals of light scattering. So I'll start really at the basis, but I will not go into all the steps because I think this will bore you, and also there's not enough time to do that on a kind of a lecture level, but I'll try to introduce the important steps. So in light scattering, we have a light beam, a monochromatic light beam, which these days is always a laser. And this light beam has a wavelength. It travels in a medium with a refractive index n. And the wave number or wave momentum is 2 pi over lambda. And this wave in the medium will excite dipolar oscillation. So this is a wave that can interact with charges in the medium. As it is illustrated here, there will be a force due to the electric field on the charge. This will polarize the molecules inside the particle and will therefore lead to an oscillation of the dipole. And this dipole, like an antenna or an emitter, will in itself then emit radiation. And this is the radiation that we detect when we look at light scattering. So a particle is a collection of atoms, and the polarizability of these atoms, this determines how much light scattering you get. And this is then, in a simple model, can be also used to calculate the refractive index or the polarizability of your particle. So we have this dipole, the dipole is induced, the dipole oscillates, and this radiation emitted from the oscillating dipole, that's the scattering. It's very simple, it's classical electrodynamics, and can be treated on that level to some extent quantitatively. What is important is that we are, in this context, dealing with elastic scattering, meaning the dipole oscillates with the same frequency as the incident wave, which is given by the by the light wavelength and the speed of light. So you have frequency is wave number times speed of light. Okay, so we have elastic scattering. So we have scattered light that comes from this polarizability. And then we have many, many sources of scattered light. So we have many, many of these oscillators, oscillating dipoles that emit, and then they interfere, like you have it from a double slit or from a grid. You have interference. And in this case, the interference is between all the points inside our particle. So we have incident light, we have dipoles that are stimulated here to oscillate. They emit in a certain direction where we have the detector, and there are many of them. So we have to look at the relative position between these emitters. The relative distance between these emitters is controlled by the size of the particle. So the maximum distance is the diameter, and then we have a distribution of distances inside the particle. If the particle is a sphere, this can be analytically solved. If the particle is more complex, like this potato-shaped particle, then you have to do a kind of a numerical analysis. What is important here is that the incident wave comes here. It generates a scattered wave with the same properties, propagating in this direction. And then the other emitter here introduces a phase shift. So the path that the light travels here is longer along this path than here. And the differences here are illustrated by these fat, bold lines here. So there are different optical paths, which leads to the fact, as we have already seen also this morning, that sometimes you have constructive interference, meaning there's more light generated at the detector, or destructive interference. And this can be calculated, this optical path length difference, by introducing an optical phase, the phase of how the waves are positioned relative to each other. And this can be easily calculated by this vector product between the incident wave vector and the position distance between R0 and R prime here, or R here. So this is the distance vector. I will not spend too much time on the mathematical details. Just listen maybe to the general concept if you're not familiar with the mathematical details, but it's important that these distances introduce phase differences between the waves, and these are then controlled by the so-called distance vector and the wave vector, which is Q. Q is the difference between the incident wave vector and the scattered wave vector. And the angle between these two directions, it's a scattering angle theta here. Okay, now we can do that over all possible distances, and this gives us then the scattering pattern of a single particle or any type of distribution of material that we might have in our sample. So this can be a continuous modulated distribution, or it can be a collection of scattered, independent of whatever your system is. All of this can be summarized by this contribution here of this interference term. And then you have to integrate or sum this interference term over all possible R primes that you might find in your system. So this is relatively simple. This is the same for X-ray and neutron scattering. So what is important is that the wave length that we are using to probe our material also sets the resolution that we have in static light scattering. I'll come back to dynamic light scattering, where which works a bit differently. But in static light scattering, classical scattering like light, X-rays, or neutrons, the wave number controls the distances that you can probe. So 1 over q is the distance you can probe, and 1 over q is proportional to the wavelength. So if you have a wavelength of visible light, which is a few hundred nanometers, typically you can probe structures that are on the tens or hundreds of nanometer range, and you cannot see atoms or molecules as you would if you would use X-rays, for example, or neutrons. And the typical undulations of the scattered light intensity are also then for objects of these length scales. That's why light scattering is perfectly suited for studying soft materials, particles of tens or 100 nanometers of size, and so on. Okay, so how does it look in a practical experiment? If you do an angle-resolved, multi-angle or variable angle light scattering experiment with a goniometer system like the one that Alice Instruments produces, you have a detector here that can move over a certain range of angles, theta. You have the sample here that is moving. It's still important that the sample is under Brownian motion, so you get statistical averages of the configuration of the sample. And then you measure the mean count rate, which is then proportional to the scattered intensity as a function of angle. And as I just said, for the angle and the wave vector are proportional. I mean, not directly proportional, but they are linked via the sine function. So once you have the angle, then you can either plot the intensity as a function of angle, or you can plot the intensity as a function of q, the wave vector, or the modulus of the wavelength. Okay, and now it gets a bit complicated, but I'll walk you through the different steps, because this is really important if you want to do a quantitative and precise measurement on your system. So the scattered intensity now that you measure as a function of angle or q has a number of parts here. Some of them are interesting and some of them are just instrumental parameters. So here we have the incident intensity or the incident power of our laser. This is known. This is something we can measure. We have a factor that is related to the geometry. So how big is the aperture of my detector? Where is it positioned? How far is it away? These are things that you can calibrate. Then there is a parameter that is related to the optical properties of your sample. So this is the scattering contrast. So how much material, I mean, how high is the polarizability and the scattering contrast of your particle? If you have polystyrene or silica or polymer gel, this can be different. And then the parameters that are directly related to the size and the structure of your material are the last three parts. So you have the volume squared. So the scattered intensity is proportional to the volume squared. This we already heard this morning. This is directly related to what is known as this r to the power 6 factor. So the size of the particle influences the scattered intensity with the volume squared, which for spherical particles would be the radius to the power 6. Then we have a shape function, P of Q. So this is a characteristic for the shape of your particle. I'll give you an example in a minute. So this is the form factor. And then if you have interaction between the particles or you have other more complex systems, then you can also have structure between different particles. So they are not randomly positioned, but they are structured in some kind of specific way throughout the sample. And this can be an indicator for attractions or repulsions, or if you have gel, some kind of hierarchical structure that is captured by the structure factor. I want to make here one remark because this is sometimes a bit misunderstood. I also had the feeling this morning. The scattered intensity is proportional to the power 6 to the radius, r to the power 6. But but the particle volume also scales with r to the power 3, meaning that if you work at constant volume fraction of particles and you change the size, it doesn't scale with the power 6 because you have less particles. The particle number density also goes down. So it's not quite as bad. So you're not going to the power 6. You're more like going to the power 3 if you have a mixture of small and big ones and you're more interested in the volume, relative volume. So this is something, because this r to the power 6 is sometimes a bit too over hyped, I think. And if you look at the angular dependence, also changes. If you have larger particles, there's more forward scattering. So as a matter of fact, the total cross section, so how much of the light is scattered out of the way, for larger particles, for particles larger than the wavelength, usually actually doesn't increase so much. So whether you have a 1 micron particle or 2 micron particle, if you have the same volume fractions of the two populations, they contribute more or less equally to the scattering cross section. So it's a bit of a detail, but I mean, sometimes this R to the power 6 gets a bit overhyped in my view. So look carefully if you have different populations. Are you looking at number distributions or C averaged or size volume distributed? That makes a big difference here. Okay, so now a simple example is a sphere. Obviously, a sphere is always the simpler thing we can look at. So we have this function, which is the distance distribution function. So this is the distances that I mentioned before, this R prime between the different, or in this case, R between the different lumps of material or atoms within our sphere. And this is then squared in order to get the quantity that characterizes the shape of the object proportional to the scattered intensity that we measure. And what is a bit unfortunately, but there's nothing we can do, we cannot change nature or mathematics, is that this quantity that we measure is not directly a Fourier transform of the density distribution. It's a Fourier transform of this density distribution correlation function, so the distance correlation function. That's a complex mathematical object, but that makes life much harder. So you cannot easily invert what you measure to get the real space picture of your sample and the particles that you have therein. So usually what people do, or what everyone does, is you do some kind of forward modeling. So meaning you have a model, like you say, okay, my particles are spheres. I know how the spheres scatter, and then you fit the data with this model. It's very difficult. I mean, there are ways to do it the other way around, this inverse Fourier transform, but it's difficult and problematic, and you still don't get the full shape out of it. What you get out of it is this distance distribution function, and then you still need an interpretation of what you're doing. This is sometimes done in X-ray scatterings, but I will not go into the detail. Usually we do forward modeling. So we have a model, we fit it to the data, and this model has certain parameters. In this case, the model has only one parameter, which is the particle radius. So if you fit or two, if you want, the particle polydispersity. So this is the solution of the particle form factor, which means everything that is related to mass and optical properties and instrumentation is in the prefactor. And here we're only looking at the shape contribution. And this then you can fit to experimental data. And you have only one parameter here, which is the particle size. And this works very well. Now, if you have a distribution of particle sizes, you can convolute this result with the particle size distribution, as it is shown here for the number distribution. And then you get different results. So here the blue line is the most uniform, not quite monodispersed, but always monodispersed. You see, oh no, the red one, perfectly monodispersed. You get these deep minima. So you have zeros here due to the destructive interference that are at characteristic positions relative to the size. And then if you introduce polydispersity, here indicated by this blue and green line, I forgot to put the numbers, but this is maybe 10 and 20% or so. You see that these minima are smeared out. So that's very important that you know what is the signature of polydispersity in a static light scattering signal. This can be fitted, but this can also be convoluted or confounded with other effects like multiple scattering I'll come to later in my presentation. And if you have a lot of polydispersity, you can see you're losing all these features, these rings or minima that you initially had for the uniform particle size distribution. Everything kind of falls off gradually, and then it gets much harder to extract a particle size if you have this highly polydispersed system. Here's an emulsion from a measurement that we did on emulsion droplets. So these are radius 400, nearly 400 nanometer, polydispersity index 12%. And here you see you get a very nice fit, and you can very nicely extract these two parameters from a fit of the model relatively simple model to the light scattering data that you collected as a function of angle. I'll give other examples later. Okay, you can also extract the particle size in the low angle regime or in the low Q regime by doing a so-called Guinier plot. Some of you might have heard about that. So if you expand the shape function for small q, go back one slide. So if you expand this function for small q, then you get a much simpler expression. Then you can simply plot the shape function as 1 minus q squared rg third, and rg is the so-called radius of gyration. And this is defined here as the integral over this distance distribution functions times r squared. And this is reminiscent, or it is corresponding to the moment of inertia. So like you have all the mass, it's the second moment of the density distribution. So like if all the mass is concentrated on a shell that has this Rg radius with respect to the mechanical properties of this particle. You also find that in polymer and so on. So it's a common quantity, and this can be simply extracted by plotting the scattered intensity measured as a function of angle or q logarithmically, and then the slope of this curve at small q gives you the square of the radius of gyration. So this is usually applied for small particles because this has to work in the small angle regime relative to QR. So QR is the dimensionless wave vector times the radius of your object. So if you want to be small in that measure QR, then if R is small, then it's easier to be small with this whole object. So usually this is applied to small particles or polymers and these type of things. Whereas for big particles, like I've shown you in the previous example here, is emulsion droplet, which is almost a micron, and then you can nicely see the minimum, which gives you very good stability in terms of analyzing the size, whereas with this particle, with a normal light scattering apparatus, you cannot easily extract the so-called Guinier regime, which would be here in the very low Q range, which is not accessible because there are certain limitations of what you can do with light scattering apparatus in terms of angle, scattering angle. You can also measure correlations between in dense particles where the particles are structured, but I will not go much into detail, although I will come back to the structure factor in a minute. Okay. Coming back to this general expression for the scattered intensity. So we have a lot of these prefactors. We had the molar mass here separated with the mass concentration, written in a slightly different way. We have still a sample contrast, and we have the instrumental constant, the structure factor, and maybe some background scattering. And now I want to go for the so-called Zim plot. So how you can analyze that also in terms of varying the density and varying the scattering angle or the scattering wave vector. So if you do this type of scattering, static light scattering experiment, as I've shown before, you're doing this angular scan of the detector. And now you can plot it in a slightly different way, which is very useful for extracting certain quantities and very widely applied if you do it right, because it corresponds then, it's proportional here to the volume squared, the molecular weight, again, the shape function and the structure function. If you have weakly correlated systems, you can relate this structure function to the interaction parameter quantified by the second virial coefficient. So these are weak interactions, repulsive or attractive. So if this, in this approximation, if A2 is larger than 0, positive, it quantifies repulsive interactions. If it's smaller than 0, you have attractive interactions. And this can help you to quantify phase behavior. These are thermodynamic quantities that might help you, and people use that in protein stability, protein crystallization to predict how would be your phase behavior at higher concentrations, where you might have phase separation and crystallization, and also in polymer systems. If you want to do this analysis, it's a bit more involved because you have to vary not only the angle, but you also have to vary the concentration here. So W here, this cursive W is the particle concentration. It can also be expressed in terms of the particle mass. So here, such an analysis is shown back to the early days, and I show you a more recent example in the next slide. So here now we have this delta R is called the excess Rayleigh ratio. It's proportional to the scattered intensity times all these instrumental prefactors that I will not go into the detail again here. And here plotted as Q squared plus a parameter and the density. So here we have density, and here we have 1 over scattered intensity. So if you write all of this down based on what I just showed you on the previous slide, then we see that this quantity here redefined is 1 over the molar mass times the shape function, the form factor, and the structure factor. If I use these approximations, then you see I have 1 over the molar mass. I have this Guinier type of parameter term, and I have the interaction term. And now you see we have separated the Q dependence and the concentration dependence. So if I go along this axis, I only have the Q dependence. Sorry. Here, okay, I can separate the Q dependence and the concentration dependence, and thereby I can separate these two lines here that are bordering this kind of parallelogram. Okay, so if I extrapolate to the density 0, here from the slope, I can get the radius of gyration. From the intercept of this function, I get the molar mass. If I go to Q equals 0, then I can extract the interaction parameter, the second virial coefficient. And as I just said, the intercept of these two lines where they cross at the apsis here is 1 over the molecular mass. So I get a lot of information from this type of ZIM analysis on particles. You can use that for small particles, proteins, and it's widely used, and it's a common technique for characterizing polymer globules in solution. Okay, here's a software that LS Instrument develops that automizes this type of analysis. So you run an angular scan at different concentrations, you load the software, you load the data in this software, and then you can extract certain outliers. You can automatically obtain the molecular weight, the radius of gyration, and the second virial coefficient from such an analysis. And that's routinely done these days. And you can basically only do it if you have an angular dependent analysis tool like this goniometer that I showed you in the illustration just before. Okay, now I'm about halfway through, a bit more. So this is kind of the static scattering data. So you can apply it to large particles. You can even apply it to larger particles if you use the diffraction apparatuses that we have already seen this morning, which I will not cover here. And you can apply it for small objects if you do these low angle approximations in the Guinier or ZIM regime. These are very powerful tools to characterize small particles and even interacting small particles or objects. On the other side, we have the dynamic light scattering. We have already heard a lot about this morning, so I'll be relatively brief on the fundamentals. Here we are studying also using light scattering, but we are studying the Brownian motion. So as a reminder of what we heard this morning, you can do that with microscopy, and you can also do particle tracking, as we have seen, based on the scattered light. Or you can do light scattering in the far field, so with a detector or a screen. And as I said, if this would be a video, you would see the fluctuations of these laser spots here, of these scattered light spots. They are called speckles. They fluctuate in time, and they fluctuate characteristically for the speed of the diffusion due to Brownian motion. And this we have seen this morning. So in a static and dynamic light scattering goniometer setup, you would have a laser here, you would have a detector here, and then you could change the scattering angle continuously from some 10 degrees to 150 degrees. You can probe these fluctuations on many length scales, and you can get a more stable analysis of the particle and particle size distribution. And you're probing now the fluctuations of the scattered light and not the mean intensity of the scattered light as we have done before. Okay, Brownian motion, thermally activated Brownian motion is something we've heard about, so I will be brief. This leads to fluctuations of the scattering intensity. These fluctuations are used to construct the correlogram, I think it was called in the morning, or I think more properly the intensity correlation function via a digital or software device. Not go into the details. This is the mathematical expression. And this correlogram or intensity correlation function, this is related to the Brownian motion as it is expressed here with the, again, with the scattering vector and the displacement vector. So this is the, gives then rise to the so-called mean square displacement that you have also already seen this morning as well. So all summarized, what we measure is this correlogram, correlation function, which decays exponentially with the mean square displacement and the square of the scattering vector. And the mean square displacement for Brownian motion is linear in time with the diffusion coefficient. And the diffusion coefficient, I think it comes here, is given by the Stokes-Einstein relation that we have already seen this morning. It's a few steps, but in the end, it's really very simple. This is very fundamental theorem on how particles move in thermal equilibrium, and everything else is very precise. So the difficulty here is, what is the hydrodynamic radius? We have heard about that this morning. So it's the equivalent hard sphere diffusing. And what about the particle size distribution? So the particle size distribution is nothing else than taking this exponential and convolving it with the particle size distribution. That part is easy, but the part back is difficult. So get back from what you measure to extract the particle size distribution can be difficult. And we heard this morning, there's a lot of efforts and research going on to improve this by measuring several angles and by improving the algorithms to extract the particle size distribution. So it can be done. You can get polydispersity fairly easily. Distinguishing different populations of particle sizes with dynamic light scattering can be challenging. And we heard this morning, the limit is about a factor 2 to 3 in average radius if you have different populations of particle sizes. And then it also depends on the contribution to the signal, how much of the signal that you measure is coming from one population to the other. And there again, it's not only the size, it's also the volume fraction. So how many particles you have, how much of the volume is occupied by the species. So in general, we can measure from very small to very large particles, nanoscale to micron scale. It's fairly easy. And I also want to emphasize, I mean, there are other techniques that are very useful. We heard about backscattering close to the cuvette wall or nanoparticle tracking. I mean, one of the nice things about light scattering in general is that you are measuring in the bulk. You're measuring far away from surfaces. So if you push these other techniques to the limit, small sample volume close to the surface, you have to be careful that the surface is not influencing your measurement, which is not the case if you do traditional dynamic light scattering. So it's very, very stable. Okay, there's just a mention in terms of this inversion of getting from the measured correlogram or correlation function, getting back the particle size distribution. We have spent quite some time in improving the stability of this a priori ill-defined inversion by applying a machine learning algorithm to stabilize the constraints that you set on this inversion process. And this is something that you find described also on the Alice Instruments homepage as a regularized nonlinear least square fit optimized via machine learning called Coran. And here's just an example where we applied this to a mixture of 4 and 45 nanometer particles, where with traditional contina analysis, you will get spurious faults peaks, whereas with the Coran algorithm, this improved algorithm, you can nicely reconstruct these two populations. But this is a factor of 10. In the morning was at a factor of 2 if you have multiple angles. All of this is challenging. If you want to be better than 3 to 5, you have to be very careful, as we have heard also this morning with the baseline corrections and so on. So there's improvement going on. Something that we have also implemented, which is non-trivial for treating with these correlation functions or this correlogram, is the noise So you have always statistical noise in the measurement in addition to baseline fluctuations and dust. You also have statistical noise in how many photons, how much light you collect during a measurement. And this can be quantitatively included in the analysis which we did, which gives you an error bar, not only the fit to the parallelogram, but also an error bar around the parallelogram, which can also help to stabilize the analysis of the correlation function and the inversion that you're later doing in order to extract different populations of particle size. Try it out if you're interested. I'm sure you can get access to a demo version if you want to play with different signals and particle size distributions. And as we heard also this morning, it's always good to look at the bare correlation function first to see that the quality of your data is good before you're going through some blindsided analysis tools. Okay, this I can skip. So now to the last 10 minutes-ish, I would say. I'm on time, it's okay. Is the concentrated system. So we have heard it this morning. If you do light scattering, dynamic or static light scattering, you have a sample that is usually has to be diluted, or you have a powder or something and you put it in solution and you put it in your instrument. And that can be very dangerous because you can either be too dilute, then you get a lot of problems with dust and maybe scattering from dirt on your cell and so on, or you're too concentrated. If you're too concentrated, then you get contributions from multiple scattering. And the bad things about the contributions of multiple scattering is that, well, depending on the instrument, you might not be alerted that you have multiple scatterings. You might measure some kind of particle radius. You say, okay, I'm fine. Let's move on to the next thing, but it might be wrong by a factor of 2 and you don't know. I mean, there are other companies I know that are dealing with this problem, as we have heard with the Malvern system, but we have developed a different type of approach that completely suppresses this multiple scattering contribution. So if you get a result, it's correct. If you don't get a result, then you have to dilute. But usually you don't have to dilute because it suppresses efficiently the multiple scattering. And this is illustrated here in the next 2 slides. So in a dilute sample, we have only single scattering, meaning the incident light hits a particle, the dipole oscillates, or the many dipoles, and at the detector we measure the signal from this one particle. And this defines the scattering angle. If you have multiple scattering, as shown on the next graphic, the light hits the particle scatters light, and then it scatters light again by another particle, and maybe by a third one. And then it reaches the detector. I mean, now it's easily seen that there are many scattering angles involved. So whatever you detect, you don't know what is the scattering angle of that you're probing because there have been several scattering events. And basically, you cannot use this signal to reconstruct the particle size because the particle size that you measure very strongly depends on the scattering angle. Small scattering angles, you have very slow fluctuations. For the same particle size, at large angles, you have fast fluctuations. So this completely corrupts your signal and usually leads to faster decays and apparently smaller particles that are in reality not that small. So you know the detector angle, but you don't know the scattering angle. And therefore, the analysis is kind of useless. And depending on how much multiple scattering you get, and usually it can be quite a bit, you might completely misestimate your particle size, and even worse for the particle size distribution. So this is illustrated here just with this graphic. This is actually already exaggerated because in reality, already here you have a lot of multiple scattering contribution, and then you get an undetectable systematic error if you don't take account of this problem properly. And there's also other problems. Some samples you don't want to dilute because maybe the properties change, and it's generally more time consuming. In principle, if you do a dynamic light scattering particle size analysis, you should always run 2 or 3 concentrations and check that you get the same result for all 3. Or you suppress the multiple scattering like we are doing, then you can be sure that your measurement will be correctly reflecting the Brownian diffusion coefficient due to that is used in the Stokes-Einstein relation. Okay, I have a few minutes left, so I will show you how this is done. So what we're doing and what we invented is that we are, instead of using 1 laser beam, we are using 2 laser beams. So we split the laser here before it enters the sample. We have 2 beams
both beams are focused in the center of the scattering cell. Here's a real live picture of how that looks, which you should not do because I guess it's not allowed. Because, usually this is obviously closed for safety reasons, but if you open it, you would see the two beams cross here. And then we look at the scattered light from these two beams on two detectors. And basically what we are doing is we are doing the same experiment twice under a very small inclination. And in a nutshell, what we are doing is that the contributions of single scattering take the same path from the upper to the lower detector as from the lower to the upper detector, so they give you the same signal. However, if you have multiple scattering, you have different trajectories arriving at different detector, and they even out to background. So we don't have a contribution from multiple scattering, we only have contributions from single scattering if we cross-correlate these two detectors. This is all done automatically, you don't have to worry about it. This is something we developed almost 15 years ago, published here and implemented in the light scattering setup here through cross-correlation filtering of multiple scattering. And then we get the pure single scattering signal. Let me see here. And we are doing this modulated so that there is no crosstalk between the two beams. And this modulation happens at very fast speed, so it doesn't show up in the correlogram. This is at several megahertz of modulation. So we can filter out the single scattering signal with this patented technique that developed in my lab a while ago. So how does it look in practice? So here we have tested, I think this is polystyrene, 100 nanometer particles for different turbidities characterized with the sample transmission. So if the sample transmission is 99%, it's very dilute. The autocorrelation and the cross-correlation modulated give you basically the same as we heard also this morning. You get this kind of signal or intercept, which is about 70–80%. As you introduce the pure 3D cross, you get a drop-in signal because of the crosstalk, but we can ignore that. We are focusing on the most modern implementation and the classical implementation. So in the classical implementation, if the transmission goes down, sometimes you get a reduction in intercept that's related to the coherence of the laser. And you also get a reduction of intercept if you have multiple scattering in the 3D cross correlation, so the technique that we developed. So what happens is the signal to noise goes down. But what does not change, and this is shown here, is the particle size. So in 3D cross correlation, this is the red and the black symbols, the particle size is 45, nearly 50 nanometers, independent of the turbidity. So here the transmission is 0.2%. So this is really white stuff. You have very little light transmitted. Most of the light is multiple scattering. There's a little bit of single scattering left. We can still detect it, and we can get the same particle size. If you would just stick that into your normal particle sizer, the apparent radius would go down by a factor of 3. And most instruments wouldn't tell you, they would just give you the wrong result. So this is the way this can be done very efficiently. You can also apply that, and this is almost my last slide. You can also apply that for static light scattering, whereby you correct from the detected signal and the signal to noise. The signal to noise is characteristic for how much multiple and single scattering the detector receives. So we can actually measure the percentage of singly scattered light that we detect. And by this, we can correct the static light scattering signal. So here's a comparison between doing this correction and doing nothing. So if you have this is a polystyrene particles with 430 nanometer diameter. If at a certain concentration, I don't remember, turbid enough that you get a full smearing of the scattering form factor. So the black line is what you expect to measure for this particle based on Mie or Rayleigh-Gunn-Stibbe theory. The red signal is what you measure if you don't correct for turbidity, because turbidity smears out the characteristic interference pattern, because you measure at 90 degrees, but the light might have come 45 and 50 on the way to your detector. So you get contributions from other scattering angles
because of the multiple scattering, and that smears the whole signal. And you might misinterpret this as polydispersity, but it's not polydispersity, it's just multiple scattering. Correct for the multiple scattering, then you can recover the original nice form factor of the sphere. So this can be very useful if you want to really do very accurate measurements of particle sizes, in particular in dynamic light scattering, but also in static light scattering. Here's also an example of a more applied system. So we work together with Solvias, which is the former central research of Novartis in Basel, to characterize a nanoemulsion, Adavax, which is an adjuvant for vaccines. So this is the particle size at relatively high concentrations with the standard backscattering already improved technique. And you see that the particle size eventually drops by a factor of 2 if you go to 5%, nearly 5% volume fraction. Here's a real picture of the adjuvant nanoemulsion in a now reduced size cell where we can even shorten the scattering path. And here you see now the relative particle size error now plotted as a function of the volume fraction between the multiple scattering suppression using the 3D DLS that we developed and the standard backscattering. You see there's almost no error if you do the modulated 3D, because it really gives you either the correct result or you get no correlogram. It will be flat and then you cannot analyze it, but it will never give you a wrong result. Whereas in essentially all other techniques, even if they try to suppress the multiple scattering, you always get a result and you don't know how much it is contaminated by the multiple scattering contribution. And in this case, this can reach almost 50% error. So this is published in this paper that appeared this year if you want to look it up. So this is really a powerful tool to suppress multiple scattering in terms of a really advanced light scattering technique. In order to do this advanced light scattering analysis, normally you would need to have a multi-angle setup that in the most versatile version has a variable scattering angle in a goniometer setup, and that's what LS Instruments people have developed a modern version recently where you can do this variable multi-angle static and dynamic light scattering and extract all these parameters that I have been talking about, and you can implement there this 3D cross correlation that efficiently removes all multiple scattering. I'm not so much into the practical kind of operation of the company. So if you have any questions about that, feel free to contact the guys at LS Instruments. There's an office in Los Angeles that is run by Ian Block, and he'll be happy to hear from you. This is my group in Fribourg at the University of Fribourg. Thank you for your attention. And tomorrow I'll present some applications of the techniques to systems of relevance.
Time for some questions. Any questions? Everyone seems to have
Everyone's saturated, yeah.
Yes.
Oops. I killed the screen sharing, sorry. Okay. Let me go back to 19, you said? This one?
No.
Do you want to activate that again?
Yes.
Give me a second. Okay. Next one. This one?
Yeah, I think that's the question. So where is the most of the market?
This is the time averaged count rate or intensity that you measure. You can write that as I of Q and T. Then you have the time dependence. Here the time dependence. So this I of Q is, sorry, now I went out again. Okay, the I of Q is the time average. So I could have put brackets as time averages.
So let's say you randomly set the configuration of the particles, but they are not moving.
Yes.
You won't get different results.
You need to do time averages to get noise-free data. If you don't have Brownian motion, then this interference pattern is static, so you have fluctuations in space of the intensity that you have to average out by Brownian motion. Otherwise, you have to rotate the sample. So you have to do some kind of ensemble average over the position of the particles, either by mechanically moving the sample or by letting it relax. So this is a time averaged intensity, an ergodic average. You're using the ergodic hypothesis, you get
Now, the sample is static, right? Meaning that there is no macroscopic motion of the fluid. It's still.
there's Brownian motion.
Okay.
Yeah.
So would you be able to apply the flow, the move? There is move motion of it.
You could apply flow, yes, that's also a way to.
With this.
I mean, usually people try to avoid that because it gives you additional. I mean, we've heard sedimentation or creaming of the sample. There are specific applications where you could flow the sample that could be of interest. Usually, this is not what is done here.
Then you have to separate out the contribution from the Brownian motion and the motion due to the.
Yeah. If the flow is not too fast, you can separate this, but it's an additional complication. And at the moment, I mean, you could measure the flow velocity, but I don't know if that's of interest. You wouldn't learn anything about the sample unless if you flow a lot such that the sample would be influenced by the flow. Usually the flow would be too fast and you would lose the signal due to the Brownian motion.
And for non-ergodic samples for gels, I mean, you do the averaging in the instrument? Right?
Yes, you can do that. I mean, there's an additional motor that is available that you can put to rotate the sample for ergodic averaging. Yes.
Oh, right.
Thank you very much for your presentation. So one, you have a way to see that.
I mean, normally, tomorrow I'll show some applications. So normally, like in this example here, you would record the count rate as a function of angle. And then there are different tools that are implemented in the software, like the Zimplot and the Guinea plot, where you can extract certain parameters. If you want to fit the form factor of a larger particle, usually would do that offline in some software, because that can depend on the refractive index. And that's what I showed at the beginning. So you can plot this as a function of Q, and then you can fit with a certain fit function to extract the polydispersity and the particle size. It's not automatically implemented as far as I know. Mm-hmm.
Right? One was capturing means that you're getting like
Yes.
now you have the capturing better from two different points.
So on both points that you detect, you have contributions from single scattering and multiple scattering. They are kind of mixed. But by comparing the two over time, you can filter out the multiple scattering, because the single scattering will be the same on both, whereas the multiple scattering will be different. And over time, the multiple scattering then averages out, whereas the single scattering stays. That's the way it works.
How do you get paid for your expected other than
I mean, there's a Zim approximation. If you have a more structured system at even higher densities, and you have particles, for example, then you can divide out the particle form factor and you get directly the full structure factor. That's something I think I briefly skimmed over. So that's what we are doing if you're working with particulate system at higher densities. The problem with particulate system at higher densities is that they're usually very turbid, unless you work with model systems that are nearly refractive index matched. So for most people working with applications, I mean, you're not clearing your sample just to access the structure factor. Then it's maybe better to go for X-rays or neutrons. But in model systems, you can reduce the scattering so much that you can, even at 30–40% volume fraction, still access multiple scattering free the performance structure factor, and then you can simply divide. I mean, if you can properly measure this even at high densities, like 30–40%, then you can simply divide the measurement by the form factor, which you might know if it's a sphere, and then you can study the structure factor as a function of density. And people have done that for charged particles, if you have heard this morning, and also for hard spheres, for emulsions, for mixtures. All of this can be done. But it's not so much of practical relevance, I would say, because you don't want to, if you have 30% emulsion or 50% like in mayonnaise, I mean, it's just too turbid even for our method to access.
Any other questions? If not, let's thank Professor Stefan again.
Thank you.
So our next talk will kind of go into kind of the world of AI and machine learning. Obviously, there's a lot of kind of aspects going on in terms of utilizing AI and machine learning for various different applications in terms of formulations and other areas. So Kevin's going to give us an overview, I guess, of some of the very fundamentals, I guess, right, of AI and machine learning, assuming that basically people don't know much about AI and machine learning. I know there's a lot of people in the audience who actually do know quite a bit. So we'll kind of, so apologies for that because we're covering some fundamentals here, but I thought we'd just do like a light introduction into AI and machine learning and show some of the applications that we're doing. So Kevin is currently CTO at Fast Formulator, which is a startup that myself and Professor Yelena Yesha from the computer science department started earlier this year, well, earlier last year in January 2024. Kevin, your background is in a computational chemistry, but then going on into AI and machine learning, and kind of I guess computer science as well in that context. So again, thank you, Kevin, and I'll hand it over to you to kind of take us through that.
Sure. So hello, everyone. As Dr. Mead said, I'm Kevin Padron. I'm a machine learning engineer, and I'm the CTO at Fast Formulator. And today we're gonna go from fundamentals of AI and then the role of AI in chemistry in general and in formulation.
Can you try that again?
There we go. And just a quick introduction, because you might not be familiar with Fast Formulator. So Fast Formulator, here's the team behind it, and we're trying to revolutionize product development by combining AI and expert formulation science to really accelerate R&D and reduce costs across a whole slew of different industries, cosmetics, agro, and biopharma. And actually, we'll be launching our first product very soon, actually in mid-January. So just a little background of the company. Okay, so just a quick outline. I'm going to cover AI really from the fundamentals. We'll define what AI and machine learning are. Then I'll talk about its applications in chemistry and in formulation, and then some examples of what we've been working on at Fast Formulator. So I'll start with defining it. So AI is definitely not magic, but sometimes it can feel like it is. But AI has well-established roots in algorithms and mathematical principles. It's kind of like an intersection of a lot of different disciplines: computer science, probability theory, optimization. And to give it a nice definition, artificial intelligence is really just when an agent performs an action that us humans consider intelligent behavior. So an agent could be anything. It could be a computer. It could be a software that's running on a computer, a car, a robot, whatever it is. And intelligent behavior is really something that we agree upon is intelligent behavior. So something as simple as tic-tac-toe, little children can lose at tic-tac-toe, but two adults playing each other, they should always draw. Or if someone makes a mistake, it should be a win. So if you're going to get a computer program, an agent to do that, then it's intelligent behavior. And that's very simple, but much more complex things like driving a car. Maybe not so much in Miami. That's debatable if it's intelligent behavior, but this is really the core of it, right? When you get an agent to do some kind of behavior that we agree is intelligent. And the work behind AI really kind of started with Alan Turing, famous for the Turing test, which you've probably heard of. And that was really more conceptual. It was more formalized at the Dartmouth conference in 1956 with the big guys in AI, McCarthy, Shannon. And here's just an example of tic-tac-toe, how you would play tic-tac-toe. So to get AI to work with tic-tac-toe, all you have to do is take the current board state and see every single possibility from there. And for a human, you know, we can't do that. There's 9 spaces, 3 different options in each space, but for a computer, it's completely tractable. And once you have the entire state, well, you can go to the nodes and you could say, which one am I going to win and which one am I going to lose? And if the AI is coded properly, you would just follow down one of these promising paths, and it should always either draw or win. And if it does that, then it's intelligent behavior, right? So now let's move into what machine learning is. So machine learning is a subset of AI. It's still an agent doing intelligent behavior, but it's crucially different in the methodology of how you approach it. So how I just described the tic-tac-toe problem, you're integrating this algorithm. It's called the Minimax algorithm, actually, specifically for solving tic-tac-toe. You're gonna write all the rules down. If there's 3 in a row, you're gonna write down that whole process of constructing the tree. All of that stuff is written by the human using heuristics that us humans have figured out on how to play the game. When you're dealing with machine learning, where the human's not creating fixed rules, you're essentially designing a model, and that model is going to learn its own patterns from training data. So it's a very different paradigm where the model is more generalized and you're showing the model different examples of how you want it to, and it's going to construct its patterns of how you want it to reach its goal. And if you really want to go back, you could say that machine learning started with Gauss in the late 1700s doing linear regressions. I'm sure probably everyone in here has fit a line of best fit. That's technically machine learning. But probably a more appropriate origin would be Frank Rosenblatt's perceptron. So that's really the dawn of the neural network, and that's in the late 1950s. And that itself was based on work from McCulloch and Pitts, which they kind of defined the calculus behind an artificial neuron based on an actual neuron. And actually here is Frank Rosenblatt with his perceptron. The perceptron is not this, it's this massive cabinet behind him. And actually what's in front of him is the photosensor. And you can see it's trying to predict what letters in front of it. And it's incredible because this was implemented analog, and it's an incredible feat because there's no software in there. But this is all the way back in the late 1950s. And I have a quote here that I love. It's from the New York Times. It was published in 1958, and it says, "The embryo of an electronic computer," referring to the perceptron, "that the Navy expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence." So if you thought AI hype was a new thing, all the way back in the 50s, we were hyping this up as the incredible achievement. So let's think about how can a machine learn? So like I said, rather than programming the rules ourselves, we're going to have a more generalized model, and we're going to try to get it to solve a problem by picking up patterns that we show it with training data. And this is really an optimization problem. You're going to go through 2 phases. So the first phase is going to be the training phase. This is where you're going to have the model adapting its inner representation, learning from the data, picking up on the patterns. And then once you've met some kind of threshold and you say, my model is good enough, you're going to transition into the inference phase. And at that point, you're happy with your model and you go out into the real world and you can use your model on real world data. And in that case, there's no checking if it's correct or not. You're just hoping that you have a good way to infer these predictions. And really nowadays there's kind of 2 branches of machine learning. So There's the more classical machine learning that deals with kind of faster, smaller, simpler methods like regressions, decision trees, random forests. Support vector machines have kind of fallen out of favor, but in this regime, you're typically handling very nice structured data in tables, and some features, you're going to do feature engineering to get it nice and clean, and everything's going to work nicely. Deep learning is quite different. So deep learning it only uses neural networks. That's why actually it's called deep learning, because you're just going to have multiple stacks of neural networks on top of each other. And these architectures can get super deep and have tons of parameters in them. But that's where the name deep comes from deep neural networks. And it relies completely on neural networks. And typically this kind of data you're dealing with can be much more pliable. It could be unstructured data, text data, we all know, like ChatGPT and things like that, where the data is messy and it's not as clean in tables. And this is where my work is concentrated in and what we do at Fast Formulator. So I'll start talking about the actual training process itself. So the training process, the very first thing you need is data. And there's, the saying that everyone says, garbage in, garbage out. The data is probably the most important aspect of the entire pipeline. So when you're collecting data, it's important that you have high quality data, enough data. If you ask any machine learning engineer or data scientist, most of the time that they're spending is in collecting training data. And typically the problem that you're trying to solve is typically one of two things: regression or classification. There could be other things like clustering and other unsupervised things, but typically you're trying to solve either a regression where you're just predicting a number, some continuous value, like the stock price of Apple or the viscosity of a fluid. And then there's a classification where obviously you're trying to predict a class, right? Picking between, a picture if it's a dog or a cat. And then once you have sufficient training data, you can actually start training. And in this case, I'm going to talk about neural networks specifically. So this is completely an optimization problem. So you could think of a neural network as a mathematical equation. And your features in your data, whether it's things like height, weight, age, whatever your features are in your data, those are going to be variables in this equation, in this neural network equation. And what you're trying to do is you're trying to optimize the weights of this equation such that it gives good predictions based on the training data that you have. So your training data, you know what the output should be, right? And this becomes an optimization problem. And I say that it's a mathematical equation, but this is really happening in extremely high dimensional space. There's no nice clean formula that you can look at. And this could happen with billions and billions of neurons. And what you're doing during training is essentially calculating a loss. So I think I'm missing I'm missing a slide here, but essentially during training, what you're going to do is you're going to run the sample through your model, and it's going to run through all those weights, like I mentioned, and it's going to give a predicted value. And now you know what the value should be, so you calculate something called the loss, and that's essentially the error between what it predicted and what the truth is. And once you have this error, you actually go and back propagate through your network with something called gradient descent, very well-known, well-established optimization algorithm. And you will go back and change all those weights slightly, change all those weights. If it was incorrect, you're going to change them, to push the model to be more correct. And you're going to do this continually. You're going to give it one training sample, and it's going to change the weights a little bit. Give it another, change the weights, and it's going to continually change those weights until you reach some point that inner kind of representation, that inner kind of formula of this neural network reaches some point that you say that's an acceptable loss. And in many cases, you'll have a test set or some kind of metric that you're measuring to know that you've reached the point where you think that it's an acceptable model and those weights are generalizable. That's really the goal. So once you finish your training and you reach that point, you take your model and you take it out of this training mode, and now you go into the inference phase. And the hope is that you got sufficient data, high quality data, you trained it properly, you can go into the real world and apply this formula to anything. So you get the real data, you put it in, and the output you accept as the prediction. So unfortunately, I don't have my slide here. It's missing a piece, but yeah, the goal is really to generalize from this kind of small sample set of your training data to make a model that can generalize to the real world and to the real population. So here it is kind of visually. Here's the training process where you have your collected training data, and this will be nice and labeled. So if you have a picture of a car, it'll have a label of a car. And then this is how we represent neural networks. Actually, if you look at a single one of those green nodes with those connections to it, those would be the weights. A single one of those would actually be a perceptron, going back to Frank Rosenblatt. That'll be one perceptron. And actually, when you combine all of these perceptrons together, you get an MLP, or a multi-layer perceptron. So we still call it that all the way back from Frank Rosenblatt. That's another name for a neural network. And what happens is you're going to get your training data. In this case, it's images, and images are really nice because images are made of pixels, and pixels are just 3 numbers, red, green, blue. And those can feed into each one of these neurons. It'll run through the different weights, and it's gonna essentially, you're just gonna go through this equation, essentially, and it's going to make a prediction. In this case, it's correct, it's car, but you could imagine if it said dog, right? It's gonna be very incorrect. So you're gonna calculate some kind of error. In the case of categories, you have, cross entropy error. And once this error is calculated, you're gonna go backwards through a process called backpropagation. And you're going to change all of these interconnections. Those are weights in between the values. So all of those interconnections, you're going to slightly tweak them each. And essentially, it's called gradient descent. Without getting too far into it, you're going to take the gradient of the weights, and the gradient's going to tell you where you're going to move in the opposite direction. And you're going to go down into a lower loss, essentially. You want to navigate downwards towards the lower loss. That's gradient descent. And then you're going to keep doing this, and you're going to have, hopefully, a lot of training data to go through, and you're going to keep going and going through this loop as these weights in the middle change. And then again, when you're ready to do inference, all you're going to do is the forward, right? You don't know what the actual label is in the real world, so you take that as the prediction. So just to talk about some of the major fields in machine learning, computer vision is one of the original, big AI movements. So the convolutional neural network started in the 90s. It's still a major part of machine learning, a lot of the concentrations in computer vision. But nowadays, everyone is talking about NLP, or natural language processing. So definitely with the advent of large language models like ChatGPT, this is becoming major investment and major interest in this particular field. And then this is kind of somewhere out there. So robotics and autonomous agents, they use something called reinforcement learning. Reinforcement learning is a little bit different to what I explained. It's more so like a reward-based system where you're kind of helping the AI pick between exploration and exploitation. It's a different paradigm, but actually it was kind of falling off until recently. It could actually be used in NLP. If you've ever used ChatGPT and you see that little thumbs up and thumbs down, when you're clicking that, you are feeding data into the reinforcement learning of ChatGPT. It's called reinforcement learning with human feedback, and you're participating essentially in the study, right? Whenever you're using ChatGPT for free, you're definitely giving something back to OpenAI. So I've kept it here, and I've kind of pushed it back, but this is definitely the buzzword about AI is generative AI. Everyone's talking about it. Everyone wants to talk about it. And I guess I want to formally say what it is, define it first. So it's essentially whenever you have a model, in this case, this is deep neural networks. Okay, generative AI is very deep. I mean, extremely deep. You could think of hundreds of billions of parameters. We don't really know how big ChatGPT 4 is, but about 2 weeks ago, we had the biggest language model release so far, open language model, and it's about 678 billion parameters. So these are colossal. It needs a small data center to run. So these are hugely deep neural networks. But to define generative AI is identical to other AI, but the outputs resemble their inputs. That is the only way That's the only distinction. So in ChatGPT, your inputs are text, the output's text, it's generative. That's really all there is to it. And I can't talk about generative AI without mentioning large language models. And large language models are really interesting because they're able to solve problems that we could never solve before with traditional machine learning. It's incredible that they can do it because they're actually trained just to predict the next token. You can think of a token as the next word, and they're just trained to take in some text and predict the next word in the sentence. And incredibly, with just that simple bias, they can do incredible complex reasoning and generation. And its success is really owed to the model, the architecture that it's based on. It's the transformer model, which was built in 2017. And its success is almost all attributed to how well it scales. You can see the scaling is very evident in the companies that are doing the scaling. Google, Anthropic, OpenAI, they can scale these models, massively train on the entire internet as a corpus, and it pays off because the more compute you throw at it, the better they get. And this kind of complex reasoning is called, it's an emergent property, and it's called in-context learning. And it's incredible, really, because again, it's only predicting the next token. Actually, to go back on what I said, it's actually a classification problem. You're taking in the input is some kind of text, and then the model is actually predicting which token out of all the possible tokens is the most likely. So it's really a classification problem. You're classifying which is the most likely word. But from that incredibly simple bias, you get this emergent property called in-context learning, where you can actually steer the model to do things that it was never trained to do, right? ChatGPT was never trained to do a lot of the things that we ask it to do, like rewrite an email. It was never specifically told how to do that. It just emerges from this kind of in-context learning. So now I'm gonna switch gears now that we understand AI and machine learning to machine learning specifically in chemistry, and specifically the challenges that you face when doing machine learning in chemistry. So AI and machine learning have shown great promise in other fields. Maybe we see in NLP, certainly, imaging. So chemistry and formulation shouldn't be any different. Current solutions, computational solutions, are things like molecular dynamics, quantum mechanical modeling, things that I used to do a long time ago. And these are very slow physics-based simulations. So, to get a couple nanoseconds on a molecular dynamics simulation, it's going to take a month. So they're very slow, brute force, calculating a bunch of trajectories and just going through each atom and moving them. So it's extremely slow. And machine learning has immense potential to kind of disrupt this, because machine learning in that two-phase approach, when you're doing the training, that's where you're going to spend a lot of the time and effort. But once it's trained, predictions are fast, very fast. So it has this kind of, you kind of invest at a different point in time, and now you can use that model elsewhere very quickly. And not only can it speed up these kind of predictions, it can do predictions that are just not even possible with physics-based, like molecular dynamics can only go so far. You can't really do large macro scale experiments to predict things like viscosity and things. So here's some of the things that you can do with machine learning. So obviously property prediction, I'm going to talk a lot about this. So the predicting physiochemical properties like surface tension and viscosity. And then there's the idea of optimization. So if you're able to predict that, can you optimize with other external variables, things like sustainability or cost or logistics? And then there's the very interesting kind of cross-section with automation, where maybe can you apply AI to improve high throughput? So the biggest challenge in doing machine learning in chemistry is, without a doubt, the training data. So in other fields, there's tons of training data. If you look at text, you have massive corpuses like Red Pajama, The Pile, Fine Web. These are massive corpuses, hundreds of terabytes worth of text that you can use to train. In images, there's tons of images. There's Lion 5B, which is 5 billion different images. But when you look at chemistry, there are extremely limited, actually publicly available data sets. And, you know, there's a lot of factors that go into that. Experiments are inherently slow and they're labor intensive. And if a company wants to conduct research, and they typically don't want to share because of that, you know, that intensity and the cost that goes into it. But if you want to do machine learning in chemistry, there's no way around it. You need high quality data and you need a lot of it. So actually at Fast Formulator, we solve this by just collecting the data. So we have a lab with formulators and they're painstakingly collecting the data ourselves and building up an internal database. And actually working connected with a lab is very, very beneficial. We always know what the format of the data is going to be. We can do changes to the data, so very beneficial there. And another thing is not only when you're training the data, like from our side, is when you're going to say a customer or user is trying to train data, we're trying to do smart formulation. We're trying to cut down on the amount of experiments that have to be done. So you want the actual user to conduct less experiments. And we do this actually doing something called fine tuning. So I mentioned that there was two phases. There's the training phase and the inference phase. But actually, once you're doing inference, you can actually just go back and train the model a little more. There's nothing stopping you from changing the weights. And here, there's something called transfer learning, which is immensely useful here. So transfer learning, it's kind of really big with images. When you can have a model that's trained on just random images of whatever, dogs, cats, trains, planes. You can actually use that network, put it back into training mode, and then fine tune it on something way out there, chest x-rays or COVID, whatever it is. And it turns out that if you do this, first of all, you need a lot less data. And in domains like chemistry, medical, you don't have a lot of data. And another thing is that it just works much better. And it's because of this idea of transfer learning. So when you're training on other unrelated images, the model itself is learning inherent properties. It's learning how to look at an image, how to understand how it's working. And in the context of our models at Fast Formulator, we're working with, molecular data. It's understanding what the underlying chemistry is, even though it might not have the full, view. Once you give it whatever you're trying to fine tune on, say it's a new component that a customer is bringing, it already has this inherent knowledge in it of just general chemistry. So it requires a lot less data and it becomes a lot faster to do this kind of fine tuning and transfer the learning that's already been done by our, what you call foundational models that we've already trained. And this is just kind of like the loop that we use. So it all starts with obviously the data collection and then creating the model. But very importantly, you have to validate this model. And we do that with experimental validation and making sure that the model is giving correct outputs. And based on that output, you can kind of steer the next phase of data collection, right? What is doing well, what's not doing well, what needs to be more represented in the data. So this loop helps in reducing the overall data requirements of training the model. So specifically, I'm going to talk about actually modeling in chemistry. So images and text, they have really nice, efficient, well-structured representations, right? Images are just pixels and pixels are just RGB values, just numbers. Text, you can just assign words different numbers. That's really what tokenization is. You can do it character level, word level, byte pair encodings. And the problem with chemistry is that there's immensely different ways to represent structure. And the big thing is that different molecules can have very different structures, right? You can have a polymer that's massive, long, lots of cross-linking, or you can have a tiny little molecule. You can have salt, right? NaCl is a tiny little thing. And when you're doing machine learning, to train efficiently, you need to have consistent inputs. It's just a requirement of doing machine learning. You're doing matrix multiplications. You need to have everything in consistent, nice sizes. So the common solution to this historically in machine learning in chemistry is to use simple heuristics, things like cheminformatics, where you're doing, fingerprints of molecules, how many valence electrons, double bonds, things like that. But that doesn't really give you a full picture of the actual molecule and the structure that's in there. So more modern approaches are things like encoders and embeddings. And that's what we work on. It's our molecular encodings. And this actually uses the deep neural networks themselves to come up with a representation for these variably sized molecules and put them in a nice latent compressed input that we can use in any other model. And one other thing when you're modeling chemistry is the problem of the black box of neural networks. Like I said, these could be huge models, billions of parameters, and there's really no way to understand fully what's going on there. Actually, this is a very hot topic for LLMs. It's called mechanistic interpretability, trying to figure out what's happening inside those neural networks. But the best you can do, and what we do, is try to give the model a full understanding and train the model how we would think is the best way to train it. So one thing is physical priors, in addition to giving it the actual structure, right? So it's actually working on that structure, but you can give it physical priors that is kind of the whole formulation environment, things like the pH, the concentrations of salt, all these things that describe the environment. And of course, the best solution to the black box is just testing it experimentally, right? You can just go ahead and actually test that the model is working correctly and do that often and well enough. And that's how really we combat that issue. So now I'll talk a little bit more specifically to formulation itself. So what we're trying to do is smart formulation, right? So using AI models, can we cut down on these large, expensive DOEs and do formulation much more efficiently and effectively? So one thing is like I said before, we rely on this transfer learning. So we build what are called foundational models. And these foundational models are for predicting, again, I'm missing a slide here, but yeah, okay. But these foundational models are based to do physiochemical property prediction. So things like surface tension, viscosity, things that like stability and foaming, these are our foundational core models, right? So these are trained on this data that we collect, painstakingly collect, and this internal database. And using this, we can empower smart formulation, right? So if you're able to predict those properties, those properties really control a lot of the downstream properties. So external properties like sedimentation, extrusion, chewing, spreading, these kind of properties are all controlled by those underlying physiochemical properties. So if you can predict those, you can optimize for these further downstream properties. And doing this is with machine learning, you have the major speed increase, right? Like I mentioned, it's a lot faster than any kind of slow simulation. So you can survey a massive search space, right? You can have input parameters and it can search through hundreds of different formulations. And this can give the formulator an idea of what regions of that space are, what is going to be more optimized for those key targets. If you're looking at this area, this is more promising. If you're looking at this area, these are not going to be stable, things like that. And it can really allow a formulator to cut down on all these, all the experiments that they'll have to do. And here are some of the kind of predictions of these foundational models that we have. So in this case, this is a rheology model, and this is for a surfactant system. And the colors are kind of hard to see here, but the model inputs are, like I mentioned, from our molecular encoder. You're going to have the actual structure, and then you're going to have component concentrations, how much of those components are in there. And then things about the formulation environment, right? Your pH, your salt, any kind of things related to that environment. And then of course the shear rate here, because we're predicting our shear viscosity. And this is going back, this is a regression, right? We're trying to predict a continuous value. So all you're going to do is a regression on this data. And you can see here our predicted values in red here. It's hard to see, but predicted versus actual. And here you can get that thinning and Newtonian behavior. And once you can predict this rheology and all these physiochemical properties, like I said, you can use that to optimize for downstream properties, things like spreading, mixing, sedimentation. They all come back to this kind of, very fundamental properties. And here, this is foaming. In this case, we're predicting foam volume as a function of time. So again, a lot of the similar inputs, you have your molecular structure, formulation environment. In this case, this is a time series, so you're going to have your time step. And again, we're doing a regression. We're predicting volume, so this is a regression model, and we're going to predict it as a function of time. And you can see here the actual versus predicted as the foam goes down over time. And just to kind of wrap up here with some future applications of AI machine learning. So generative AI, like I mentioned, it can solve problems that was previously completely unsolvable with old machine learning, classical machine learning. And there's a lot of things specifically in chemistry and formulation that are a lot of textual data and unstructured data, specifically when you're talking about compliance and reports, and a lot of these things that regular machine learning would really struggle with. This is where generative AI is really good at handling this kind of unstructured data. And not only can it handle this new kind of modality, it can also, like I said, it has these emergent properties like in context learning. So it can actually work to do other things that you would never imagine to do with classical AI, stuff like more business and logistic related, things like optimizing inventory, logistics, even sustainability targets and things like that for increasing efficiency at the company scale. This is another potentially massive use of generative AI that's really impossible to do with classical AI. And then one more thing, which is really neat. So this is kind of the intersection between everything. So if you have a generative AI that really understands the problem and it has this kind of ability to do this emergent behavior, this in context learning, and you have property prediction models like our foundational models at Fast Formulator, can you combine them on a robotics platform to do really end-to-end automation that's much smarter, right? Have the actual platform, instead of going through X amount of formulations, can it actually use the AI to guide that experimental design and do it in a much more efficient and effective manner? And this could have a immense potential to revolutionize high throughput automation. And yep, that's it for me.
Yeah, quite a lot of time. It's a bit early, so I don't know if there's any questions. There's a couple, yeah.
So, talking from the chemistry and the formulation side, does your number of percentages change with your molecular studies or change number their concentration?
Yeah, so you can't kind of change the architecture on live like that, right? Once you pick the size of the network and you pick your model at the beginning. And there's a lot of work that goes into that actually to do it, because if you have a massive model, it's going to take forever to train. And if it's too small, it doesn't have the ability to properly model. So you do that in the beginning, you kind of, and when you're talking about these variably sized inputs, it's very hard to actually fit that into a neural network because they are a fixed size. So you can't change that. So during training, it's fixed, and it's quite a challenge to get that to kind of output nice fixed values for you that you can use later on in the chain. What do you, can you say that again? Oh, right. So retrieval augmented generation. Yeah. So that's a way of kind of supplementing the model to reduce its kind of hallucination. This is all large language models. And essentially what you're doing is pulling in data that you know is correct, right, from sources and putting it in the context window of the model. And RAG is, like you said, Perplexity, they do it very well. And it's a way of kind of mitigating the model hallucinating, right? Because you're giving it the, real data that you know is from some corpus that you trust. So yeah, the retrieval augmentation is different. That's completely generative. That's something new that's arisen with these language models specifically. Although you can do RAG now with images and things like that. But yeah, it's a different paradigm.
Thank you very much. Putting into online for people that for example, how classical data to
So the molecular encoder, the idea is really, you have to take this input, this variable size input, and the input is the molecular structure itself. So there's a lot of ways to represent molecular structures. The easiest and the nicest way to do it computationally is SMILE strings, right? These are just kind of ASCII representations of molecules. And then the actual code behind it, I can't really get into, the nitty gritty of what we do, but it's essentially, can you convert stepwise downwards from this molecule into one solid representation of a molecule, right? And this is a fixed size representation that you can use later on. So if it's, compress it down to a small tensor or vector of values that is generalizable to different molecules, like you said, you can have very different things, massive polymers, very tiny, just water. So it's a big challenge, and it's certainly it's, a lot of the success that we've had with the modeling is attributed to that.
Yeah, David.
So giving a C as a simple example. For a car, driving a car, there is no rule that says you cannot ride in reverse from the means there are certain things that are divided that are bound by direction. In case of chemistry, there are stereochemistry and stereochemical bases, for which chemical reactions, certain chemical reactions are formed. Also molecular phase products. Situation like that, how to train on one? You don't have now data. But in recent years, they have down prediction of molecular reactions that are happening. Speed of for it, things like that. So how to predict for molecular forbidden reactions? You need a certain reaction, certain stereochemistry.
So really, the training is on collected data, is on experimental data. So since we have that experimental data, that is essentially the bias that we work with, right? So it's whatever is collected experimentally is what the model is picking up all its patterns from. So that's really the way to combat that issue. And you talk about stereochemistry, that's also something that's handled in the molecular encoder as well, is so that the model has a full understanding of the actual molecules that are going in.
So, just a comment, maybe you can say something about that. It seems like you have experimental data and you're taking all this information, training model. You don't really know the physics, you don't really need to know the physics or the chemistry or the basic principles of the physical, right? Is that true? You don't need to know the physics to get complete because everything is data. Even if your physics or chemistry is very complicated, you don't need to understand as long as your experiment provides you, let's say, reasonable.
Can I take that a little bit as well?
Sure.
Yeah, so one aspect of that is that primarily the way we are doing experiments is very well designed DOEs, because like if you're looking at surfactant self-assembly, and trying to understand kind of where you kind of get to high viscosities due to kind of a certain microstructure of the system. The way we are training the model is actually kind of doing the experiments to kind of take that into account in a sense. So although it's kind of not taking the actual physics, but the experiments are based on the physics. So I don't know if that makes sense, but the thing is that because if we don't base it on the physics, we kind of get larger errors, because the problem is we don't have that much data still, right? So it's impossible to kind of collect for all the different types of combinations of materials that you have out there, which are used in industry. It's extremely hard to collect all of those in different combinations and permutations, right? So you have to have a limitation of that. So the way we're training it is based on very well-defined DOEs, where basically, for example, we know like this combination of an anionic and a surfactant with a zwitterionic at a certain salt concentration usually kind of does this sort of a behavior, right? So and this is also synergistic. So we use that principles to do the experiments which train the models in a sense. So in a sense we are capturing it just because it helps us predict better at that stage, because we see that because we put the chemical structure inside the encoder, as we change from one anionic surfactant to another or to another, it starts to pick up those trends to an extent, and then we do that validation as well. So there is an aspect of it which is underpinning it in that context. If that makes sense. Other questions? It's not, we are running a bit early, but I mean, if you're okay. Yeah. A break, yeah, maybe that's probably a good idea, yeah. So let's take like what, 5 or 10 minutes?
Back at, 2:55.
Okay, 2:55. Let's take 10 minutes then. Thank you so much, Kevin. That is good. Appreciate it. I actually in the morning, I looked at it and I was, oh no, because it's not actually, I think it's not quite, it's not quite. I'm very certain. Oh, okay.
Okay, I'll do it again. So let's get back to our tutorial, the third tutorial, and it's going to be given by Dean Pratim Biswas, who has been working on aerosol science and technology for many, many decades. And as he always said, if you wanted to do good aerosol technology, you have to have a good fundamentals. So that's what he's going to focus on. So let's welcome Professor Pratim Biswas.
Oh, great. So I think we can all relax. You all are already listening to, let's speak here, maybe listening to advanced topics. So mine is very straightforward, but I'm going to just zoom by as if it's teaching a full aerosol class, but it's going to be very basic materials, right? And hopefully you can relate to it from what I learned from the program. And also the earlier talk on light scattering is interaction of light with particles, but I'm going to take a step backward, just tell you what a particle is, how it behaves, and some of the dynamic behavior with these, right? So very basic tutorial. So just sit back, relax, stop me anytime you have a question. And maybe occasionally I'll ask you a question because this is simple stuff. Okay, great. Let's go. This one? I can just use this.
Try one more time.
Okay, so as I said, I'll tell you what is an aerosol, life cycle of a particle, right? All the way from where does it come from, and then what it does once we have a particle. I'll talk in a little more detail about nucleation. And then once we have a particle, does it move around, right? And just some very basic concepts. And you'll see that, of course, you've heard a lot of particle size, and you might have heard of concentration, but we'll also see that transport is very size dependent. And then, of course, if the size changes, right, particles are going to interact with each other once they are formed, and then try to put everything together. And just referring to the previous talk on machine learning, I'll also try to throw that in and say that we need that to solve these complex equations, okay? And the student is here, Onochi, who did that work, so he can relate to it. Of course, just a very quick run through, so you have to get into depth. These are classic textbooks that, of course, those who are students and have taken a class have encountered these. We took some of, I've been also teaching this class for many, many years now. You know, the gray hair begins to show. But we also have some of these in an online modality, right? And whenever we talk about aerosols, particles, there's a lot of equations we have to deal with. So this is actually done on a smart board, so you can follow all the derivations. And then Yang Wang, who's one of the main coordinators of this workshop, we put together a nice book with problems. So that is, we gave it a nice title. And if anyone wants to really solve problems, we of course pose the problem, but also provide the solution. Okay, so let's say you already know this, so I'm not going to talk about it. Of course, you go outside, you see a nice spray of sea salt here. The students love to hang out on the beach, but sometimes you go further out and they might say, oh, aerosols are stuff that comes from a spray can. You already know it's a lot more than that. Some particles are good, some are bad, some are really ugly. So that makes it more important to really study this. And by understanding these basics, you can really, this is a sort of a different discipline by itself. You know, we talk of chemical engineering, mechanical engineering, or diving in fluid mechanics, and so forth. But this is really putting everything together, and it makes it very interesting, and is often referred to as an enabler. And tomorrow you might get a dose of some of the applications of particles and so forth, right? In fact, I'll give a talk on nanoparticle synthesis plugged in a hole in the program. So I look forward to that. Today, go back to basics, but it really helps solve some of these challenging problems. We, of course, came off one. COVID was an entirely aerosol problem. If the aerosol scientists had, I blame ourselves here, aerosol scientists had stepped more vocally forward, so many people wouldn't have died. You know, the end point is just very drastic in this case, but there are many problems related to energy, climate, environment that we face today, and they could be tackled by these. So I'm going to go back to basics. I want to define what a particle is. And you heard a lot of these building blocks. To me, a particle is just a stable cluster of molecules, right? So it's made up of molecules. I can look at a dust particle floating around. We can't see it here, or a water droplet coming from the bay here, or a sand particle coming from the beach. It is a cluster of molecules. The molecules could all be similar in nature. If it's a pure water droplet, it's water molecules. It could be atoms if I'm looking at carbonaceous particles, or a carbon particle, for example. So that's why molecules are atoms. I'm not going to break down further. In the previous talk, the light scattering talk, you heard about polarization and dipoles. Those are the electronic structure, right? Obviously, molecules are made up of those things, but in this simple aerosol physics dive in, we are just going to stop at molecules and atoms. So particle is a stable cluster of molecules, okay? Simple. I say that because it's very different from the molecule, because here we have what we refer to as gases or vapors, and a lot of molecules floating around, which are not a stable cluster. And classic example could be oxygen. All of you are, I'm getting excited as I talk about my favorite subject. So I breathe in more oxygen molecules, or I retain more oxygen. I breathe in oxygen and nitrogen that is present here. So that is a molecule. So let's differentiate it from a stable cluster, meaning a number of molecules sort of hanging on together. And I could, of course, have water vapor in this room. There are water vapor molecules, right? We are close to a humid environment, the bay. So the moisture might be floating around in this room. Though we are indoors, we might treat the air, but still there's water molecules floating around. Those are molecules. But I could also have water droplets, right? I just came from up north, and they had droplets which had really frozen up and coming down as snowflakes and things like that. So that is a stable cluster. I would refer to that as a particle, and of course suspended as an aerosol. So it can just be a particle on a surface. It could be suspended in this room as an aerosol, or it could be a colloid. We saw a lot about colloids and measurement earlier on, right? And then, of course, you always like to show pictures. Basketball, this is football season. I should have drawn a football. In fact, flying back from New York today, the entire plane was filled with Penn State supporters. By the way, Penn State plays, anyone know? Who do they play here in Miami? Notre Dame. So are you rooting for Notre Dame or Penn State? Notre Dame. Okay, I was filled with the Penn State crowd, so I had to, play along with them. But so that when I toss a football, it's a stable cluster of some molecules, multiple types of molecules. I could refer to it in flight also as an aerosol, right? But definitely a particle. And then you could have a spray of liquid droplets. You have this black smoke coming out of trucks. And you heard about colloids and light scattering. So these could be anywhere. It could be sitting on a surface also, right? So if I look at this surface, there might be dust particles. So we are very clear on it. So now I want to follow the life cycle of this particle. And this is multi-scale physics, chemistry, transport, deposition. So very simple stuff. If it a particle is a stable cluster of molecules, I'm going to start with molecules. Now you could take a big rock and break it up into smaller particles too. That's not exciting, you know, mechanical stuff. Let's start with molecules and really create the cluster, okay? And you can look at water vapor. So water vapor in this room, I can begin to cluster them and create stable clusters by just cooling down this room, right? And we'll see that in a little more detail. So cluster formation and growth is extremely important. That is literally the birth, moving from a molecular state to a particle state. And by understanding this, I can then utilize this knowledge to make functional particles, right? Not all particles are bad or naturally occurring like I've been referring to. I could intentionally make particles, and tomorrow you'll hear a lot more about it. Once these particles are created, they begin to move. You also heard particles move around, Brownian motion. And when they are moving around, they can collide with each other, and they could stick and become a larger particle, or two particles could collide, stick, and become one particle. So you see the size is changing, the concentrations may be changing, and they could be multi-component. I'm going to keep things very simple while I talk about it. I'm going to just refer to single components, right? The simple physics. And then they move about. I might want to capture them. I might want to deposit them. And there's a whole bunch of like diffusion, convective diffusion. Someone asked what happens if I'm flowing particles in a system, can I still measure them? Sometimes these things move slowly. I want to move them faster. Like you hit a baseball with a bat that is applying a force. I can apply an external force field, right? So electrical force fields, for example, and move things around. So in terms of motion, so I'm showing you this image here. These are molecules now, okay? They look like particles, but let's call them molecules. Of course, my scale goes haywire. I can't see small particles. I definitely cannot see molecules. But let's say these are molecules. They all look like the same kind. Even in this room, I have oxygen, nitrogen. But let's just assume these are molecules. The most important thing is molecules are doing a dance, right? They're constantly moving unless I'm at 0 degrees Kelvin. And I'm not going to go into those domains, though it's very interesting to also see what happens. And then I have a stable cluster. And intentionally, I've said it's made up of red molecules. It could be made up of these blue things too. For example, these could be water vapor molecules clustered together, but let's just differentiate it, right? So one clear thing that happens is these molecules are bombarding this particle. It's floating around here. And as was said, that causes it to move. It moves randomly, and that is diffusion, okay? So, and then, of course, I want these to deposit, and I want to grow structures. I can grow very fascinating structures, which can then be put to good uses, like semiconductors. We hear a lot about semiconductor physics now, and chips and so forth. We heard about AI, machine learning, those big data centers that we need to, you know, churn out all the data. All the way back, we might use a particle process or an aerosol process to even make thin films of semiconductors, and which would operate fast. The cell phone is getting smaller and smaller, but we are making it more and more powerful, right? So these are all basically particle processes. So let's now dive in a little more in detail and talk about birth of a particle. By that, I simply mean initially I have only molecules, and now I'm forming a stable cluster. And I want to understand this. And this I'll call aerosol formation, or the process of nucleation. I'm just going to use classical theories and discuss this. So we want to understand. So there is a critical size, depending on what molecule I choose. Not like two molecules are not going to necessarily form a stable cluster. They could, but maybe it doesn't. So there is a critical size beyond which the cluster will be stable, right? This comes from classical thermodynamics, and that's what I'll look at now in terms of a simple derivation. So let's say I have NT molecules of pure vapor. Assume it's water vapor molecules floating around. And then some of these cluster together, G molecules, G of these molecules cluster and form a single cluster. So I still have remnant molecules. Obviously, G is less than NT. So NT minus G remains in the vapor state. Okay, so I show this initially molecules, NT molecules, right? Remember, they're doing their dance. They're moving around. I'm not showing it here. And they could collide with each other, but break apart. They're not forming a stable cluster. But now I'm saying, let me form a stable cluster containing G molecules. And of course, then you bring in the Gibbs free energy. These are thermodynamic properties of this system. So I can do a simple balance or evaluate the change in the total Gibbs free energy of the system, which is just G final minus G initial. My initial state is just the pure vapor, right? That was the assumption, only molecules. And the final state is an embryo or a stable cluster plus remnant vapor, because many of the molecules are going to remain in the vapor state. And now you start plugging in relationships, NT minus G. So G sub V is the specific Gibbs free energy for the vapor, G sub L for the liquid, and you basically write a balance. But when I create a cluster, I also have surface energies holding this cluster together. And that macroscopically can be explained by the surface tension, 4 pi r squared sigma. Sigma is the surface tension, right? So, and then you do some simple algebras, rearrange terms. G, the cluster containing G molecules is related to the particle radius, assuming it's a nice sphere. Just the volume of the particle divided by the volume of a molecule, right? That is G, the number of molecules in the cluster. And then some more algebra you can follow through here. I'm just substituting. It's very straightforward. And then I have a relationship for the specific free energy. I'm keeping the temperature constant using the ideal gas law, and I get some more relationships, and I define something called a saturation ratio as a ratio of the vapor pressure to the saturation pressure, okay? And if I plot this now, so I'm going to plot the free energy change of the system as a function of this radius of the cluster that I'm forming, right? So if there are two terms now, you can see the first term and the second term. If the first term is greater than 0 and the second term is greater than 0, the net is that the free and if S is less than 1, you can look at this relationship. If S is less than 1, the saturation ratio, the first term is also positive. So the Gibbs free energy change keeps on increasing. So I don't have any semblance of a minimization of the Gibbs free energy, which will create that stable cluster. But when S is greater than 1, I don't have a minima, but I do have a maxima in the free energy curve, as we can see, and it's a metastable state. So, and that defines the critical size. So RP star is the critical size. If I'm smaller than that, the cluster breaks apart. If I'm bigger than that, larger than that, the cluster keeps growing. Okay, so that defines this critical size. And you can see the critical size, it's a very simple relationship, depends on the surface tension and the saturation ratio. And one can dive in and again, look at these and you can get expressions and so forth. So this is basically defining birth of a particle, what will be the size, the minimum size at which it will be stable. And beyond that, also it will be stable. And I can do calculations for water, plug in values. It's always good to play with numbers, right? So if the saturation ratio is just 1, which means I'm just equal to the vapor pressure, I'm never going to form stable clusters as per the classical nucleation theory. But the minute it exceeds 1, like if it's 2, you can see that I have a certain critical size. As the saturation ratio gets larger and larger, the critical size becomes smaller. And that's when I can take this out to the atmosphere now. I can go up. If the saturation ratio goes up as the vapor moves up, I begin to form cloud droplets. If the cloud droplets grow and become large, they'll come crashing down as rain or maybe as snow, as I referred to. And of course, you can do these calculations at different temperatures and so forth. So very simple stuff, but gives you a good idea. Okay, so that's all I'm going to talk about it. But there is a rate at which these droplets or particles are being formed. I can also derive it. Of course, I've just written the final result because, as I said, it's a 45-minute lecture. So we want to cover a lot more terms. We want to go beyond just the birth. So it's the rate at which I form new particles per unit volume, per unit time. And of course, it's a longish looking expression. It depends on the number of monomers I have. For example, in this room, I could fill in a lot more water molecules. Then the rate of nucleation would be much higher because I have more molecules, and that qualitatively makes sense and so forth. And it depends on the surface tension, the molecular volume, and things like that. Okay, so these are just some simple parameters. Okay, so particles can be different sizes, just even by the critical size, right? I have a smallest size, but it's not the same for water and maybe for some other material that I want to nucleate, or if I have some sulfuric acid in the atmosphere, in a contaminated atmosphere, or if I have some salt dissolved in the water, I'm going to get different critical sizes. So that tells me that particles can be of different sizes, right? And we've already heard about this. There are many other reasons why we have them. Now that we have these particles, let's go again into basics. So N is just the number concentration. So I take a unit volume, let's say 1 meter cube. I can choose 1 centimeter cube. You can imagine a centimeter cube, and I can sit and count all the particles. That gives me the number concentration. I want to know the total number concentration. It's also number per unit volume, but I add up all the concentrations to get a total number concentration, right? And dP, I'm going to assume things are spherical, so use a single dimension. Not everything is spherical, and I'll point that out in a second too. But let's assume that I can use diameter, a single dimension, to denote a particle size. But then I have a size distribution function, and we want to really become mathematical now. Of course, the derivative has to exist. The derivative of the number concentration with respect to size, I refer to as a size distribution function. And there are reasons why we do this, because we want to get more and more complex, as you'll soon see, even going through this simple tutorial. We want to use these mathematical forms. So the total number concentration is just the integral of the size distribution function with respect to particle size. That just comes from the definition. And I choose 0 to infinity just mathematically. There is no 0, obviously. Remember the critical size. So the smallest size should be the critical size. Infinity just denotes that I want to go to all particle sizes to get a total number concentration, right? But mathematically, we can use 0 to infinity. But I might be interested in a mass concentration, not just the number concentration. If I'm making a catalyst, if you heard about fast formulator, they want to make some polymer. Maybe I want to get a certain mass of it. I just don't want to sit and count my particles. A mass concentration up to a size X. If it's spherical, of course, I just multiply by the volume of a single particle, by its density, and integrate out. And I want to get particles only up to a size X. I'm not interested in the larger ones, let's say. So I define something called a PM, particulate matter concentration, up to a size X. And having a size distribution function allows me to simply integrate out from 0 to x, okay? And PM, by the way, you might hear about it in the later presentations tomorrow and day after, but I'm just showing you first, before that, a sketch of a size distribution. I go outside and measure it. There are some coarse particles. I talked about sand particles. They might be floating around, but they're on the larger side, right? Whereas if I form very small particles from a molecule to stable cluster formation process, I might have ultrafine particles, or a truck goes by and emits these small combustion-based particles, and you have, a complex distribution with peaks and valleys and so forth. We give them names: ultrafine, fine, coarse, super coarse, and things like that, right? So one has to know that. I can plot a number distribution and change it to a mass concentration distribution or a surface area. So if I'm intentionally preparing a catalyst, I might be interested in the surface area concentration. I don't care for the number nor the mass. I might want to know the surface area because that's where the particle action takes place, or the chemistry takes place, and so forth. So we can plot surface area distributions and so forth. Okay, not everything is spherical. You can see I'm just jumping from topic to topic and keeping it rather brief in some sense. Each of these one could go into detail. Not all particles are spherical. There are geometric concepts like fractal concepts that I can use. I define the center of mass of the structure, and then I can fit a curve to get something called a fractal dimension. And I use that to represent my agglomerated structure and so forth. Then what is the particle made of, right? The chemical composition. We heard this also in the earlier talk. I've not even gone into that. The elemental composition, it's not necessarily it's a pure water droplet or a pure salt droplet. There could be organic, inorganic species mixed up. I could have a size-dependent composition, and these are extremely important when I'm looking at air quality or climate issues. Why is climate change so complex to predict? It's because of some of these particles and the complex compositions which impact the energy balance. Nanoparticle technology, I might intentionally want to produce functional nanomaterials by adding dopants and things like that, and all kinds of applications. So this is another very important topic. And then particles can be alive. We talked about, I mentioned COVID, but there's bacteria, there's viruses, DNA, protein fragments, and some of these are not good for us. Some could be good, like protein fragments or pollen, for example, but these are just actual sketches of particles. Many of these are airborne, like influenza virus would be airborne and spread the flu, right? We, of course, take flu shots and things like that. Anthrax we had heard about, and so forth. And of course, the SARS-CoV-2 virus, which caused a lot of havoc, was also an airborne particle. Okay, so that was birth of a particle, maybe size distribution, enough to say that we would have a distribution with complexity of chemical composition, maybe even biological, if I want to understand the biological nature. And again, you'll hear topics or lectures on these in the next 2 days. Let's now see, we have these particles. I'm saying these particles don't sit stationary. You already heard about Brownian diffusion. They're always on the move, right? So, but to really understand that, I'm bringing this picture back. Molecules are now differentiated from my particle. This has probably sunk in now. Particle is a stable cluster, but there are a lot of singlet molecules or non-clustered molecules. A gas is a good example. In this room, oxygen, nitrogen, doing their dance, right? And I want to be quantitative to understand this. So these molecules are moving very rapidly. It depends on the temperature. I told you at 0 Kelvin, they stop moving, but 0 Kelvin is really cold. Complain about New York temperatures or up north. Some of you are coming from there. Miami is nice and warm, but at room temperature, it could be as large as 300 to 400 meters per second. We also, as scientists, really need to have a good handle on numbers. Is this a large number? Yes, it moves very fast. Of course, my leg is injured now. I had surgery, but I would still move at 1 meter per second, right? And of course, there are people who run very fast. They would do 100 meters in 10 seconds or less, 10 meters per second. Look at this, 300 meters per second in this room. You can't see them. They're just zipping by, and they move randomly. Because once they're zipping on, they hit another molecule, change direction. So the motion is random. And this is sort of, and I mentioned this already. So do particles move? These particles are bombarded by these molecules. So remember simple Newton's law. If there is a force acting on something, it's going to start experiencing that force and move, right? That's his one of his initial laws. So particles start moving, and that is Brownian diffusion. Molecules move randomly, strike a particle, and they cause the particle to start moving randomly. Particle is much bigger than the molecule because it's a cluster of molecules, so they would move slower. They won't be zipping around that fast, but they are moving around. Smaller the particle, faster they move. And this is describing diffusive behavior. Okay, so particles move slower because we just said they're heavier and so forth. Okay, so I'm not going to talk about all of this. As I said, one has to go on. But whenever a particle is moving, it experiences a retarding force because it's in the bed of gaseous molecules. So there's a drag on it. It's just like if I want to start running fast, I'm going to be held back because the fluid sort of imposes a drag on myself that is moving. Same way with the particle. And just the concept of drag is a fabulous concept. I design instruments based on that. I do a lot of things, so I'm going to talk a little about it. And then someone asked in the earlier class, I want to flow particles. Yes, that is convective diffusion. I'm not even going to get into that. And then external force fields. I want to move them around. I want to trap them. These forces may not be enough, so I want to use electrical forces to trap them. Any industrial system, combustion system, at least in the United States, we have something called an electrostatic precipitator. I see folks, colleagues from TSI here, they design instruments based on electrical forces. So you'll hear more about these later on, okay? So I'm not going to get into that, but just talk about some simple concepts. Particles move. How did I calculate that 300 meters per second? Of course, we can even measure them, but it's a simple formula. Depends on, it comes from the kinetic theory of gases. Higher the temperature, faster it moves. Heavier the molecule, slower it moves, right? This is qualitatively also very clear, but look at these numbers. As I said, they're pretty large. But as the molecule is moving, it moves a certain distance before it collides with another molecule. And this concept is extremely important in defining particle behavior. And we call this the mean free path of the gas. It's the average distance a molecule moves. One can calculate it, derive expressions. I'll sort of brush by and give you the final relationship. And you want to relate it to macroscopic properties, but there's something known as a Knudsen number, which relates, is the ratio of the mean free path to the particle size, right? That is the number that really is going to characterize motion, and particles are of different sizes. So all the way from the continuum, my baseball or my basketball is a large particle, right? The Knudsen number is very small, so I can use continuum physics. On the other hand, small particles in the nanometer sizes are in the free molecular regime. they are acting like a molecule themselves. They're that small. A molecule typically is 0.1 nanometers in size, just to put it in perspective, but it is with respect to that average distance moved, not the size of the molecule. And then there's a transition regime, and the transport depends on this kind of property. Now, maybe my first question, who's this dude? Whose picture is this? Those who know should pass, who have taken my class. Who's this fellow? He has long hair, of course, so he dates. None of us, I see, have very long hair, though some of us tend to grow our hair long. But this fellow was a British scientist. There's a hint. No one? First aerosol scientist. She knows because she took my class. Isaac Newton, who was a mathematician. He was an aerosol physicist, fabulous guy. And he sat and he used to watch apples fall and he used to watch things move about in the sky. And he proposed an expression for this drag force just by observation. You talk of machine learning, you talk of artificial intelligence. This is observational intelligence. And an expression that he derived in 1600s is still valid today. And there was a big gap. Stokes was a fluid mechanics expert. You can imagine the drag comes about because of the interaction with the fluid, right? Let's just put it that way, or the molecules in the fluid. It took 200 years, I think, close to 200 years for Stokes to derive or solve the Navier-Stokes equations and then derive an expression only for small particles. And you look at Newton's expression, of course, it looks different, but Newton had this term called CD, drag coefficient. And if you equate the two, you get an expression for the drag coefficient, and it is listed below on the slide. And then Cunningham came and he said, if particles are really small, it behaves like the molecule, so it slips through and so forth. And then you have the free molecular regime. And now there's great understanding, but all of them go back to the Newton's expression for drag with the appropriate choice of the drag coefficient, right? And these are all summarized here again. So very quickly, that expression holds. But we always want to understand and apply it. So I always like simple examples. So let's take a particle here. Let's just release it. Newton also talked about gravity. Of course, he talked about apples falling. But let's take a small particle and do a force balance. Newton also did the force balance expressions. So there's a gravitational force, and there, as it's falling, there's a drag force which retards it, right? And I can just simply solve this equation. This is simple differential equation. We teach our first year or second year students to do it. And I plot the velocity as a function of the time. So as I release this particle, it's accelerating, but then it sort of reaches a constant velocity, and that is the terminal velocity. And there's a certain time at which it reaches it. It's dependent on the size and so forth, but it reaches this sort of constant velocity, right? So simple things, settling. And of course, I want to always play with numbers. Let me calculate the settling velocity for particles of different sizes in this room. Nothing else happening, only settling. As you saw my force balance, no diffusion, molecules are bombarding it. So I'm ignoring all of those things. But look at it, 10 nanometer particle takes 48 years to settle. That's why please be very careful where you go and dump particles in the atmosphere. Obviously, there are other cleaning mechanisms, removal mechanisms, but even a 1 micrometer particle would float around for 33 days, right? So some of you are not 48 years old here, the young students here. So if I released a particle when I was that age, you're still going to encounter it. So these are simple calculations that one can see, and it's of course a time to drop 100 meters, or if you want to dump particles, you want to release it high in the atmosphere so it doesn't come crashing down. All kinds of things one can do. Again, remember, very simple, one mechanism at a time and so forth. There's another thing I always like to say when I'm teaching a class, if people at the back row fall asleep, I'll take my chalk and throw it towards them, but the chalk will only travel so much, right? It depends. It's also experiencing a drag force, and that drag force is a function of size, and it's the initial velocity which I throw the chalk towards the back. So it traverses a certain distance and comes to stop, right? Obviously, gravity will pull it down, but I can then look at it and calculate an expression for this stopping distance. It depends again on the particle size, the initial velocity, of course, and so forth. Now, this is just an application of the drag force, right? I turned off gravity, so it's only drag force acting on a horizontally moving particle. With that, we design devices called impactors. Some of you might know these things. There are multiple stages. There are design criteria. I can measure size distributions using a device like this, which is just looking at the stopping distance with respect to the flow, right? So again, just simplifying the presentation, but there are details and so forth. And very surprising, of course, I want to measure small particles, so I want to increase the flow in these devices. This is actually goes back to my PhD work eons ago. The flow gets choked, but the scaling laws are different, so there's a lot of detail. But the thing, even today, PM 2.5, PM 10 is federally regulated, at least in the United States. Devices which are federally mandated are just based on this drag force or this inertial force. It's amazing, right? Today, of course, we have fancier instruments, which we are going to expose you to tomorrow and day after maybe. But the simple device is just based on the drag force and gives me PM10 and PM 2.5 values, which I can then I report and measure all over the country. Another important thing is we look at ourselves. We always say, hey, I'm breathing these particles. I have a head region, the upper respiratory region, the bronchial region, and the alveoli. Where are these particles that I inhale deposit? And you can see one can do measurements. These are, of course, validated, but one can also do calculations to find out the deposition fraction as a function of particle size. Of course, the total is the total that deposits and the different regions that I talked about there, right? So you can figure out. Now, this is not all bad. If I'm an asthmatic and I want to take medication, I want maybe the medication to reach my alveoli. So I would choose a particle size which is maximized. And you can see it's about 0.04 or 0.03 micrometers in size. And I would generate that and take my medication that way. On the other hand, I go out, I'm inhaling all the particles there. I can figure out what is being deposited where. The head region is very interesting. Small particles deposit in the upper respiratory tract. It's also a pathway. All the nerves, for example, the olfactory nerves get to the brain. So if I want to deliver things to the brain intentionally or want to prevent movement into the brain, I need to also pay attention to these ultrafine particles, because you see the head region, it's a very small particle. So simple things like this. So one can recap. I didn't even talk about diffusion in detail, convective diffusion. I just talked about drag force, but I hope it gives you an idea of what happens, right? But the key thing is it depends on the particle size. The movement depends on particle size, and of course, a lot more different parameters, some of which I sort of breezed by. The next thing is, if everything depends on size, does the size distribution itself change, right? If a particle is moving about, what prevents it from colliding with another particle and sticking together, right? In some sense. So aerosol dynamics, we use that term, alters the size distribution. You already know it better be important, because if it's happening, it's going to impact all the aerosol phenomena that I've sort of referred to in some way. or even some of the things you heard about earlier on. Let's look at collisional growth. I have two particles of size I and J. And now see that I'm not using diameter to represent size. I use the volume as a size metric. This is nice because when V sub I collides with V sub J and they stick together, the new volume is additive. Diameters are not additive. In fact, the shape might be so messed up from a sphere that initially I have spheres, but then I don't have a sphere. But the volumes are always additive. So we tend to use volume as a metric of size. The rate of collision depends on the concentrations, N sub I, N sub J, and just a collision frequency function, right? And of course, I then refer to Smoluchowski. I'm not showing you his picture. I think he was 1800s or maybe mid 1800s. He came up with this simple expression. The change in size of K size particles. K is formed by I and J forming K. So V sub K is Vi plus V sub J. When I and J collide, they form a K particle, but I double count because I collides with J, J collides with I. That's why that factor half. But then a K particle collides with everything else to no longer be a K particle. So I subtract the second term and I sum up over all particles as beta Ni Nk. So very simple number balance type expression. And then, of course, we want to solve it. It's not that straightforward, and we'll come to that in a second. I can look at this in continuous form because sometimes summations are good, but they're discrete representations. So in a continuous form, I just have a V minus V hat colliding with V hat to form a particle of size V. And then I do a similar kind of expression, just replacing the summations with integrals, right? But this is an integral differential equation, right? So not easy to solve. I solved simple settling equations. These now become really hairy, even mathematically to solve. And now I combine everything together because I'm coming to the end of my time here. So we put all these terms together, transport, dynamics. I am interested in the change in the size distribution function. The first term is the transport term. It could be due to a velocity. It could be due to diffusion. I'll give you an expression for that. And then changes in the size distribution. And of course, I should have added nucleation terms and condensation terms also. But the transport terms, let's look at the dimensionless particle velocity. If a particle is moving with the fluid velocity would impact it. Then there's this inertial effect, which is due to the drag. Then there's diffusion, and then there's gravitational settling, there's thermophoresis, external forces. So this transport term itself is quite lengthy, and solving something like this for the size distribution function becomes very complex, right? And let me try to illustrate that. So if I look at a computational model, I want to predict the concentration at every particle size. And let's say I'm starting from 1 nanometer size. The next particle would be a particle plus a molecule, right? A molecule could come and connect to the particle and become part of the particle. We call that condensational growth. So the smallest size that I have, 1 nanometer plus the molecular volume would give me the next size. So I again keep track with respect to volume. So if I want to simulate from 1 nanometer to 100 nanometers, sometimes I have to go much larger. Diameters are not additive. We already know that, but particle volumes are. So at the bottom, I list the particle volumes. So from 0.5 nanometer cube, I'm going to about 500,000 nanometer cube, right? So how many, and I want to predict the concentration at every size. So it's very simple. The number of discrete sizes is just the final volume minus that initial divided by the molecular volume, because that's the step size, right? Obviously, when 1 nanometer collides with another 1 nanometer, it's going to form a point or a 1 nanometer cube particle approximately. But in between, I could also have a molecular addition and so forth. So the number of discrete sizes is that much. So I have to solve 10 to the 9 equations to get my entire size distribution. And I have to do that at every time step, right? If I'm looking at a process. So this is not fun. And that's why we had the previous tutorial. Can I rely on machine learning algorithms? Onochi took this on. And then there are molecular models, right? There's chemistry. I'm just talking about simple physics, things colliding. There's chemistry and there's techniques. In fact, he was an expert in molecular modeling, I think, in his previous life. But then I want to combine with these aerosol models. I want to look at the transport and get something out of this. So not a simple thing. Like even the fastest computer is not going to readily solve 10 to the 9 equations, a billion equations. It's going to take months or even years to do that. And sometimes we have to do that for climate change predictions, for other predictions, or even in an aerosol reactor, making nanomaterials. All kinds of papers in the literature, making simplifications, all the way goes back from many years, including some of our own work. I'll just leave it at that here. But let's say everyone wants to use AI and machine learning. Can it really help us? So I'm just connecting now to the previous talk. And neural networks really allow us. There are others, aerosol scientists are bringing these in a big way. And Onochi is sitting at the back. He used a physics-based machine learning algorithm. I'll just allude to it because you've heard some of it. I need a training data set. So if you have a good graduate student, he ran we can use a very accurate model. And he did this for 60,000 initial conditions. And he did it based on the detailed physics. You can sit and do that, once you have a computer and an algorithm. And this, by the way, is only collisional growth. So very simple, one aspect of it. So you get a training set relating an initial size distribution to the final distribution. I can use integral properties and so forth. So this becomes my training set. And then we come up with, as you heard, the neural network, which is, to me, a simple matrix multiplier. The first case, I'm solving integro differential equations. Yeah, we spend a lot of time, generate a training data set. I could rely on experiments, but I'm not going to get 60,000 experimental data sets. We do have some, but not that many. But then use that to train and get a matrix multiplier, which goes from the initial parameters to the final parameters, right? But just doing that, this is brute force neural network. It's not going to be as accurate as you heard. Ultimately, you want the accuracy and the generalization to be true. So can I bring in some physics-based? So coagulation happens at a certain time scale. I'm throwing that into the process. I'm splitting my time domains into smaller time domains and bringing in the physics of the coagulation process in a simplistic way, and then trying to do this training process. And again, just jumping, of course, one has to see the details. You see that the physics-based approach results in the most accurate, most general predictions, agrees with the detailed sectional models and so forth. One ultimately has to look at the CPU time. It cuts the CPU time. There are others that would cut the CPU time, but would not be as accurate, right? So this is how you do it. So this is an exact example of what you heard before applied to aerosol physics, right? And this is just collisional growth. Now you bring in all these other terms that I said, and you begin to modularly develop these algorithms that people can then use maybe to solve the climate problem or at least predict. So with that, I'm going to summarize. We saw this graph earlier. I didn't mention timescales, right? In reality, I want to apply it to a system. So I want to bring the concept of time in. Just creating a particle, it happens at a certain rate. So this is the characteristic time for nucleation. I'm not describing all the terms. It depends on the critical concentration divided by the nucleation rate, right? So depending on the characteristic time and the residence time, one can then begin to get a good idea of what is happening in the system. This is for condensational growth. Remember, a molecule sticking to a particle and becoming larger. So depending whether I'm in the free molecular regime or the continuum regime, I have expressions. Actually, Professor Wu derived this expression very elegantly of several years ago now, I think. So, and then the coagulation process, which I referred to, also has characteristic times. So we put all these characteristic times together, either to guide our simulations or even to understand the process. So if it's an aerosol reactor making nanomaterials, I might want to choose a residence time and then want to control some of these parameters to promote a certain process over the other and so forth, right? So again, this, we talked about transport, capture, deposition, not too much in detail, but all of this puts together, and then we can bring all of this together. So sort of a runway description of an entire aerosol process or the life cycle of a particle, but a lot of details. So I hope some of you, the students especially, would refer to all the materials and have a more detailed understanding. So I'll stop here. Thank you for your attention. I think there's another talk, right?
Okay, now the session is open for questions.
Yes.
I'm just learning here, so question. How do you determine how many number of molecules in that cluster?
Correct. So that, let's say I'm using a classical prediction, right? So it's a thermodynamic process. So initially I have only molecules. Then I'm saying I'm forming one stable cluster with molecules. So it's a change in the free energy of the system. And obviously the surface tension will hold my cluster together, right? So that's what I showed. So the critical size then is calculated from the thermodynamic processes, right, of the surface tension, surface energies holding it together, and the number of molecules in this system, right? So that gives me a critical size, correct? So we actually calculate it based on. Correct.
So what is the how that is, how good the prediction is?
Okay, so this is very good. You're asking, I gave a very simple explanation for understanding the classical theory of a single component. But let's say I have water and sulfuric acid, which we have a lot, at least in Midwestern US or even in the atmosphere here, right? So if you have two component systems, the equations become a little more complex, but I can still apply the classical theory, just as I described it. So the free energy that I used for a single species now will be free energy for all the different species added together. And that will tell me what is the number of water molecules and number of sulfuric acid molecules, for example, or organic species molecules. Organic species are also very common here and so forth. So yes. But the classical theory really fails when I want to go into my lab and make nanomaterials, right? In high temperature systems, it's way off in prediction. So there we use other kinetic expressions or chemical kinetics approaches. I don't know, tomorrow you might hear some in the nanomaterials session and so forth, right? Yeah. So this was very simplistic. Yeah. In terms of a first step. Yeah.
cannot go used to a single phase fluid mechanics, or fluid dynamics, right?
Yeah.
So, but then when you're dealing with aerosols, now you have two phases.
Correct.
So if you got to define the lay a number of properties or criteria for us to define when the single phase fluid dynamic cannot be used. So now we have to do the transfer equation for aerosols, what those parameters.
Very good. So that is also defined very well. So you move from, so the way in most aerosol systems, even in our reactors, the volume of particles to the volume of the gas is quite low, right? So we can use single way coupling. So the fluid is impacting the particle motion, but the particle is not impacting the fluid motion. But you're absolutely right. As the concentration goes up, there has to be a two-way coupling. Oftentimes, they use the term in chemical engineering, multi-phase flows. They, of course, deal with much larger particles. So it's in the continuum regime. So it's, I would say, relatively easier to derive. But when we have these smaller particles, the relationships become more complex. There is a way to calculate that now a critical concentration above which we have to, the simple explanations I gave, like the drag force and things, will break down because I need a two-way coupling. So it is also a very good point. But if I look at, by the way, these are industrially produced nanomaterials. DuPont has been making TiO2 particles for hundreds of years, empirically. Even in a TiO2 reactor, which produces 1 ton of material per hour at, let's say, 300 nanometers, the concentration, it's a one-way coupling that still works at those levels. So the concentration has to be rather high before the two-way coupling comes in. In multi-phase reactors in the chemical industry, petrochemical industry, where they may be referring to oil droplets and other things in water, there it's a little lower because these are much larger particles. But these are very small particles, so that limit is quite high, right? But very good point, and one has to be very cautious as to the coupling. Yes.
Didn't understand it correctly, but in your deep learning based collaboration model, do you start with the a priori assumption of a distribution? You do a long term, the input data is the long term, do an a priori distribution.
No, I have to train my set, right? So I train with randomly chosen distribution, more relevant to, so initial size distribution is a size distribution, but then I fit to get the final conditions, you see, rather than track every single size, I'm just using an integral moment method to represent the distribution. Yeah. And yes, so.
And you're only statistical study, you're not really,
yeah, very simple coagulation, right? But this is the first step. And now you want to begin to, yeah, start advancing that, right? Mhm. Good.
Any more questions? If not, let's thank the speaker.
Yeah.
Okay. And we will move on to the next tutorial, the final tutorial. Dr. Walter Mui. Yeah, we are very happy to have Dr. Walter Mui from California coming over here. And Dr. Mui is the director for the South Coast Air Quality Management, right? And they run a very large network of local sensors for PM and other air pollutants. So it's great that we can learn from their experiences and also sharing with us what are the new challenges that are in front of us. Now we are just waiting for the slides to be loaded. Yeah. Thank you so much. Thank you.
Hi, good afternoon, everyone. Thank you so much for your attention and for attending this talk on low-cost air quality sensors. So low-cost sensors, what their promise is they allow for accessibility into air quality measurement that traditionally hasn't been open for some folks. So that includes community scientists, regular people, regular consumers who can go on Amazon and buy one of these things. They open pathways for people in low and middle income countries, LMICs, to be able to make air quality measures because they can't afford what we consider in the West to be regulatory or research grade proper instruments. They also afford lots of collaboration and intersection in the academic space, right? Because now we're seeing with low-cost air quality sensors, we allow other kinds of professors to enter to do some kind of work with air quality measurements, like environmental justice professors, those who work in public health, those who work in indoor air quality spaces, or mechanical engineering and building design. So all kinds of potential pathways for accessibility for air quality measures being opened up by how affordable these devices are. And yeah, so funnily enough, I'm actually a South Florida native. I was born in Miami Beach. I grew up in Hollywood, just up in Broward, and then and most of my life in Hialeah. And I have never, my whole time living here, I had not been to UM, either the main campus or here until now. So thank you so much for inviting me. Thank you, Professor Jiayu Lee, for inviting me. So yeah, I did my undergrad at the University of Florida, and I was taught a few of my classes in undergrad by Professor Wu here. So thank you. Good to see you again. And then I did my PhD at Caltech. I graduated out of the Flagen and Seinfeld lab, and I think that's the same lab that Pratim Biswas came out of. So, just a small world. And so after graduating, I worked at the South Coast Air Quality Management District. So you have at the federal level, you have the national EPA, and then they delegate air pollution responsibilities to each state. So here it'd be like Florida DEP. And then in California, we have the California Air Resources Board. And because air pollution is such a complex and serious problem in California, they just handle the mobile sources. So cars, trucks, buses, ships. And the stationary sources, they further delegate that to like 35 something air districts. And so the South Coast Air Quality Management District, that is the local government agency that handles the stationary sources of air pollution in the Los Angeles metro area. And so I worked there as a air quality specialist. It's like your analyst kind of grade position for 5 years. And now I run the low cost sensors group at the agency. Yeah, some stats. Southern California, 17 million residents under jurisdiction. So I think some history is fun. I know there have been some other historical facts brought up previously, but I wanted to pick out some historical incidences that have led to our understanding of low-cost air quality sensors today, as well as the group that I run, the low-cost sensors, the AQ-SPEC Air Quality Sensor Performance Evaluation Center at South Coast AQMD. So in the 1860s, we had John Tyndall discovering light scattering by particles, the Tyndall effect. And then in 1908, we have Gustav Mie developing Mie scattering theory. And then specifically to Southern California in 1943, they had their first major, not their first, but the most majorist smog event where visibility was limited to just 3 blocks. And then, as a reaction to that, the LA County Air Pollution Control District was created. And back then, it was the air districts were on a county by county basis. So they just followed political lines. But we know that air pollution doesn't respect political boundaries. They get transported north, south, east, west. And in the Southern California area, we have onshore and offshore daily flows that happen. So there's an east-west kind of transport of ozone precursors and secondary organic aerosol formation that moves from the coastal western part of the area to the eastern inland and desert parts. And in recognition of this being a regional air pollution problem, there were efforts to unify some of these politicized air districts into what we now know today as the South Coast. Oh, I'm getting ahead of myself. Okay, that's a fact on the next slide. So I'll talk about it later. But and then we also have some inventions that happened that help make our current understanding of low-cost sensors possible, like the one in 1951 by John Shai for a photoresistive translating device, which is a light responsive electrical device. And then like 1950s, somebody invented the laser. There's a debate about who exactly, because there's a claim by a Japanese guy and a claim by someone like a grad student at Columbia University, and there's other debates about that. And then in 1964, we had the patent for the miniaturized electronic circuits. And then finally, when the government got around to doing things in 67, we had the Air Quality Control Act passed by Congress so that each state could then develop their own air quality standards. And at that same year, the California Air Resources Board was created. And then actually later, that's when the federal government, EPA, was formed. And then Congress then passed the Clean Air Act to set national air quality standards. But by then, California had already established its own stricter standards. In 71, we had a patent by Naoyoshi Taguchi for a metal oxide sensor or metal oxide semiconductor material. And then finally in 76, that's when I circle back to the coalescence of some of these politicized air districts into what's called the South Coast Air Quality Management District. This was an effort that was led partially by the League of Women's Voters to make sure that we had proper protection of all the people from east to west, and that people in the east weren't disproportionately suffering from the air pollutants that were generated by those living near the coastal areas. And so, starting around the 2000s, that's when we start to see some major momentum building in the low-cost air quality sensor space. And in 2014, at my agency, the Air Quality Sensor Performance Evaluation Center, AQ-SPEC, was formed. So this year is the 10-year, well, we've just passed the 10-year anniversary of the low-cost sensors group at South Coast AQMD. Okay, so what do we mean by a sensor? If you talk to a layperson who's been looking at these on Amazon versus someone who really works on these devices, the optomechanical electrical devices, there may be different understandings of what's meant by a sensor. So your layperson might envision them as something like this. These kind of integrated devices that have a nice little screen that tell you, what is the PM 2.5 concentration. But more technically, a raw sensor is, these OEM electronic devices. They sense a physical phenomena that could be current, resistivity, and these signals, they correlate to some concentration of a pollutant. And, major classes, and you might be wondering, I'm going to get into gas, why are we talking about gases? But gas sensors are important. But major classes of low-cost air quality sensors are electrochemical sensors, metal oxide sensors, and then the ones that perhaps in this audience are more familiar with, those that do optical light scattering for particles. So gas sensors, they may not be of too much focus, but if you had the option to do measurements with low-cost gas sensors, it'd be beneficial because the gas measurements, they could tell you something. You could infer like, particle composition or maybe source of the particles. And also what's important is that if your gas concentrations are changing, that also tells you that perhaps there's a temporal shift in the source or composition of your particles. So anyways, onto gas sensors, we have electrochemical sensors. They're typically used for sensing ozone, nitrogen dioxide, carbon monoxide, and VOCs. And they basically work on a redox reaction happening on an electrode. Yeah, okay. So they are susceptible to temperature, humidity, and other non-target gases. And they do have an aging effect, the time since manufacture, because they are continually exposed to the air ever since they are manufactured, and so their lifespan degrades after that. And then related to that are metal oxide sensors, and again, they will measure some of the same kinds of pollutants that electrochemical sensors do. They are basically also working on electron donor and acceptor phenomenon happening on a surface. And they have some of the same susceptibilities to interferences as electrochemical sensors as well. And then sticking to gases, you can also use infrared to detect some gases, specifically carbon dioxide and carbon monoxide. And their aging or drift effects are more about a lamp runtime phenomenon, not necessarily how long since they've been manufactured. And then finally, on the other end of the light spectrum, UV, you can use UV light in VOC sensors, specifically what are called PID or photoionization detectors. And so these, some VOCs, they will ionize depending on the electron volt rating of the lamp. And then those ions will then collect on the photodetector, and then you can correlate that signal to the concentration of the VOC. And this, again, also the aging or drift effects are due to lamp runtime. Okay, moving on to particles, which is what we're probably more familiar with in this space. You've got two major classes in the low-cost sensor space, nephelometers and optical particle counters, or OPCs. So first, the nephelometric type of low-cost sensors, they are the most common, they are the cheapest. So they are used for sensing particulate matter in an ensemble light scattering manner. So the amount of light that is scattered is related to the overall concentration of the particle mass through some proprietary manufacturer developed calibration curve. And these sensors, they're indirectly affected by humidity because you do experience particle growth at certain humidities based on the composition of the particles. And again, their aging effects, we've seen these be stable for about 3 to 5 years. And it is also due to a lamp runtime. I think there was a talk earlier, I think the first talk of today about like multi-angle and broadband angle scattering. But for low-cost sensors, the best you can hope for is 90-degree light scattering with a very cheap, LED light, probably in the 600 to 700 nanometer wavelength. And they're probably not going to be, you're not going to see anything less than 0.3 nanometers of particles. And then they claim, a lot of them will claim that they can measure up to 10 micron size particles, but so on the low end, as you go smaller, the light scattering drops as a power to the 6 power of the diameter, right? And then the light scattering from these low-cost sensors, they probably peak at around 1 micron. And then as you get into the super micron size range, the specific scattering drops off. So they're not really great for coarse particles. And then they're also blind to particles less than 0.3 microns. So it's really that 0.3 to 1 micron range that these low-cost sensors work the best at. Okay, and then the other one, the optical particle counters. These are less common. They're typically more expensive. There aren't really that many of them on the market, but these will detect single particles, assuming that the designer has properly focused the particles to flow in a certain flow path. And again, these sensors, they do suffer the same kind of susceptibilities as the nephelometric type. So that is particle growth at high humidities and aging from lamp runtime. And I forgot to mention at the very beginning, I am representing a government agency. We don't endorse or recommend any particular model, make, or whatever. Don't ask me which is the best sensor. I can't tell you. And if I mention any make, model names, or you see any on the slide, that's just for discussion purposes. I'm not endorsing anything. And I know there's some TSI folks in here, and I didn't mention any TSI stuff, so sorry. Okay, so that was a raw sensor. Now for your typical layperson, what they understand as a sensor is a sensor system. So this includes, the raw sensor inside of an enclosure. It already has power, so you can plug it into a 110-volt outlet. And it has a means of transmitting the data, whether through Wi-Fi, cellular signal, Bluetooth to your phone, or maybe LoRa, or maybe it hooks up with a USB cable to your laptop to do some data logging. And they will come with a user interface. And then it also has some kind of built-in way to convert from that raw voltage, resistivity, whatever, to parts per billion or to micrograms per meter cube. So all that work's been done for you. That's what is meant by a sensor system. Okay, and this is just a nice little illustration of some of the main components that are in a sensor system. Okay, and so it's important to draw a distinction between low-cost sensors and regulatory grade monitors. So on the left, there's an example of a couple of common low-cost particulate sensors. And on the right is an example of some regulatory grade monitors. And so you might notice offhand, some differences just on size, right? You could probably assume that there's a price difference. So yes, those are the differences. Low-cost sensors, they are by their name low cost. So that makes them accessible to many people. And also there's strength in numbers because they're so inexpensive. For the same capital cost, you could probably buy 100, for the same money you would have spent on a regulatory grade instrument, you probably could buy like 100 or 1,000 of these and then get a much more dense coverage, what some people call hyperlocal, hyperspatial, hyper whatever, hypertemporal, all kinds of buzzwords. And also these sensor systems are typically much easier to use out of the box than a regulatory grade instrument because they are often designed for the regular layperson to plug and play. However, the drawback is the data quality can be pretty questionable, and that's a big obstacle for acceptance of low-cost sensors, at least in the United States regulatory space. Whereas regulatory grade monitors, they're much more expensive. They're pretty much only accessible to people who have money, governments, academic institutions. And you also need not only is it capital expensive, but it's also technical knowledge expensive. You need people who are trained and skilled to be able to operate and maintain and calibrate and interpret the data from these instruments. However, this is what kind of data is acceptable for policy, legal, and regulatory purposes. Okay, that's just some more comparisons. So when we talk about low-cost sensors, we might be talking about hundreds to thousands of dollars range, as opposed to tens of thousands of dollars for regulatory grade monitors. A lot of these low-cost sensors, they are running their business model off of a subscription model. So you have to not only buy, spend a couple $100 on their product, but then you have to pay like a monthly subscription fee to even see the data that you collected, to download it, right? But that is the business model that most of them have found to be sustainable. Whereas for regulatory grade monitors, like for example, TSI isn't charging a subscription fee for you to get data off the APS or SMPS. The maintenance costs can be low for low-cost sensors, but some of these do have replaceable components, as opposed to the consumables for more research and regulatory grade instruments. They can be quite a bit more expensive. They're also much smaller and quieter, less noisy, and also require a lot less power. Most of these you can run off of a 5-volt USB port. And when I say expertise needed is low to medium, that's kind of misleading, right? So to use it out of the box, yes, you don't really need much more skill other than to know how to plug something in. But the interpretation, it is not that straightforward and can be very misleading to just read the straight PM 2.5 off and think that that's the truth. But that is the reason why our program exists, the AQ-SPEC program, because we do, and I'll get into this later, our function is to clarify to the public how low-cost sensors are factually performing as best as we can. And then they're, it's sad to say, but they're also pretty much disposable. It is an e-waste problem. These things, gas sensors, as I mentioned, they start degrading from the time that they're manufactured. So they might last 1 to 2 years, and then you have to replace that. Particle sensors, they probably can last 3 to 5 years. Whereas your regulatory grade monitors, they will probably last decades, but minus the consumables that some of them have. Now, the performance and accuracy, that is a huge difference. Again, questionable for sensors, whereas regulatory grade monitors are considered, regulatory and research grade, considered the best, and they are used as the point of comparison for these low-cost sensors. So in some parts of the world, low-cost sensors might be the only source of air quality information. So for example, here is a map of Kenya, and these are the purple airs that exist in Kenya, and it's better than nothing. At least some people do have some sense of the relative air pollution problems and exposure they're facing. And then we kind of have an inverse right now. So I just flew in from LA last night, and then overnight, when I woke up this morning, I found out that a wildfire just started, and my neighborhood is actually just adjacent to one of the evacuation zones. So actually, right after this talk, I'm going back to the airport and cutting my trip short to try to get back to my cat. So it's funny because like in the United States, for example, in a wildfire situation in Southern California, we have very dense coverage of purple air sensors. And so it's very useful for like tracking where the smoke plume is going. And so that, regular people can find a map with, red, bad, green, good, and know whether, they are going to be exposed to a lot of smoke. But then the reason why we have wildfires in Southern California mostly is, sorry, let me not misspeak. Sometimes we have wildfires that spark because of our electrical transmission lines, which is exactly what happened. And so large swaths of the area don't have power. And so you have this dense purple air map, but a lot of the sensors are actually offline now because there's no electricity to run them. And so actually that data doesn't exist. But going back to this situation, if there is power and some means of data transmission, this does serve as a way for low and middle income countries to gather air quality measurements and for their EPAs to be able to have the data to either develop air quality policy or enforce air quality regulations. At this time last year, I was actually in Accra, Ghana. I visited the University of Ghana because they had just started up a low-cost sensor evaluation center. And so I visited there to give a couple lectures, but also to visit their low-cost sensor testing space, give some feedback, see their data practices. and advise on things. And so, you know, I spoke to one of the folks at Ghana EPA, and they said that they literally don't have the resources to even purchase one $200 purple air sensor. Like, can you imagine that a whole nation's EPA could not afford $200 for that? And so but that is still more reachable than $20,000 for, you know, a beta attenuation monitor. And so part of our assistance is actually, you know, some of our sensors that we have access, we have been sending to Ghana. Whoops. So yes, air quality sensors, one of their great advantages is the accessibility for lower resourced entities. Now, in the United States, we're not quite there yet on relying on low-cost sensors for it, because we do have concerns about the quality of the data, but there is some acceptance of low-cost sensors at least supplementing or complementing the air quality information that comes from regulatory monitors. So here's just a graphic of, on the left, you know, you might have, you know, EPA, FRM, you know, PM 2.5 measurements happening, you know, 20 miles apart. But if you can imagine on the right, if we have a lot of affordable low-cost sensors, these could be installed on, you know, in every neighborhood. And then you can see that gradient of how the air quality is changing between, you know, in between these spaces where the regulatory measurements are happening. And actually, that's something that we've done at South Coast AQMD, our agency. So we have on our website a public air quality index map, and it's color coded so folks know what, you know, their current exposure is. And so you can see in this plot, the big circles, those are our regulatory monitoring sites. And then the little blue circles, those are all the purple airs that existed actually several years ago. This map is a lot more dense now with the blue dots. And then our jurisdiction, we divide into 5 by 5 kilometer grid cells. And so what our agency has done is we've blended regulatory grade information with low-cost sensors, with a little bit of satellite models. And there's a bit of residual creaking that's happening to differentially weight the contributions of the air quality information coming from the different measurements, because we want to trust the regulatory measurements more. But in certain 5 by 5 kilometer grid cells where there's only low-cost sensor information, then you might see the weight given to the low-cost sensors more. So this provides a more granular public air quality information to our residents. And this is just a side-by-side comparison. Previously, the air quality index map was just based on our regulatory air monitoring stations. So they were giant polygons, one color applied to that entire polygon. But now with the incorporation blending in the low-cost sensor data, we can provide a much more granular hyper-local neighborhood scale air quality information. Okay, so now to the program that I've taken over as of a year ago. The Air Quality Sensor Performance Evaluation Center, AQSPEC, we were established in 2014, and to date we have evaluated over 250 low-cost sensors. And what we do is we bring in these devices from the market. We either buy them ourselves or we work with the manufacturers to say, hey, you know, we do this testing. Would you like to send it to us? And we'll do this testing. And we do this testing for free as a public service. The caveat is that whatever the results are, good or bad, we're going to publish on our website. So that, you know, what's nice is that we do maintain a degree of independence and third-partyness and, you know, influence from the manufacturers, because at the end of the day, we're serving our taxpayers by, you know, giving them the information of like, if you, a regular person, were to buy this product and plug it into the wall out of the box, what kind of performance would you see? And the plot on the right, that's just a cumulative quantity of the sensors that we've tested in our program. And the most recent one we had is VOC sensors. Okay, oh, I already talked about this. Main goals, you know, evaluate the performance of these commercially available sensors. We do also want to promote the marketplace though. Like we do want to see this space grow and improve. And so part of our work is that we, you know, our reports, we're giving the brutal honest truth, and that is for the sensor manufacturers to take as feedback to improve their next round of product. And so we do this for free, and we publish, you know, free PDF reports on our website for the public. What we don't do is we don't provide sensor calibration functions or corrections. We don't rank, score, grade, promote, recommend sensors. We don't certify them, at least not yet. There are efforts in Korea and France, in Europe overall, and then maybe in the United States, we may get to sensor certification. But at the moment, you know, there's still a lot of work that we need to do, not only us, but also other levels of the levels of government to come to an agreement on like how would we, you know, certify and pass fail or whatever sensors. But that's what we really do need for the public, because, you know, we can pump out as many sensor test reports as we want, but they're not really understandable, accessible to the public. They're not you know, it's like time series and scatter plots, but they just want to know pass fail, is it good or bad? That's really just what they want. But we'll get there someday. Okay, we just test these cheap sensors. Okay, that $2,000, that's kind of outdated, inflation, everything, maybe with the accept higher thresholds, because now everything's more expensive. And for the past 10 years, we have been testing out sensors that measure criteria pollutants, but there is a lot of innovation happening in low-cost sensor space, and I do want to pivot the program to start testing out more devices that are non-criteria pollutants. So we just finished testing our first low-cost CPC. There's a $3,500 CPC on the market. And so we just finished testing that out. So we expect to publish that report in the next couple of months. We've tested a couple black carbon sensors, and we are doing a lot of VOC sensor work now. And then hopefully we'll also get into some methane sensors soon. We have the infrastructure to do methane. We just haven't gone around actually doing it. Okay, and in this program, it's grown way beyond just sensor evaluations. So yes, we test out air quality sensors. We also do work with sensor data management. We manage a few sensor networks in the Los Angeles area, and we do a lot of educational outreach as well, such as this talk I'm giving, such as some conferences we attend, we give presentations at, we do publish papers in our group, and also we are starting up a sensor library. So the idea is that even though they are inexpensive, you still see the vast majority of low-cost sensors being purchased and deployed in wealthier neighborhoods. Because $200 is still a lot to people in lower income neighborhoods. So we are trying to build up a bank of sensors to operate like a public library. So anyone in our jurisdiction can come and check out a sensor. You know, maybe it's a K-12 teacher that wants to use it to teach her students about air quality and environmentalism, or maybe it's a concerned mother in a community who wants to do some measurements in her home, or maybe it's a community scientist, you know, that wants to help out their neighborhood association or whatever, make some air quality measurements. So our duty would be not only bring in the sensors and keep them calibrated, and then, you know, after that, we kind of lend these as tools to build public trust with our communities and also expand their accessibility, remove the cost obstacle to using these tools. And then sorry, the font is really small, but our group's role is we're kind of an intermediary in the sensor landscape, because you've got sensor manufacturers, they make the things, they improve on the things, they sell the things, they market the things. You know, they publish spec sheets and claim that their things can measure it this good or this, you know, not so good. And then on the other end, you've got consumers, the people, you know, buying things on Amazon, and all they see are the 5-star Amazon reviews, right? Like, oh, the user interface is so sexy and it's great to use, and oh, I trust it a lot and it's so easy to plug in, but that doesn't speak at all to the accuracy. So, you know, what our group does is we kind of bridge that gap in understanding, because you've got claims from manufacturers on one side, and you've got a lack of technical understanding on the public side. So we test these products out. We are doing our best to communicate in a way to the public how these sensors work. Okay, and we are really blessed at our agency to have the infrastructure to do this kind of work. So we do field testing. So we operate about over 30 air monitoring stations in our jurisdiction, and they're all equipped with regulatory grade and research grade air quality instruments. So we can put these sensors, co-locate them, you know, next to these air quality reference air quality instruments for about 2 months, and then we have side-by-side comparison data to judge their precision and bias. And if these low-cost sensors are not designed to be deployed outside, like they're not sufficiently weatherproof, we also have a Stevenson shelter, like a chicken coop kind of enclosure to install them in, and then, you know, yes, on the ultra-fine side, there's definitely concerns about particle loss. And on the coarse side, there is. But I think we're talking about PM 2.5, that I think our meshed enclosure is okay. And then we've also got 2 laboratory chambers. In the photo, you see a blue chamber. We use that for like 8 years to do criteria pollutant testing. And then we've since retrofitted that to do VOC sensor testing. So we've done a lot of leak proofing of that to inject benzene and other terrible things to the VOC sensor to see how they do. And then we have the white chamber on the right. That is our newest chamber. That one we are using for our criteria fluids, and that can handle about 20 sensors at a time. So we do a big batch. And so in these lab tests, we'll expose them to controlled temperature and humidity conditions and yes, progress. We're getting there.
Okay, presentation mode. Up here. Okay.
Okay, thank you so much.
Yeah, no worries.
Yeah,
Sorry about
I'm glad we get our online viewers back. Okay, so yeah, as part of the cherry on top is we do have some vehicles at our agency that we've gutted and fitted in some research grade and regulatory grade air monitors in. And you know, part of my early time at the agency was working on designing a double shrouded particle probe to do mobile sampling of particles. Because you can do isokinetic, but then you can't really keep up the same velocity driving on the traffic congested freeway. So I was like, what do we do on aircraft? Shrouded probes. Let's do a double shrouded probe. Let's do, you know, computational fluid dynamics modeling. Let's do some Monte Carlo particle trajectory simulations to model this shrouded probe. So we've got the shrouded probe done. We've got our gas sampling system set up. All we need is just to get our program, you know, our bread and butter running. And then when I have the staff time available, I'll get them working on getting this mobile sensor testing lab up and running as well. Okay, so, you know, we've done this for 10 years, you know, hundreds of sensors. And so there are some generalizations we can come to in our experience so far. So for example, in our field testing of PM2.5 sensors, over the years, we have noticed that their R squared with the reference monitors has been steadily increasing. So the products are getting better with time. We don't know if that's an actual physical hardware improvement, or maybe it's a software proprietary, you know, algorithmic improvement. You know, it's possible that with successive generations of products that the same manufacturer has tested with us, maybe they've been using our test, you know, test results as training data for their future product, right? But nonetheless, their R squared has been going up in time, and their mean absolute error has also been trending down in time. So this is very promising because it does indicate that the state of the industry is getting very good for PM2.5 sensors, and that these tools are becoming more trustable, credible, reliable, especially for lower resourced entities who want to use these tools. We're also seeing some improvement in NO2. NO2 started off really terrible, but it is slowly getting better. There may be some physical improvements like doping. They might be doping the substrates to improve its performance, but there's probably also some algorithmic IP stuff they're doing to improve it. So if we look at the overall collection of sensors that we tested, so for particles, I've got this plot on the right. So on the x-axis, we've got the mean absolute error, and on the y, we've got the r squared. And then I've got gray points are sensors that report PM1 particle micron. And the blue points are those that report particle mass below 2.5 microns. And the yellow are for reported observations from sensors for less than 10 microns. And you can see that for PM1 and 2.5 sensors, we're actually doing really good. We're well above 0.7 of an R squared, and the mean absolute errors are in the single digits of micrograms per meter cubed. PM10, the coarse fraction, that's kind of where the sensor space is still struggling. I think there's a lot of possible explanations for that. There's certainly design flow path considerations, because these larger particles, you're asking them to flow in the air and then maybe get sucked up, make a 90-degree turn into this sampling space that's done by a fan, not a pump. And then they have to navigate some circuitous path. And so with their inertia, they're getting impacted onto various surfaces. So there's that physical contribution, but also the specific light scattering as you go supermicron also decreases. So that's probably another contribution for the underperformance we're seeing for sensors that report PM10. Yeah. Okay, and then on the gas side, sorry for the x-axis being in log scale, but that's because of carbon monoxide. But we can generally see that we're seeing pretty good performance from the ozone metal oxide sensors right now. It's kind of getting there too for carbon monoxide and what's the great one? I can't even, nitrogen oxide. But, once you start getting to the other gas species, their R squares are falling below half. So it's kind of a 50-50 guess if it's right or not. But that just tells us, where we should focus our attention to be testing more sensors that measure those pollutants and then provide more feedback to the manufacturers to improve their products. So getting into data quality, there's many data quality hazards with sensors. You have hazards that come from the product itself, from how you use it, and then from how you interpret it. So from the product itself, these are pumped out at a very low cost, high volume. The quality control may not be there in the manufacturing process. The manufacturers may not be making quite accurate claims about their performance. And then there's also data transmission reliability issues. So if one good use case for these low cost sensors are in remote areas. So you connect it to a solar panel, maybe with a Cradlepoint, SIM card, but depending on the cell signal strength out there, you may not be getting the data you need. Or on another end of the spectrum of the use cases, you give it out to a community member and you tell them, plug into your wall, connect to your home Wi-Fi. But then we've seen instances where we've given it to a church and they were going to keep it up, but then for Christmas they unplugged the sensor and plugged in the Christmas decorations, and then February, March, we're what happened to the sensor data? They never plugged the sensor back in after Christmas. So it's just gentle reminders so there's all kinds of ways that the data transmission, the uptime is not there. And there are interferences inherent to the operational principle of the low-cost sensor. Electrochemical sensors, metal oxide sensors, light scattering particle sensors, they all have different influences on whether the data is correct for particles, especially the humidity. Okay, setup and operations. People may not be installing these low-cost sensors at appropriate sites. They might be installing them, directly over their barbecue grill or something, and then they see this light, where's that happening from? If their objective is to measure ambient air quality. We see lots of issues with people installing them at proper heights. Power reliability, again, some folks not remembering that these things need power to work. We also, at least in our area, we've seen some theft, vandalism problems. So, one of the obstacles to installing is at every city street lamp intersection is that if we put it too high, it's too difficult for the city workers to maintain. But if we put it too low, people will damage and steal them or do something to them. So yeah, it's unfortunate. So theft, vandalism, and curiosity. Maybe curiosity is not malignant, but people will poke and prod these things. And keeping the units well maintained or calibrated. These things do have consumables, especially the gas sensors. So if you it's not necessarily just set and forget it and expect it to work good for 5 years. Okay, and then finally on the other data, the final leg of the data quality hazards with sensors are analysis and interpretation. These things do drift, they do age. There are outliers. You can't just trust that, every single data point coming from these sensors is valid. They're not calibrated to your local conditions. For example, purple airs, at least at the beginning, they were calibrated to a Beijing atmosphere. And then you can't expect to deploy them in Miami or Los Angeles and assume that they'll work because you know that the particle compositions are different. So your signal, there needs to be some kind of correction to the signal. And then, the conditions at which you deploy may not be representative of the conditions at which you calibrated. So you could calibrate them in the spring, and then you deploy them in the same area in, the summer or the winter, and then there's a shift in the wind direction, your composition has changed, your particle size distribution has changed. So again, your calibration probably won't be quite right. Yeah, and then finally, an ambiguity and interpretation of results. So, again, they're accessible and great for people who are not classically trained in air quality measurements. When you have community scientists, regular lay people, or even other academics who are not classically trained in air quality measurements, there are a lot of obstacles that they need to be helped with to properly understand what, 10 micrograms per meter cube means when the thing hasn't been calibrated. So, ideally you would set these up, make sure that it even turns on, calibrate, deploy, and then maintain. And that's a continuous cycle of maintenance to keep up the data quality. So sensor calibration, I think I do need to rush through a few of these slides on time, but calibration is just co-location. You put the thing next to a reference of some sort. And so if you can calibrate it to a regulatory or research grade monitor, this could allow you to reach quantitative conclusions using that low-cost sensor. But again, not many entities have this expensive equipment other than universities and government agencies. You could also opt for a more medium cost reference. Again, these things are not endorsements of anything that you see on the screen. But there are lower cost things that are probably somewhat more trustable than a low cost sensor. And so this is your quote unquote truth, and then you may be able to reach quantitative conclusions, maybe not. And then finally, in some cases, you may have no other option but to calibrate it to, if you have a network of 20 sensors and you just have to arbitrarily choose the golden one, say that's my truth, and then calibrate all your other sensors to that one. You probably can't make quantitative conclusions, but you could probably at least make relative conclusions. You could see, certain spots of the neighborhood are higher than others if they're all harmonized to the same sensor. And so this is often a situation that's faced in low and middle income countries. There are no regulatory grade monitors to calibrate to, or the only option is a beta attenuation monitor on the rooftop of the nearest US embassy. And so calibration, there's many ways to calibrate. You can do a simple linear regression model, but as we might intuit, humidity could play a large role in this calibration function. So you may want to incorporate some kind of term in your calibration model to account for humidity. If you happen to know refractive index or composition, that may be another term in your model. So that may evolve into multiple linear regression models. And then this is also where the intersection of other academics are coming into the air quality space, because there's also a lot of space for AI ML experts to develop random forest or neural network models to try to correct low-cost sensor data when exposed to a large training data set. These are elementary, basic, you probably don't need those, but the simplest thing you could do is a simple linear regression, put in Excel, X, Y, put the trend line. And then this is probably, the simple linear regression model. That's when we're working with community groups and we were doing our education outreach with community groups, we rely on the simple linear regression model, something in Excel, because that's what is most understandable. And that's that's what we can expect to be successfully used in community groups. And I'm not trying to sound like I'm talking down about, but that's just, realistic. And, maybe if you're working with, undergrad students, you may, be able to have them use multiple linear regression models. But when it comes to the more advanced models, or ones that are not as transparent, that's a hard sell to work with community groups, because there's already that government distrust that we have to overcome. And so, more, presenting them with more things where it's well, we can't really explain it to you, and it's a mystery box, that doesn't really help with the trust building. So there's many wonderful things that we can do with AI ML and to get better corrections. There's so many kinds of techniques. There's, gradient boosted regression models and Gaussian, all kinds of things we can do. But, for our public outreach, we have to stick with what is understandable, hopefully for a community member. Yeah, that's just, this is just simple starter slides. I think these are like elementary things you learn, but, okay, so using sensors without any calibration, that's the danger zone. You may not be able to trust the accuracy or even the precision because the quality control by the manufacturer may not be great. You know, a slight improvement is individual calibration functions for each sensor if you can choose a golden sensor. At least they're all harmonized and you can make relative judgments of air quality when they're deployed across the network. You could also choose to apply a single calibration function against all the sensors, and that's another way of harmonizing them. So in those two paths, you could either get them all close to each other, or you can also get them all close to the truth. And in the ideal case, you would have an individual calibration function for each sensor unit against a regulatory gradient for grade reference monitor. Okay, that's near the end. So I just want to point out that, you know, if you check out our website, I don't know if these slides are available to you guys afterwards, so I did put the hyperlink, but if in doubt, you can always Google search AQMD sensors or AQMD sensor guidebook or something, and the first Google result will take you to our webpage. And we do have a, you know, over 100-page PDF document that's a very community-friendly designed sensor educational guidebook. This is a product of a past EPA STAR grant that we received. And so it's not just this sensor guidebook, but it's also, we have engaging YouTube videos that are understandable by, you know, regular people. We have some resources for data analysis and interpretation. We used to have a R package that we developed in our group, and then we've since not maintained that at GovCran. But that R package was specifically designed to handle purple air data to make it easier to do the data cleaning and wrangling, and then the QC functions on the purple air data. So anyways, but our shining jewel of that STAR grant is the sensor guidebook. It covers all kinds of topics, and it's geared towards community members. It teaches them how to plan a project, an air quality monitoring project, gives them guidance on sensor installation and deployment. And it also clearly explains limitations and opportunities of low-cost sensors, because, you know, one of the most important things when working with the public is being upfront and honest about the limitations of low-cost sensors. Yes, they're easy to use. Maybe it tells you the truth about the air quality data, but there are limitations, and you shouldn't trust the data out of the box. We should calibrate it. So, you know, just not letting them go off this, you know, going off this cliff of expectations, and then running off and doing this air quality monitoring project, and then they bring the data to, you know, their local environmental agency and say, look, we collected data that shows that this factory here is doing this, but actually it may be just that it may be that the VOC signals are just correspond to the diurnal changes in humidity. But in their interpretation, it's like, oh, this factory is doing something terrible at nighttime, every night, when you, the government, aren't watching them and monitoring them. And here's our data. So it's like, and then if you go, you know, when you have to kind of counter that data, it just further breaks down the trust between the public and government. So it's important to lay those expectations up front early on. Okay, and then what else I was going to say? Oh, well, I'll come. So anyways, I'd like to thank, you know, my team. I do oversee a team of 7 staff. You know, Dr. Kwong, Randy Lam, Dr. Mozadek, Dr. Panji. They're my analysts. And then I have 3 wonderful technicians, Jenna, Noel, and Victor. And then I also like to thank my management because, so Dr. Feenstra, Polidor, and Lowe, because with their, you know, they do believe in low-cost sensors. They do believe that there is a future and important role for them to play in our agency's air quality monitoring strategy. And so, you know, as a service to the public, we want to not only provide our residents with that information of how these devices do, but also further push the industry to develop and improve their products because they may be, you know, it's going to grow into something big. So anyways, feel free to check out our website, aqmd.gov/aq-spec. That's the Air Quality Sensor Performance Evaluation Center. We have a general email line. You can also email me personally. And then if there's anyone looking for jobs, you know, just keep checking our website, aqmd.gov/careers, to see if there's a good fit for you to join somewhere in the agency. We do all kinds of things, not only science, but also policy, legal stuff, money stuff, technology development, and grants stuff. So yeah. And with that, I'll be happy to take any questions.
Okay, now open for questions and comments.
So, I understand that in Beijing, Shanghai, they had similar air quality problems, so you can do it at night.
Mhm.
Did you ever correlate the work with those people and see what they're doing and how it?
Yeah, that's a great question. So the question was whether our agency has worked together with Chinese pollution agencies to see if there's like compare our work and see if there's collaboration, right? So I do know prior to my time, there were folks who had previously visited other countries like Taiwan and Korea to cross-pollinate with their air agencies and low-cost sensor work. And then I went to Ghana. And then my predecessor went to Nepal. Working directly with Chinese government, it's a different, it's not straightforward, I think, politically. So yeah. Yeah. Yes.
Thank you for your amazing presentation. So, I was wondering, do we actually extract HUI from these local and low-cost sensors for different areas?
So I'm hesitant to say yes because air quality index is a term that is related to policy, is related to regulatory stuff. But one could there's nothing stopping you from doing the proper time averaging from a set of ozone measurements or a set of PM 2.5 measurements to come up with an air quality index. There are certainly many manufacturers that do that. Purple Air on their map, they display an air quality index. Clarity, IQ Air, all these, they display some version of air quality index. So it's like, I guess I'll just say, if you could do a good job at calibrating the device, maybe it's a locally derived air quality index, but it's still not something that would be used for like regulatory legal purposes. But it's better than nothing, and it is useful to have very granular air quality indices at a neighborhood scale.
Actually, the idea is that you have more devices that can measure the fluid. So
Mhm.
actually getting the HUI must be a little bit easier, but concerning the politician and regulatories.
Yeah.
To update the terms in the AQIs.
Yeah, that's a good.
The thing is, if you go to Texas and Middle East, there's a lot of flares
Mhm.
that actually doing the external combustion, that they have a lot of problem actually measuring the pollution of these flare devices. Do you have anything on this particular matter back in your team?
Yeah, so there's a sister group at our agency. They do optical and remote sensing around oil refineries because we do have quite a bit of them in the LA area. So they have I'm forgetting the instruments, but they have a whole variety of what very, very much research grade and expensive stuff to do like optical tents, to do FLIR, to do all kind of stuff to see if these refineries are flaring when they shouldn't be. But as far as the low-cost sensor space, what we have at the moment are total VOC sensors. They come in two flavors, metal oxide and PID, photoionization detectors. And they are just responding to some ensemble of VOC species, supposedly. And they may be useful for fence line monitoring. You could put a bunch of them around the fence line of an oil refinery, and maybe that'll that you can kind of figure out if there is a off property, plume happening at near the ground level. And so they can be useful for like neighborhood alerting, or triggering further investigation. So if you see a hotspot with a low cost sensor, that can then trigger that the agency pours more resources into deploying like, expensive research grade instruments out there to verify and see what's going on.
There's a cheaper method that is going on that they actually connect the parameter emission monitoring, like PEM, with a thermal sensor, and they reflect the thermal that is these flares are actually generating and get it back to the emission that they got the data from like PEM and 1D combustion solving. So this is something that they are working on in chemical companies that they hoping that they have some like preliminary data about the pollution of this flare. That's something that you in mind. And also the last thing is comparing PEM to these cheap actually sensors is a lot of countries don't have any access to these resources. So they're coming into the basic of the combustion problems. So they develop like small programming that they do parameter emission monitoring. And how you see the accuracy of the parameter emission monitoring?
I think that might be creeping a little bit in my wheelhouse. But I'd be happy to refer you to some folks that are in my sister group that do the oil and gas refinery monitoring. But I don't think I can speak quite properly to that question. Yeah, apologies. Yeah. I think I saw a hand. Okay, let's start with this. Sorry. Yes, go ahead. Uh-huh.
I want to talk about forestation. In Korea, there is a lot of air cleaner manufacturers. And we have all four air cleaners have local equipment there. And but the manufacturer wants the lifetime of local sensor is longer than 1 year because of the carbon contamination in the local sensor. So if there is a problem in the sensor, we have to clean the sensor by the software. So my question is how keep your local sensor clean, because you have a lot of natural phenomena with a high concentration such as wildfires. So how to keep the performance of the local sensor?
Okay, that's a great question. And so the question was, in Korea, they have air cleaners that are usually integrated with low-cost particle sensors, and the manufacturer will say, if it gets too dirty, you clean it yourself. So that's a very interesting thing. I have not really heard that often where manufacturers advise like a layperson to do their own cleaning of a particle sensor. But if I imagine the most accessible way for a regular person to do this is if they have like a can of compressed air that you use to like clean your keyboard or something. Maybe you could blow that through the inlet of the particle sensor. Other than that, I don't think it's a great idea probably for regular people to try to disassemble and do more other kinds of cleanings. I think you'll get worse data quality after that, but probably just trying to blow some compressed air through it. But yeah, that's really interesting. And you know, I recently learned, I met with some folks from a testing lab in Korea a couple months ago. And I didn't know this, but in Korea, they have a certification scheme already for PM 2.5 low-cost sensors, and you have to pass the Korean certification scheme to even be able to sell your product in Korea. And so, you know, we learned about their testing procedures and the certification. And so that's something that, you know, it'd be great if in the United States we could move towards as well. Yeah, thank you for your question. I think Pratim had this.
I think we really get
I have not. I have a new staff member. He comes from the satellite data. His background is in satellite data and AIML. So I am trying to collaborate with someone on a NASA grant. Who knows what's gonna happen to NASA now. So we did apply for a NASA grant to use satellite data and combine it with low-cost sensor data to develop. Actually, I'm drawing a blank on what it was about now. But it's something that we're just starting to hopefully get into. But you know, there is already some maturity developing in the low-cost sensor space and that intersection and collaboration with satellite and remote sensing experts. Someone, yes.
As low-cost sensor performance improves with newer models, how do you manage the phasing out of older models? Are you waiting for their lifespan to, you know, complete, or do you replace them as significant?
So our testing, one of the limitations of our testing program, because we do this for free, we do have staff and resource limitations. So we only test them for a couple months. And then if they do well, we'll test them in our laboratory chamber. But after that, we don't keep these things running long-term to investigate their aging or drift effects. So we don't investigate that. But some of our sensor networks that we do maintain, they are quite old models. So we just have to put in a lot of staff hours to drive out to each one if they have to replace like an ozone or an NO2 cartridge and do some compressed air dust blowing into them. They can be quite labor intensive. So they may be capital low cost, but capital, money wise low cost at the beginning. But with the subscription fees and then with the staff time needed to maintain these things, they may not be so cheap after all. And then as far as our publicly available performance reports for older models, we still keep those up. It's good for posterity. And it's also good so that, someone can still see, the evolution and improvement of a certain product line by a manufacturer. I'm aware of one study in the UK that took place over like from 2019 to 2023, where they did study the long-term performance of some of these particulate matter low-cost sensors. If you email me, I can send you that paper, but yeah.
Okay, it's at 5 o'clock, so we'll have just one last question from Dr. Wong.
Yeah, sorry to keep this so long. But first I want to thank you for the specs efforts, because now it's we or only going to install a new sensor. Go actually go to your website.
Yes.
And look for the model and check all the details. Very fun. Anyone hasn't checked it, but exactly try that. So my question is, I think they probably 2 years ago, they gave out more than 50 grants in different cities to install local house particle or air quality networks for exposure disparity analysis.
Okay.
So I guess maybe publication for also too. How can we use it? You think there will be issues, especially if we're trying to analyze the disparity.
Sorry, I was like multitasking. So there was an EPA grants, and then there's all these grantees are doing different co-location studies.
Yeah, co-location, not necessarily co-location, but trying to look at the exposure disparity, social-economic conditions, all the air movement exposure using the low cost perspective. So, how can we use this data from the profits? Like, are there overall R&Ds that we developing, but we're seeing in terms of coming up with new policies, trying to use it?
Yeah, so I can't speak at what the EP at the federal level might do with the results of these grants or the local communities where these grantees work. But one of the requirements of receiving one of these EPA grants is to develop what's called a QAP, a QAPP, quality assurance procedure, or something like PP, whatever, protocol procedure. And one would hope that these grantees using low-cost sensors, they've incorporated a way to co-locate and calibrate these sensors, first of all, and then secondly, that the data analysts are following, good practices for QC of the data and interpretation. It's interesting. A lot of grantees, they actually reach out to AccuSpec because we have a wonderful sensor guidebook and we have the expertise in QC and best practices sensors. So we've been asked to help out a few grantees with some guidance on developing their quality assurance practices for their grants. I can't speak for how the EPA would handle the results of all these different community air monitoring grants. But I think that there'll be some weight consideration given to the results of the grants, and maybe for future funding opportunities to get more expensive instrumentation and for more research-oriented methods into those communities, if the results of their low-cost sensor monitoring find something concerning. Yeah. Oh, I remember what I wanted to talk about.
I think we have to do sharing.
Oh,
different screen, I guess.
Oh, I'm so sorry. I was like, when I was multitasking, I was navigating to our website to show you like.
Shruti, can
I was just pulling up our website so you can kind of see example of like how we're a clearinghouse for low cost sensor performance data. Oh, there we go, that one. Thank you. So yeah, this is our website. So there's many, oh, there's one more. Oh, great, thank you. So yeah, I was just wanted to show our group's website. So we have many fantastic resources on it, but one of the most used resources is our clearinghouse of sensor evaluations. So this is a list of all the particulate matter sensors we tested, and then each one has at least one PDF report, a field report that walks you through, you know, how these sensors performed. And so it's like, oh wait, that's sorry. So like, for example, if you click on each product, you can go to that page, and then we have, for this one, we have a field and a lab report and a summary report. So you can see, you know, we try to be as transparent as possible. So we just give out the time series and all the data. So you can see for yourselves how these things did compare to a reference monitor. And the last thing I want to mention is that EPA, they did hand out some community co-location shelters, so that anyone in the public, they can bring their low-cost sensors to these co-location shelters, so it can be co-located with a regulatory grade monitor, so you can collect that data. So in Florida, there's 4 of them. There's one in Tampa, Winter Park, Jacksonville, and Davie. And so if you Google search EPA's community sensor co-location, they at least have information up for the Jacksonville one. But yeah, so that resource exists for community scientists and even for academics if you are looking for a place to co-locate and calibrate your low-cost sensors against regulatory grade measurements.
Okay, so let's thank Dr. Mui again. Okay, that concludes today's program, and we're going to have a happy hour at the SALT. And before that, I just want to make one quick announcement. So tomorrow we are going back to the Coral Gable campus, the Frost Institute for our Thursday and the Friday program. It's not going to be here tomorrow. Okay, just wanted to remind you of that. So now please enjoy the happy hour at the SALT. Thank you.